Hello，Hello，Hello，Hello，嗨，
Hello，testing 1 2 3。你的 Zoom 呢？Zoom 你稍 Zoom 听得到吗？Testing 1 2 3。test。你用你自己的 laptop 的麦呢？你用自己的 laptop 的麦。
现在是我自己的。
所以不知道外面能不能听懂。
也是没有声音。
诶，
你把 link 给我放进去。
我给你发一个你。
有一个人 join 那个来听。
你是要加 Zoom 还是加什么？
随便啊，Zoom 都可以，不要加。一个是 master。
Zoom 的。
要 share screen 对不对？
testing。那边要 testing。
给我靠谱。
哦，好。你是 speaker 是吗？诶，现在是谁放的？
对了。
啊。 发了个邮件，你可以在 YouTube 直播上看看有没有声音。
你用这边可以。
好，
我是分你的，开麦就可以。这也没有麦，这没有都可以。这个是毛丝。就跟 audio 有了。他要 play 他的 video， 刚才那是
因为是用的我的，
你在 switch 回
我在 switch back to。
应该可以的。
Hello, hello, testing 1, 2, 3, 4, 5, 6. Second test. Second test using creative. Hello, hello, test. Third test, third test. 4, 5, 6, 7, 8. 这边很小声 ，OK 啊，蛮小声啊。我听得到。Hello, hello, testing 1, 2, 3, 4, 5, 6, 7, 8. Hello, 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 hello. 有啊？Hello, hello, test, 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 test. Test 1, 2, 3, 4, 5. Test, 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 test. 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 不是你自己的 laptop， 应该不是。坏掉。啊，应该 OK 的。Hello, hello, test 1, 2, 3, 4. 可以用你们可以移来上下。有 checking 你走路，我turn off 了，我 turn off 了，turn off 了。它跟着你走，它有一个 feature 跟着你走 ，AI 啊。等下它移来移去，它哇头晕。
Mic check 1, 2, 1, 2, 3, 4. 1, 2, 3, 4.
这个 PPT 也是你做的，是吗？
Okay. Good morning, distinguished guests and friends. Hello, ladies and gentlemen. Welcome to the 2023 Joint Forum of Nanyang Technological University, Tsinghua University, and the National University of Singapore on flexible electronics technology. I'm Yihui Zhang from Tsinghua University. It's my great honor and privilege to chair this opening session. So this joint forum is a testament to the rapid developments and innovations of the field of flexible electronics. So we are very honored to have three leading institutions in this field: Nanyang Technological University, Tsinghua University, and National University of Singapore to host this exciting event. Okay, today's forum provides a real opportunity to learn and interact with the leading scientists in this field. They will share their insights and pioneering works at the forefront of flexible electronics technology. The essence of this gathering is to facilitate the exchange of ideas, to foster collaborations, and to explore the latest technological trends that will undoubtedly shape the future of this field. Now I'm pleased to introduce Professor Xiaodong Chen from Nanyang Technological University, a co-chair of this joint forum, to give his opening remarks. Let's welcome Professor Chen to the stage.
Okay, yeah, very good morning, everyone. So welcome everyone to be in this campus. And also really our great honor have our colleagues from Tsinghua University and also National University of Singapore to be here to come this joint forum of flexible electronics technology. No doubt this is, in fact, it's almost the first event in this campus, which is such kind of a cross campus, across university, also across countries of this kind of forum. So for me, I think this kind of technology forum is very important for a few reasons. One reason is really promoting the emerging technology in flexible electronics developments. So everyone know already. So this is really kind of emerging developments. I really need a lot of efforts from multidisciplinary, not only about materials chemistry, biomedical engineering, electrical engineering, mechanical engineering, even medical school, and so on. So this is something very, very, very important. So that's why we feel this kind of joint forum really can promote this kind of more collaboration. And also, importantly, my personal view is very, very importantly, not only about this forum in this venue, I think very important is interaction, especially after COVID-19. So we almost stopped for 3 years, no interaction at all. So this is kind of forums really provide a lot of opportunities for us for this kind of promoting international collaboration and also interactions. So without further much to do, and then I will hope everyone to enjoy this event. Thank you very much.
Thank you so much, Professor Chen. Next, please join me to welcome Professor C.T. Lim from National University of Singapore to give his opening remarks. Welcome.
Thank you very much. Good morning, everyone. Firstly, I want to thank Professor Chen as well as Professor Feng for including us from NUS as well as the co-organizers. This is actually a very, to me, a very prestigious joint forum on flexible electronics, by three very leading, world's leading institutions. And although we may be gathering as three separate, entities, I hope we will be, united as one, intellectual might with, we're driving the same aim, which is to share, to learn, and also to shape the future of flexible electronics. I'm glad that actually this forum also includes some really leading and pioneering researchers in this area. So I hope that all of you can also not only learn from them, but also be inspired by them. But most importantly for the participants, whether physically or virtually, hope you also would challenge the speakers, the ideas they are presenting, and then we will engage in a very meaningful dialogue, and then we will all learn from each other. With that, thank you so much.
Thank you, Professor Lim. And next, let's welcome Professor Xue Feng from Tsinghua University, also a co-chair of this joint forum, to give his opening remarks.
Hello, everyone. Professor Zhao, Professor Xiaodong, Professor C.T. Lim. As one of the organizers of this joint workshop, I'm very pleased to say it's finally the time to rebuild our collaboration ties. During the last 3 years, many conferences and collaborations were frozen or waiting for the right time to restart. So I'm very happy to be here today. So our communication never stopped by the COVID pandemic. I would like to express my gratitude to Professor Xiaodong Chen. Thank you for always coming up to inspiring ideas and suggestions to make our collaboration better throughout the last 2 years. I also would like to thank Professor Gao, together with all other professors and my colleagues from Tsinghua University, who involved in this collaboration program. Today, we are also pleased to have Professor C.T. Lim and other professors from NUS to jointly host this workshop. We truly hope to build a connection and regularly update our last works on flexible electronics technology. In recent years, flexible electronic technology is undergoing rapid development and innovation. It's far more than the application we have seen. On one hand, flexible electronics extends application of the electronics to environments by creating flexible, multi-functional units that work well in soft hardware service and alternative space. On the other hand, it's also provide a new way to further enhance the electronic functionality and performance by integrating flexible chips and flexible circuits to produce for flexible IC and fundamental industry. So in this way, flexible electronics to change the way of life in many aspects, such as Medicare, human machine interface, and Internet of the Things. So I believe this workshop provides a valuable opportunity for research scientists. I'm grateful to friends and colleagues who come to share their knowledge and ideas. So I'm sure we will have a fruitful and rewarding experience today. I wish you fully enjoy this important joint workshop, and I'm looking forward to this wonderful experience. So thank you very much.
Thank you, Professor Feng. Next, we'll step into the opening lecture of this joint forum, and I will be very honored to chair this opening lecture. The speaker of this opening lecture is Professor Huajian Gao. While most of you must be very familiar with Professor Gao, I will give a very brief introduction to him. Professor Gao received his bachelor degree from Tsinghua University and his bachelor and doctorate degree from Harvard University. He served on the faculty of Stanford from 1988 to 2002, and as the director at the Max Planck Institute for Metals Research from 2002 to from 2001 to 2006, and as the Walter Annable Professor of Engineering at Brown from 2006 to 2019. At present, he is one of the 6 distinguished university professors at Nanyang Technological University, and also scientific director for the Institute of High Performance Computing in Singapore. Professor Gao's list of honors includes elections to UK Royal Society, US National Academy of Sciences, US National Academy of Engineering, American Academy of Arts and Sciences, German Academy of Sciences, Chinese Academy of Sciences, and Academy European, as well as academic awards, including the Timosenko Medal and Zolli Hill Prize, the 2 highest lifetime achievement awards in solid mechanics. So without further ado, let's welcome Professor Gao.
Thank you, Yihui, for the kind introduction. Yeah, I'm very honored to kick off this very exciting workshop. Thanks, Xiaodong and Xu and CT for inviting me here. Okay, so my field is solid mechanics. Right? I don't really do flexible electronics. It's through collaboration with Xiaodong, I get exposed. So the leading, the main players for the topic I talk about today is Xiaodong and his postdoc Fei Long, and my postdoc Dong. Dong is also my former students. So I have to make confession. My contribution is very minimal. So I'm just here to tell you what they have done. Okay. So the PD-induced shape morphing. The reason I would like to talk about this is an example of how mechanics and material and flexible electronics can be combined to produce some new ideas. Okay, let me start with the peeling. Right? Peeling has a long history in mechanics. Right? The main player that initiated the whole research on peeling is by Ron Rivlin, with a very famous mechanicians. if you're in mechanics field, you know Rivlin. He has a lot of theories on polymers, large deformation, continuum mechanics, including peeling. Peeling is when he was an engineer, actually, in a British a rubber producer research association. Later on, he became professor at Brown University and Lehigh University. That's afterwards. Right. So Professor Rivlin had many contributions. One of the contributions he has is to develop this first theory on peeling. He devised very interesting setup, right? Just like a substrate here, tilted at the angle theta, then he put a weight mg, right? So here's a rubber tape. So he could measure the work adhesion. He could measure work adhesion as he increased the weight. Then the weight would drop at a certain velocity, right? He would actually measure the work adhesion as a function of the time of the stripping or velocity. Okay, so he was the first one to realize, to measure work adhesion, also show work adhesion depends on rate of the velocity of peeling. All right. So he has many theories. One of the most famous quote I have here is when at a conference he was presenting one of his theories, and there was a participant asking the question, "What is the application of the theory?" So that's the famous answer he gave. He said, "That's not the question one gentleman asked another." He has quite a character. Right. Another scientist who made a lot of contribution to peeling is Kevin Kendall. Okay, Kevin Kendall standardized the peeling test as we still use today. Today, the standard peeling test today is have this so-called 90-degree peeling. You have a tape, you measure work adhesion, so you measure a critical peel of force, F, right? And W is the width of the tape. So by measuring the force per unit area, right? Force divided by width, that gives you the adhesion energy. Very convenient. Today it's almost standardized in the industry. Kevin Kendall also have this formula here. Those work adhesion energy is proportional to the force, pure force, times the peeling angle. And this is the angle. So phi equal 90 degree, you have this case, right? This formula here. Actually, Kevin Kendall has his, more famously, he proposed this so-called adhesion paradox in one of the books he published in 1982. It's called Sticky Universe. So the paradox he poses is following. He said all atoms and molecules adhere with considerable force. For example, van der Waals force, the weakest interaction, right, is pretty strong actually from engineering point of view. It's about 10 to 100 megapascal. However, ordinary objects do not stick together, right? like desert, sand, or they're not sticky. Table is not sticky. So he proposed this adhesion paradox. But of course, there's a story behind it. I won't go into detail. But he was the one who proposed this adhesion paradox. Okay, there's many applications of peeling. I would like to quote an example by one of our organizers, Professor Feng Xue. So he's in 2006, 2007. He and John Rogers and Yong Gang showed that by control the speed of peeling, okay, you could do transfer printing. Okay, so at high velocity, right? So you basically have a viscoelastic stamp bound to the film. The film is whatever device you want to print, which is elastic, and a substrate. So the idea you want to reversibly place this film or this device on the substrate, because the energy release rate between the two interfaces are different. In the viscoelastic elastic interface is highly rate dependent, as Rivlin already showed. So at a high velocity, the energy release is high, and low energy release is low. So you could have two domains. One you can pick up. Okay, you can have this interface is stronger than this interface. You could use this high velocity pickup this device. At a low velocity, you could place printing at low velocity. So as shown here. Right? So this is a transfer printing, one of the important application, modern application peeling. Right. So the 2D to 3D shape morphing is also become very important because most electronic devices, you know, are 2D, right? 2D, they're using photolithography processing. You have 2D is in a planar devices. But if you can, for example, if you have a technology, for example, flexible electronics and so on, you like to make 3D devices. Okay, you want to make substrate printing electronic circuits on 3D surfaces. So there's a lot of superiority or advantage making 3D. So this is called 2D to 3D shape morphing. How do we make a 2D structure or 2D device in 3D? So I have to enhance the performance. And there are some strategies in the community doing this, mostly involve external stimuli. For example, using light, some surfactants or some pH or other things. And Yi Hui's our chair here has this famous paper with John Rogers and Yonggang on the buckling induced shape morphing. Okay, I will say a little bit more here. Okay, so this is the one page showing Yi Hui's work. So so now by using transfer printing and structural buckling, essentially I do the transfer printing when I have the substrate stretched, right? Substrate stretched. Then I could print in some some circuits or some structure on the substrate. Then I release the strain on the substrate that causes spontaneous buckling. Now, if you can use your 2D precursors correctly, design the 2D precursors, the buckling will induce many, many interesting architecture or structures, as you've shown here. Right? Very important technique, and Yi Hui is still pushing this frontier. Okay, so the question of interest to us is the following. In some cases, it's more desirable, or it's also desirable to have accomplished 2D or 3D shape morphing in freestanding structure, so without a substrate, okay? You want to make some device that does not depend on substrate and free of external stimuli. For example, using inert plastics, which is non-responsive to any stimuli, inert plastic, using this as substrate for electronics. Okay, how do you achieve this? This is also a very interesting mechanics problem, right? So the inspiration, we want to use peeling to build eigenstring. So I call this eigenstring engineering, right? Just this video show here, right? Very commonly, and you can do this in your office, peeling a Scotch tape. After peeling, the Scotch tape will spontaneously assume a curvature, right? So why is that? So this is one of the eigenstring. So because the Scotch tape can undergo plastic deformation, which is irreversible. When something is irreversible, okay, we call it eigenstrain. Eigenstrain is a strain, it's not associated with stress. When you release the stress, the strain still remains, right? So during this process, we build a tensile eigenstrain at the back of the tape and build a compressive eigenstrain at the front of the tape. Okay, these two eigenstrains, like a potato chip, in fact, you heat on one side and cool on the other side. You cause this spontaneous curvature. Of course, this phenomenon is known for some years, right? So this phenomenon is known for a long time. Okay, so let me also quickly mention the theory of plastic peeling started in the 1980s by Professor K.S. Kim at Brown University. So Professor Kim has a look at energy balance, accounting for plasticity, plastic yielding in the film. Right, so this is work done by the peeling force, the first term, the peeling angle. Second term is adhesion energy. So these two terms are what Rivlin and Kendall have in their theory. But Professor Kim has included the energy dissipation, energy dissipated in the plastic deformation, plus residual strain energy. Right? After a stress release, you still have strain energy. So this two terms. So he has developed a very nice theory accounting for plasticity, but still using this to predict the work adhesion or adhesion energy interface. So all this previous work, that goal, the objective, is to relate the peeling force, peeling angle to the work adhesion at the interface focus, right? But today, our focus is different. Our focus on peeling, focus on how to do the shape transformation while peeling, right? While there's eigenstrain. So now I'm going to talk about the work done by Fei Long, who's mainly conducting experiments, and Dong, who's developed theory and simulation. Right? So peeling-induced shape morphing theory and experiments. So now let me introduce this angle more clearly. I already mentioned a couple of times. Phi is a peeling angle, right? So here, the Scotch tape peeling at the direction. So this angle is called peeling angle between the peel-off part and the substrate. Right? We assume it can also take negative values, because you can imagine I can peel on the other side, right? Both sides can be sticky. If I pick on one side, it's positive, the other side be negative. And delta is another angle which is rarely talked about in mechanics, right? In all existing theories, Rivlin and Kendall and Kim, they all concern about work adhesion. So you don't need this. But for shape morphing, it's important, which is called deviation angle. The deviation angle is, look at top view, you will see deviation angle. Look at side view, you see the peeling angle. Look at top view, the peel off part do not have to coincide with the sticky part, right? You can deviate at angle delta, right? So delta is an angle from short axis film to detaching line. So both, according to this definition, both peeling angle, deviation angle can vary both positive or negative, but deviation angle is clear. But for peeling angle, we can peel from both sides. So one side is positive, the other side is negative. Right. So here's some simple demonstration of the coiling mode we call. So what is coiling? Coiling mode we define as a case when delta equal to 0, no deviation, purely peeling, right, in the classical sense. So in this case, you get coiling. Here's the experiments. You can see that you get a coiling, right? And simulation. Right. So you can, right? So which you can actually compare side by side and match those very beautifully. Okay, so one more. Okay, so this is a coiling mode, right? When delta equal to 0. Another mode is when, let's see, we define as so when actually it's independent. So the helix mode on deviation, focus on deviation angle. The deviation angle is non-zero, for example, 45 degrees, right? So it turns out the coiling mode and the helix mode can be decoupled. So let's, for example, take phi equal to 180 degrees top view, right? So you can see in this case, the peeling is in the horizontal direction. Sorry, the sticky in the horizontal direction, but you're peeling in the vertical direction. So in this case, you have 45 degree deviation. Okay, so the sticky is in the x direction, but you're peeling, right? You're stretching it, you're pulling the y direction. So you get a helix out of it. Okay, the simulation here. Right. So there's two fundamental modes we're talking about here. Right. You can by intuition, right? By combination of two modes will allow you to program various structures. Okay, for example, you don't want to make a flower, make a very, very beautiful flower from orchid, right? Like botanic garden. So you can use a 2D plastic film like this, right? And you can peel here. We draw strips. This blue strips means the peeling direction. You can peel in this direction, here in this direction, here in this direction. And red means the other side, okay, by reversing, turning a negative peeling angle. By peeling on the opposite side and red color peeling this way, you can from this 2D precursor generate a flower, generate orchid like this, right? So now we have, let me speak briefly about theory. Theory is pretty takes me quite a while to talk about the detailed theory. In interest of time, I won't go into detail and just show you the theory of coiling mode. Basically allow us to predict the curvature upon release, right? So there's a lot of quantity, mathematical quantity here, but most important are the following, right? Epsilon 0 is the yield strain. So the strain where material undergo plastic yielding. And epsilon B is the maximum strain upon release. So maximum strain, which usually happen at detaching from, peeling from, right? So this R here. Once you know R, you can, this one, you can, depends on R is between 1 and 2 or bigger than 2, you can use this form to predict it. Here, H is the normalized hardening modulus. So this is because of plasticity, after yielding, you have a modulus, which is what we call hardening modulus. E is Young's modulus. So that's known, right? That's yield strain is known. So only R is unknown with the curvature here. But R itself, unfortunately, is not as straightforward. Depends on a 4 equation. You need a set of equations to determine R. Right? This equation involves the following quantity: like thickness of the film, right? Adhesion energy of the interface, thickness of the adhesive, right? Width, and so on, right? Basically from geometry of your film and your adhesive, you solve a set of equation, you can solve this R, using R to predict the curvature. So the theory is pretty, it's a detail is in the paper, which you can read. But let me show you this FEA. We use a finite element to validate the theoretical solution. So they match reasonably well, right? So here's a little bit deviation. So don't tell me this is due to some FEA problem or some kind of a simplification theory. And also experimentally we can validate, right? So here's we predicted curvature as a function of film thickness. Right? Our theory predicts the curvature will decrease the film thickness, which is understandable, right? Yeah. So as the smaller the film thickness, the larger the curvature you'll be able to bend, and so yeah. And also here you can check the predicted curvature as a function of adhesive thickness. We show the curvature decrease as function of adhesive thickness as well. You can check various quantities. Oh, by the way, the peeling force is not part of our theory. The peeling force is a part of a classical theory, right? You can use Professor Kim's theory to predict the peeling force, right? Which we didn't know. In our theory is only the curvature. This is the new thing. So we didn't. So the peeling force belongs to the classical related peeling force adhesion energy. Okay, so we can also check the predicted curvature theory, predicted curvature versus function peeling speed, and predicted curvature as a function peeling angle. They all agree. They all agree pretty well, right? Okay, so the second mode is called helix mode. Theory helix mode. Okay, this is on a deviation. So the unconventional peeling. So peel at an angle deviates from the conventional direction. So in this case, you can calculate using this a similarity relationship of this little triangle A prime, B prime. Okay, you ask question, what is the number of coils formed by this newly peeling segments here? Right? It can be calculated as OB prime divided by the peripheral length of your coil, pi d. It can also be calculated as a function of as a ratio between OB, OB this length, deviation length, and the pitch, so-called pitch, the distance between two neighboring coil. Right? So this one will give you immediately a theoretical relationship predicting helical pitch as a function of d is the diameter of the coil, right? The delta is deviation angle. And you can see that agree with the experiment very well. Here's theory, right? Theory and experiment. They agree almost on top of each other. And more importantly is the diameter, right? Coiling mode, the d, is independent, more or less independent of the deviation angle. This means the two modes can be decoupled, right? So the deviation does not influence the coiling as much, right? So negligible influence. So the two modes can be decoupled. So that's facilitated theory to make it's a great result, a great implication for simplicity theory. Okay, so now we say because they can decouple, we can individually program in phi and delta to create complex geometries, right? One example, if you want to have a spiral coil, right? You don't want to have a simple coil. You want a spiral. What do? You can gradually decrease in peeling angle. For example, peeling on a curved substrate, right? You're peeling one direction, but have a substrate coiled, have a substrate curved, right? Like in this case. So peeling angle is continually changing during the process. You can have a spiral-like structure. Or you could have gradual increase of delta, right? Changing, you can have this gradient helical structures. Okay. And or you could have like a gradient, but you could also have a bend, right? So this was shown here. Okay, you change direction, in the middle, and so you have this structure here. Or you can change in both, right? By changing both phi and delta same time. So you could have a spiral as a same time as helical spiral coil structure, right? So you can have various phase diagram. So one is the phi, one is delta, right? By changing, by programming both phi and delta, you can generate various sophisticated structures. You can design a thing, right? If you have a platform. And so more complex shape, you can use another additional degree of freedom. For example, you can have a plastic film and adhesive only on discrete regions, not continuously adhesive, right? You can have adhesives only in several spots. And then you can create this triangle, so polygons, right? For example, shown here, right? So the plasticity, you build eigenstring discretely, or you build eigenstring only at certain parts, right? You can make these polygons. So here's no curvature because no adhesive. Or you can build this so-called hyperboloid structure. Okay, by multi-step, by pitting one direction and another direction, right? You can generate structures. All right, so you can play with this essentially using phi and delta and adhesive regions. You can play with this, generate, can compete with Yihui. Right. So here's some examples showing here, right? Some interesting structures, and by the way, these are predicted structure using FEA, right? This is experiments, can predict it pretty well. And here I just show you some pictures of movies of 3 selected structures, right? So one is, right? So one is the top one here. Okay. Oh, let me show it again. Right, you peel on this side. Yeah, then you peel on the other side when you generate this structure here. Okay, so here's another example. Right, you generate this structure here. Right, or here's a strange looking chair. Okay, in any way, so in principle, the possibility is unlimited. Okay, so some discussions, this method is quite general because most material exhibit plasticity. Okay, most material, like metals, almost all metals have plasticity. So you can apply this to generate structures and using pitting to generate eigenstrain in metals. That's pretty obvious. A lot of polymers, like semiconducting polymers and things, you can use this, and you can also do it at micro scale, smaller scale, and because pitting is pretty general phenomenon, right? You can do it probably nanometer scale is questionable, but micrometer scale, so certainly it's doable, right? Because nanometer scale, you have van der Waals for a lot of other things coming, so it's probably will add some complications. Even if your film is elastic, suppose you have a film that's no plasticity, right? It's just elastic, like elastomers. They do not undergo plasticity. But in those cases, you can still use this technology, use this method to generate 3D morphing by adding a plastic mediator. For example, the film is elastic, right? But you can add a plastic part of it and have a composite structure. So that composite structure, because you have plasticity, eigenstrains still can build in a plastic part of the structure. So you can still generate the morphing, right? So the morphing is not limited to plastic, but through composite, you can extend this to even elastic materials. Okay, some 2 examples that Fei Long has demonstrated. And here's some functional 3D devices. For example, a photo detector, right? You want to detect the laser light from different directions. Obviously, 2D is limited, right? 2D can maybe detect one direction, but once you're making 3D, you can, through the pitting, you can do the morphing to 3D, you can detect laser signals from various directions. Another example is a piezoelectric energy harvester, right? Suppose you want to harvest energy from environment, such as Professor Wang Zonglin is very, his energy institute, right? You want to collect energy from the environment, from vibration. Just have a 2D, because the resonance mode is limited, right? The 2D, the resonance mode is limited. By having a 3D, then you can tune your eigenfrequency to match the environment, right? So the resonance, you can maximally collect the piezoelectric energy. So that's shown in this here. So 3D plate, you can also extend to 4D. So you can use, for inert plastic, right? They're non-responsive. But suppose you use a responsive material, right? Can you respond to external stimuli? You can use a peeling to generate structure, have a structure further respond to external stimuli, right? For example, respond to humidity and things, right? So we call it a 4D morphing. Okay, so I saw our chair has stood up. Let me put a summary. So my message here is the classical theory of peeling serves as a basis for measuring adhesion energy or work adhesion, and with numerous applications, including transfer printing. It's very, very important, right? Peeling, both in mechanics and also in flexible electronics and other fields. Now we have more opportunities. So new theory of peeling-induced shape morphing can serve as a basis for fabricating freestanding 3D architecture for functional devices free of external stimuli or substrates. And peeling-induced shape morphing is an example I would call more generally eigenstring programming, right? Because plasticity is one type of eigenstring, but we have many other types of eigenstring, okay? Like heat thermally generated or transformation generated, lot of eigenstring. So this eigenstring programming or eigenstring engineering can apply to any material capable of plastic form as well as to elastic material, well, plastic mediator. Is that, let me stop here and thank you for your attention. Thank you. Very interesting.
Thank you so much for your very inspiring and a very informative talk. We can always learn so much from Professor Gao's lecture. So now it's time for questions and answers.
Hi, Professor Gao. Thank you for the talk. So at the very beginning, you taught us the peeling rate will affect the adhesion energy. But later on, you use the angles to recognize the peeling. So anything missing the study, so I didn't see the peeling rate.
Oh, yeah. Right. Okay. Yeah, so yeah, let me clarify a little bit. Yeah, here, right? Here's a peeling angle. Peeling angle here does not mean peeling angle affect adhesion energy. Okay, gamma A adhesion energy is a material constant. This is only dependent on material, right? But the peel force is a critical force of peeling. That depends on the peeling angle, right? Peeling angle. So by measuring, this can be measured. This is known, can be designed. By measuring peeling force, you can determine adhesion energy. Okay.
Any other questions?
Hi, Prof. Gao. Thank you so much for your wonderful talk. And I have one possible thought that's about the application for this new method to make a 3D curvature and some structures. I'm thinking about whether it can just apply some, for example, chip memory polymers and to attach some solid metal or some semiconductors to make it be useful for some actuators that controlled by temperature or the light is also possible.
Shape memory polymer as a base material. Right?
Yes.
Yeah, so basically this one apply to anything that undergo plastic deformation. If it does not, you can add composites. So it's very general, I would say, right? So the question is, of course, yes. I do not see limitation, but of course, furtherly, your idea would be how to use shape memory as additional functionality, right? That can be many new ideas, I would say. But this eigenstring programming, this idea is in essence very, very general.
Yes, because you can, or I think you just use by the mechanical structure design, you can just control the different rigid points, and you can just control the, for example, the moving direction. You can control the polymer, and polymer can just maybe have some balance force between the rotation with a rigid substrate, and then control the moving direction. Maybe this is possible. Yeah.
Okay. Yeah.
Yeah,
Very interesting thought. Thank you.
Professor Bill, very nice talk. My question is, does the width of the strip influence this deformation behavior? If we have a non-uniform width, what will happen?
Non-uniform, yeah. I think I gave a talk last year also. Question, yes, we haven't considered that. Yeah.
Okay.
The width being non-uniform. I would the theory can be easily modified in that case. Yeah.
Another question, because you have obtained some relation between this mechanical property and final geometry, can this relation be used to measure some mechanical property?
Which property do you have in mind? The mechanical property here, Young's modulus is all given. Right?
At least I think the plastic capacity, deformation capacity of the interface, because this I know the interface,
string, right? Like predicting U string.
Yeah.
From the yes.
Okay.
I can do that. Yeah.
Okay.
So then basically you do the peeling and measure the curvature, determine U string of the material.
Yeah.
Yes. That's belong to the classical theory. For example, in Professor King's theory, I think already there.
Okay. Thank you.
Professor Gao, thank you for your interesting and beautiful work. Professor Feng Shui have been telling us that the flexible electronics has been the flexible electronics has been now we need to develop flexible electronics that relates its function to its shape or its morphology, and the function should be determined or very correlated to its shape and morphology. So I think the method or the method you developed here can be used to do this kind of research. So for the devices, especially for the semiconductors, the stress or the strain of the material should determine its electric properties. So I wonder how much stress or how much strain do the soft or the plastic endure during this peeling process, and how much strain can remain at the final of its 3D morphology. This can be predicted by the theory here.
How much strain remains? You mean the eigenstrain?
Again.
Yeah. So that's yeah. So that's one of the quantity in the theory here. Right. So this is essentially this R is the maximum strain. How much strain is related to don't right? Yeah, the residual strain is related to this R, which we can determine from the theory here. Yeah, basically it's one of the quantity predicted by the theory. So after PDing, what's residual strain in the structure? Of course, that's what leads to this curvature.
That will be very important if we want to design 3D electronic devices with this method.
Yeah. Thank you for the comments.
Hey, Professor Gao, thank you very much for your talk. Currently, we are doing a work similar to that, because we are curve a thin membrane on a nerve, and then the thin membrane will return back if the bending stiffness is very large. So can this theory help quantitatively characterize the bending situation and return back with liquid interface?
Liquid interface. Oh, yeah. Yes. I believe this. Even if the liquid interface, if the PD induces high curvature, that will induce eigenstrain. Then as long as eigenstrain play a role here, it can be, but probably not by this theory, right? Because in the liquid case, the liquid itself, because we assume a substrate, right? We assume a solid substrate. If you have a liquid, then you have to solve this essentially a solid product, film plus liquid. And so that was, it's an interesting problem. Yeah, we'll be happy to talk to you actually. Are you doing this research?
Yeah.
Okay.
Thank you.
Yeah, let's talk. No, let's talk about it. Yeah.
Thank you very much.
Thank you. It's okay. Thank you.
Well, our next speaker is Professor C.T. Lim from NUS. Professor Lim is currently the NUS Society Chair Professor of Biomedical Engineering and the Director of the Institute for Health Innovation and Technology at the National University of Singapore. His research in developing wearable sensing technologies for healthcare applications is truly groundbreaking. He has already published over 400 journal papers, over 400 plenary and keynote presentations, and founded 6 startup companies. He's widely recognized for his contributions to the field of flexible electronics. Professor Lim has received numerous awards for his groundbreaking research achievements, including the Leisure Lifetime Achievement Award for Mentoring in Science, Asia's most influential scientist, highly cited researcher, IES Prestigious Engineering Achievement Award, and many others. So today, Professor Lim will share his insights on the flexible microfluidic wearable sensors for healthcare and health metaverse applications. Let's welcome Professor Lim.
Thank you very much. Thank you, Professor Chang, for a kind introduction. So today I'm going to talk about some of the flexible microfluidic wearable devices that we've been developing both for the healthcare and then recently for what we call the health metaverse. To stand here. Oh, yeah, okay. Let me see. Okay, yeah, so I'm going to start with this particular slide. I know we are all aware that the AI has now been used in healthcare. Actually, this particular report is just hot off the press. It was just released over the weekend. And it's actually done by the written by the World Economic Forum. So healthcare actually has been used a lot now in starting to be deployed in healthcare. And the reason why I mention this is that in order for AI to work, actually we need a lot of data. So there's this interesting article that said that there's no AI without data, although it's not applied to the healthcare area, but more into the advanced manufacturing area. It also is true when it comes to application of AI. But actually, I also know when I was giving this talk last year in another forum, I mentioned that there's also no data without technology. So I shamelessly put my name there because no one has said that. So there's no actually data also without technology. And the reason why we need technology is because, which is one reason in healthcare, we need to develop all these wearables, is because we need to be able to collect not only accurate, but also relevant, timely, and complete data. And that's one reason why we're going to wearables, because wearables will help us to collect the data that we need in order to drive AI in healthcare. And certainly, I think if you look at this particular chart here, which is focusing on the US market, you can see that the wearable medical devices being used is actually growing quite exponentially. This is not just talking about diagnostic devices, but also therapeutic wearable devices as well. And it's growing at a compound annual growth rate of 25.7%. So certainly wearables are here to stay. And the reason is because it can help us to collect the kind of data that we need in order to implement AI in healthcare. And so our aim is to develop wearables in order to collect data, because we know that with this data that we have, it not only can help us to understand a person's health, but also the health risk and also how health can be managed. In fact, for myself, even I also wear an Apple Watch, which is a form of wearable, which is also collecting data from me, and I can see, over time, the last few weeks or year, how active I have been and so on. So actually, my own area has been in the area of mechanics, similar to Professor Gao, although I switched to more into the area of biomechanics and mechanical biology. So we've been using that to develop a lot of devices. But we found that as the year gone by, we've been actually using microfluidics to harness our knowledge in mechanical biology to develop diagnostic devices. So this is actually where I'm going to focus on. We have been actually developing microfluidic devices to do a lot of things like in vitro monitoring, where we use microfluidic device to isolate, for example, exosomes, microvesicles, and cells for us to do diagnosis. But when a number of years ago, when we were talking to some of our clinicians, they wanted us to see if we can develop devices where we can implement on, where a person can wear and be able to monitor them as well. So when I was looking at all the literature being published, there are a lot of work published in the area of sensors, in particular solid sensors. So I thought, since our expertise is microfluidics, we'll see if we can use microfluidics to develop wearable devices. So that leads us into developing microfluidic wearable devices to do in situ monitoring. But of course, there are a lot of challenges, because if you look at a microfluidic device, this is typically how it looks like in the lab. It's made of PDMS mounted on the glass slide and then put under the microscope. So you input samples and you observe under the microscope. So how do we move from here to something that's wearable on your skin? So that requires three components. The first is we need to have materials that's flexible, that's skin-like. Second is, what is the detection mechanism? What is the sensor or sensing element they're trying to use in the device? And third, of course, we need to do integration, including encapsulation, bonding electronics. So we were looking at this, and we developed this microfluidic device that make use of a flexible material. And then what we did was we incorporated the sensing element, which is actually the liquid metal. So if you look at this particular device that we have, it's a liquid-based sensor, including microfluidic channels inside this flexible substrate. And then we have a conductive liquid, which is a liquid metal. So this liquid active sensing element is highly deformable. So it can give us very sensitive sensor. And we can also customize the microchannel to tune the sensitivity. So if you look at this device here, this is one of the first device we developed a number of years ago. It's on a soft substrate. Either we use PDMS or EcoFlex. And then if you look at there's a silvery line there, that is actually the microfluidic channel, and it's filled with the liquid metal. So liquid metal we use is typically E-gain. It's a eutectic gallium indium. So it has about 75% gallium and 25% indium. However, it has very low viscosity. So at room temperature, when you pour it, it's almost like a liquid, like water. But it has very low toxicity because idiom has been used in dental fillings and gallium has been used in trace nutrients in vitamin pills. So it is actually not toxic to the human body. And that's one reason why we use this liquid metal. So that the the working principle is actually quite simple. We have a microfluidic device like this with a liquid metal. And if you were to press it, what happens is the microfluidic channel changes the shape, displaces the liquid metal, and that causes a change in the conductance. So by looking at the electrical signal that we output, we can actually determine whether the force is pressing, stretching, or bending. So that applied pressure will cause this change in electrical signal. And if we were to calibrate it, we will know exactly how much force we are actually exerting, not only on the device, but also the type of loading. So with that, we in our lab, we are actually developing many different microfluidic devices for biomedical applications, as I mentioned, from in vitro testing to in situ monitoring. So in the past, even right now, we are still developing microfluidic devices to isolate, for example, cells, disease cells from human body for diagnosis. But for this particular talk, I'll focus on 4 different technologies. I'll go through them briefly. One, it will be on a smart insole. Second is on wearable sensors for healthcare application. The third is actually a haptic glove that we developed using our microfluidic device. And then the fourth is a kind of a smart bandage or for wound monitoring. So the first problem we wanted to tackle actually is diabetes. So if you look at Singapore, Singapore actually has a very serious problem in diabetes. In fact, one of the world's top in terms of people contracting diabetes. And so if you were to look at this particular chart in Singapore itself, today, actually 1 in 3 people to be 65 years and above will actually has diabetes. And there's also 1 in 3 chance for us, in our lifetime to get diabetes. And so it's a very serious problem. In fact, a diabetic patients can actually suffer a lot of long-term complications, things like blindness, kidney failure, heart attack, stroke, and also amputation. So amputation is something we wanted to tackle because amputation results from a patient having a diabetic foot ulcer. And if they don't take care of that and they repeatedly start it, then they will lead into amputation. So this is what happens if an elderly person has a diabetic ulcer like this. And also because they suffer from nerve damage when they walk and they step on their wound, they don't feel any pain at all. So repeated stepping can cause infection and then thereafter amputation. So if a patient has amputation, their mortality rate is 50%. That means 50% of people who have amputation will die within 2 years. So this is a serious problem. So what we try to do is to incorporate our sensors into this insole, what we call a smart insole, so that we can track the pressure that's exerting ulcer. So when the patient walk, they will know that whether the pressure is too high. If it's too high, we can alert the patient that the pressure is too high. They need to sit down and rest because that is one way to mitigate, having the ulcer getting worse. So this is actually my students wearing the smart insole. And then, so we can actually track the pressure that's exerting on the bottom of the foot. So by looking at the pressure that's exerted, we know whether the person is standing, walking, or sitting. And we can track also different parts of the foot as well. So the idea is to track if there's high pressure acting on the ulcer, we can alert the patient. So actually during that time, we started a company called FractioSense to commercialize this because we thought that there's a lot of interest in this particular technology. Firstly, with such a technology, we not only can enable accurate measurement of the in-shoe pressure for the doctors to better advise the patients. The second is that patients can actually wear this back. They may not feel the pain when they step on the ulcer, but at least they can see the pain. And then the smart device will then have clear instructions given to them as to what to do. Of course, the data collected is all uploaded to the cloud. And then we can do a data analytics. And at the end of the week, we can use AI to generate a report and then send to the doctor to inform the doctor whether this particular patient has been taking care of the ulcer or not. So this is a movie to show you, this is a patient wearing the smart insole and then walking. And then this is the app that can track the pressure. So if the pressure is too high, we can have an instruction that says there's high pressure on the left forefoot. And then we'll say, first take a seat, rest for a while, offload the pressure, and then before they start walking again. So this is one way to help mitigate having too high a pressure exerting on the ulcer. So actually recently we also been now using this in the workplace because in Singapore, especially last year, there's a high incidence of workplace accidents, and slip, trip, and fall is the resulting is the cause of the accident. So what we did is now we use a smart insole to put into the worker's shoe, and then coupled with GPS, the workers can then wear the shoe and go about. So for example, in the shipyard, the workers can go about doing their job, but we can also detect where the areas where there's high slip, trip, and fall. So if there are areas where there are high slip, trip, and fall, then we can know which area for the employer to mitigate. So even for example, someone walking up a ladder and slipping, we can also detect that there's a slippage there. So from here, we can actually report also the incidence of slip, trip, and fall in the workplace. So for example, if there are areas where there are high risk of slip, trip, and fall, the employers can go and try to mitigate that. So yeah, we've been also fortunate with quite a number of awards for this particular technology, but now we're also extending it to other applications, for example, for elderly persons to track whether they are more susceptible for fall or not. So the next area I want to go into is sensors for physiological testing. I think about maybe in 2017, I was trying to see if we can create a microtube like this. And during a time, we were probably one of the first group in the world to create a very small microtube that is less than 10 microns. And my idea was to create a microtube like this to be able to have the researchers form microfluidic devices very quickly without the need to do soft lithography. However, when we started to fill it with a liquid metal, we realized that it actually became a sensor as well. So you can see this microtubular sensor is so small that we can pass it through an eye of a needle. And in fact, when we weave it into a fabric like this, and when we stretch it, we can also measure the stretching force. So this is actually, we thought it's a fantastic sensor that we can use to create things like smart textile. So with this, we actually created quite a number of different applications. I won't go to all of them, but let me show you the first one. So with just a single microtube sensor like this mounted on the knee, we can actually be able to track, for example, someone that's doing rehabilitation and doing bending of the knee. So if you look at this, we can actually track not only how much the knee is bent, but also how fast and how many times the patient is doing. Although it's wired, we can actually make this wireless as well. So this is a small sensor that can be easily attached to your knee or your elbow, not only for rehab, but also for sports. The other interesting thing is also, a lot of people are also trying to develop devices to measure pulse. So we also use that to see if we can track pulse measurement as well. So using this microtubular sensors, we were able to actually track quite accurately the pulse shape as well, as shown here. In fact, now we are also looking at, looking at measuring the pulse from the wrist. The other area is actually quite interesting, where we actually weave just a single microtubular sensor onto the tip of a thing on the glove itself. So, for example, by pressing it on the inner elbow, we can measure the bronchial pulse monitoring. So some doctors actually wanted to do this, with a finger, whichever part of the body you press, you want to see if there's a pulse and what is the pulse shape like. So this is one area. Of course, we also extended to the wrist as well, where we also be able to measure the pulse shape. The third one is actually putting it near the neck, where we measure carotid pulse monitoring as well. So from here, we can also measure the pulse. And the last one is actually measuring the pulse near the foot itself. So for diabetic patients in particular, we wanted to see whether there's blood transfused to the foot. So we use our microtubular sensors to measure whether there's blood flow to the foot. So the last application is actually this particular smart sensor that we developed into a commercial product, which can be used by the gymmers. So gymmers can actually wear this on their, for example, we can use this to measure whether we are, when you're doing curls, how much, the amount of number of reps you are doing, and so on and so forth. So that particular device actually is has been tried out by the gyms both here and in Indonesia as well. I think today we have actually analyzed more than 1 million reps that's being performed. There's also an app that can be downloaded from the iOS or Google Play Store. So I'm not sure whether you've seen this movie by Tom Cruise called Minority Report, where Tom Cruise wears a glove to call out information. So this is something actually that we also developed. We call it the Infinity Glove. So this Infinity Glove is what we did was we weave our fiber sensors into the glove itself. So with that, actually, we can use it to play games. So we can do gaming and also for rehab as well, especially for patients when they need to exercise their fingers and hands. So this is how it looks like. By just bending your finger, we can actually elicit electrical signal. So it can be used for gaming and tele-rehabilitation, but we can also use it to do control, or functions in the computer, for example. So actually, we also put this to use for VR trading and even human-machine interaction as well. We can use this to control robots, at a distance. So we have also been, appearing in the news and so on. There were a lot of interest in this particular glove. But I want to go to the next one, which is actually quite interesting, which is more in the metaverse. So recently we developed this, what we call a hap glove. It's a haptic glove and it's a wireless pneumatic glove for enabling haptic feedback in the metaverse. And what happens is this, currently if you are, in the virtual reality, right, if you, there are two particular or three particular sensors that you need. So one is that when we wear our VR goggles or headset, it gives us the visual and the audio, information. But the third is actually the haptic sensation. Right now, most of the commercial controller is actually in the form of this joystick that's seen here. You move it to an object and then you click it, but you are not able to feel the object, whether it's soft or hard and so on. So in order to have this sense of touch, you need two types of sensation. So for us, when we hold an object, we need firstly what we call cutaneous sensation. And cutaneous sensation arises from the mechanoreceptors that is in our skin. So we can feel texture, we can feel vibration, and so on. But the second one is what we call the kinesthetic sensation. So kinesthetic sensation will enable is arising from the mechanoreceptors in the muscles, tendons, or joints. So in our finger, when we bend our finger, we actually activate our mechanoreceptors and we know we are bending our finger. And whereas for the cutaneous sensation arises from the skin. When we touch an object, we can feel it. So these are the two sensations that is needed for us to have a realistic sense of touch in the virtual reality world. So currently, there are two very famous gloves that is, in the market. One is called HapX. So HapX, if you look at this particular technology, this is a glove itself, which is actually very bulky. And you look at this particular user here, she's actually wearing a backpack. And the backpack actually has the pump that drives the pneumatics that's on the glove. The second is actually Meta glove. So this is Mark Zuckerberg that's sitting on the chair in front of a table. And again, it's very bulky and it's tethered to a gas tank that's beside it. So on the whole, the current market is actually quite bulky and not so portable. The other thing is also HapX is very expensive. It's I think about more than $100,000 to buy it. So we came out with a hap glove that's wireless, that is actually quite portable. It's only 280 grams. And we made use of two things to enable the two sensations that I mentioned. One is we have a pneumatic clutch shown here in A. This is actually enabling the kinesthetic sensation. Whereas the B is we have a pneumatic indenter using microfluidics to enable the cutaneous sensation. So these are the two different components in this device. And the weight is about 280 grams. And so this is the final product, how it looks like. It's actually very portable, and we don't need, it's not tethered to any gas tank at all. We can use it to touch object and then be able to pick it up, for example, and put it over a pole like this. Or we can piece together also things like puzzles. And this is actually how it looks like. It's actually very light and portable and easy to use. Of course, now our application is in the healthcare. And so we are trying to use this to see if we can train doctors. So with this particular technology, not only can we feel the pressing of a button, and we can also be able to feel an object, whether it's soft or hard. We can actually be able to input realistic stiffness in the object and enable the user to feel it in the VR environment. We can also, as shown just now, be able to piece puzzles together. We can even feel heart rate, even raindrops as well. You don't feel the wetness, but you literally can feel the raindrops hitting on your fingers. And also, for example, you press a balloon, you can feel the balloon bursting as well. And then, my student created this archery game. We can use this to play archery, shooting games, and it's actually quite realistic. You can feel the tension of the string and the release. In fact, we can also use this to interact with someone. So if I'm here and you are in China, I can now play a game of chess with you, and then we can even high-five, and I can feel your hand. We can even shake hands as well. So these are some very interesting applications we are developing. Of course, our aim is eventually to go into the health metaverse. In fact, such a technology can be applied to many different applications, but let me just show you two. One is working with the National University Hospital. We are actually using this to train trainee doctors how to do palpation. So palpation basically uses your hand to feel your body. For example, your abdomen, to see whether there's tumor or whether your liver is stiffening. And so first we get the experienced doctor to do it first. We capture everything, how they do it. And then when the trainee doctor does it, we can then be able to give instruction to them how to do it. If they do it wrongly, we can also correct them. So this is one of the trainee doctors using the glove to press against the abdomen. So the dummy itself is a patient. It can be someone elderly, someone that is young, or even a child. And after, for example, when the person is pressing here and they felt there's something stiff, he or she can press to see whether there's a tumor there. So that the trainee doctor will know whether he or she is getting it correctly. The last one for this is actually rehab. So imagine patients can now do rehab without physically having the device at home. In fact, they can have many different games they can play. So with this glove, they can do exercise like picking up objects and putting it through a pole like this. And we can track whether they are making improvements. If they started to do it more quickly and then their hands are more, there's more dexterity, we know the patient is actually improving. So this is another, a future that we're moving towards, doing rehab at home. The physical device. I'm not sure whether there's sound for this.
手持弓箭，用力拉弓。
Okay, so this is in Chinese for those who don't know Chinese. My apologies, but this was done by the 联合早报, and I think it explains what kind of summarizes what I've said just now.
手持弓箭，用力拉弓，手指头感受到弓弦的张力。我手上戴着的这副是本地研发的虚拟实境触觉手套。手套除了能用来玩游戏，还能应用在医疗领域，像是中医把脉、物理治疗等等。手套里究竟藏了什么玄机？让我带你去了解更多。这个手套原型已做到自带触觉，能让人感受到虚拟人或物体的形状、大小和软硬度，甚至是雨滴等动态反馈。
我们的手套主要有2个核心的技术第一个是一个柔性可拉伸的应变传感器，我们是用它来做快速准确的手指运动捕捉。第二个是一个小型轻量的气动触觉反馈模块，可以使用者感受到物体的软硬、心脏跳动等等。
取名 Hep Glove 的手套，今后可能运用在远程医疗，比如说病患戴着手套，或许就能自己把脉，再让中医师隔空诊脉。此外，手套也可以用来培训医学生和见习医生。
Okay, so this is kind of summarizes what we do. So I must actually, I give credit to my student Jiaming, who is the one who actually developed not only the glove but also the whole VR, games and so on. So he actually won the IES Prestigious Engineering Achievement Award, which is actually very deserving. And also because it's together with Tsinghua, actually Tsinghua's president came to visit us early this year, and then we also let him try out our glove as well. So that's President Wang, Professor Wang, together with delegates, he came to visit our Institute for Health Innovation and Technology at NUS. Actually, a couple of weeks ago, also one of the Suji from Dang Wei Suji from this Guangzhou actually came to visit us as well. We also let him try our glove. So the last part I want to go quickly is actually the wound sensor. I think my time is running out, sorry. So this is actually with regard to chronic venous ulcer. So this is ulcer that happens in elderly patients. And what happens is currently the way they do it is to look at the size of the wound and the color, but then we weren't able to actually analyze what is inside the wound. If we want to do it, we have to take the wound exudate, send it to the lab, and then analyze it. So that will take time, a few days, and we cannot, if patients, if we can do it quickly on the spot, that would be great. So we developed this particular wound sensor that can be attached directly to the wound. The wound is, the sensor itself has a microfluidic device to route the wound exudate towards the sensor. And then the sensor itself can measure inflammatory factors, pH, temperature, and bacteria. So these are some of the things we can do in one single test, and within 15 minutes, we can get all this. So this is a PCB board that is attached to it. It's quite big, but now we have a smaller version. And then the data is downloaded to a iPad. And then that's where we can keep track every week how well the wound is, whether the wound is healing or not, looking at the inflammatory factors. So the way we do it is to use aptamers, where we design aptamers to tag specific inflammatory factors. But of course, temperature, pH, or this can be done using other sensors. So I just skip this, but basically what we have done is we have come up with a sensor that's not only enable point of care testing, but also multiplex. It's also disposable. In fact, there were a lot of interest in this particular wound sensor. The Wall Street Journal actually did an article on this, and Reuters News. Also, South China Morning Post YouTube, I think we have more than 500,000 views. There were actually quite a lot of interest in this, and quite a number of companies actually contacted us as well to see if we were willing to commercialize this particular technology. So with that, I just want to end by saying that wearable technology, ultimately what we're trying to do is to use it to help us collect accurate, complete, reliable, relevant, and timely data. This is actually what we need of the wearable sensors. And then with that, we can do data analytics and thereafter be able to implement AI in healthcare to enable not only early detection of diseases, but also personalized therapy and monitoring of treatment. So just want to end by saying that in all these devices we develop, we will do it if it can help us to improve clinical outcomes, reduce healthcare costs, also help to increase life expectancy and health span. If not, I think there's no point going into these different technologies. So these are the people I want to acknowledge, my students and postdocs who have spoken on it, and also the funding agencies. And finally, actually, last Friday, we had this workshop actually in NUS, and then today we had this flexible electronics workshop. So I think there's a lot going on in this area. I think we should continue to push ahead this particular area and see how we can all collaborate and work together. So with that, thank you so much for your attention.
Thanks a lot for the fascinating talk, very informative. Due to the time limit, I think we can just accommodate 2 quick questions. Okay, this one.
Hi, Professor Ling. Thank you for your wonderful talk and very inspiring content and the products especially. I'm very curious about the foot posture recognition of sensors. I wondering, you fabricate 6 sensors on the foot pad. I wonder, is it enough for our foot posture recognition or diagnosis?
Right, yeah. So that's a good question. Actually, not necessarily 6. We can even have 24 or maybe even 3, because it can customize according to the patients, depending on where, for example, the ulcer or the heel ulcer is.
But how many is enough for them?
How many? Actually, it depends on size of ulcer. I think even 1 to 3 is good enough to just focus on the area of the ulcer. But if you measure the whole foot, actually 12 is also more than sufficient. it depends on the resolution and how much,
Yes.
yeah, the kind of, the kind of exercise or activity you want to engage in.
Oh, yes,
Yeah,
cool.
yeah.
So then come to the second question. So you fabricate more than 20 sensors by micro fluids
Yeah.
and by liquid metal.
Yeah.
And then you need to get sensors from the small pairs of the different sensors. But the most tricky problem is how to you deal with the interface. When you get the sense, get the signals from the sensor, you need a copper well or something.
Yeah.
But the interface is a very tricky thing.
Correct.
But
So
how
I
do
have
you
another postdoc that's looking into circuitry design, to be able to link up all the sensors and to be able to collect the data from each sensor. I think you're mentioning about
but liquid will leak.
Oh, yeah. So actually now we are also moving to other types of sensor because liquid sensors sometimes can be, depending on the amount of force exerted,
Yes.
can be too much. So we are also looking at actually the latest design, we use other types of sensors.
Yes.
Yes.
Thank you. Thank you.
Oh, yes.
Very impressive. Still about the wind.
Wind, yeah.
Because the wind is very complex mixtures.
Yes.
So is there any consistent or the wind falling issues during the real applications?
Biofouling.
Biofouling.
Oh, biofouling, no, because basically our sensor is placed onto the wound for 15 minutes and then we take it out. So it's not real-time monitoring and now for over a few hours, a few days. Although that's something we are looking into.
And the amount of the wind extrude may be varied. Depends on
correct,
the stimuli or the environmental factors.
Yeah.
So how to make it constant or diagnostic valuable for these variables?
Yeah. So actually we went to the hospital and looked at it. The wound size can vary from very small to very big. And then the wound itself can also have different contours. So we talked to the clinicians and said if the wound is very big, then we might have to sample from a few locations.
But it will make the calibration very challenging for the real diagnosis.
For calibration.
Calibration
of
the biomarker, concentration of the biomarker.
Okay. Of course, we did a lot of calibration in the using in the lab itself. Then, of course, when the wound itself, we can actually take the wound isolate out and do ELISA tests, and then compare to what we have obtained using our wound sensor. That's how we do the calibration. Yeah.
Okay. Yeah. Thank you.
Okay, due to the time limit, I think we need to stop here. If you have any more questions, please talk to Professor Lim during the coffee break. So let's thank Professor Lim again. Okay. The next session will be chaired by Professor Peng Chen from Nanyang Technological University.
Thank you. So I am a professor in School of Chemistry and Chemical Engineering and Biotechnology in this campus. It's my pleasure to introduce the next two speakers. Our next speaker is Professor Xue Feng. He received a PhD degree from Tsinghua University in 2003. Subsequently, he did postdoc training at UIUC and Caltech. In 2007, he joined Tsinghua University, and now he's a tenured full professor in the School of Aerospace Engineering. He's a founding director of the Laboratory of Flexible Electronics Technology at Tsinghua, and also the director of the Institute of Flexible Electronics Technology of Tsinghua University. So he served in the editorial board for a number of international journals, and he has received numerous awards, including ASME Marvel medals in 2023, and Liang Holi Foundation Science and Technology Innovation Award in 2022. and the gold medal at the Geneva inventions in 2022, etc. Professor Feng, now the stage is yours.
Thank you very much. Hello, everyone. I'm Feng Xue from Tsinghua University. So today I give a talk on flexible ultrasound devices for biomedical applications. The talk will give following this outline. So for the flexible bioelectronics, so flexible electronics, everyone know, we try to make the sensor, the chip, and the circuits flexible. So for the bioelectronics, we combine the flexible electronics with the biomedical engineering. So we want to try to develop biomedical devices for the applications. So for the flexible bioelectronics, so can reflect the combination with the body network. For example, for the implantable devices, we can integrate the flexible bioelectronic device with the heart, with the organ inside. And we can also develop some wearable device for example, use the wearable device, we can measure the ECG, blood pressure, glucose, and many parameters. So use this method, we can make the human digital. So then combine and connect the human bodies. So we will construct the network. For example, for the body internet. So from this way, so we can change the medicine, the medical diagnosis. Now we are developing many devices and methods for the flexible electron device. For example, for the physical signals, we can develop the device to measure the body temperature, strain, pressure. We also develop some biomedical chemical devices for blood sugar, sweet components, and develop some devices for ECG, EEG, and blood oxygen, blood pressure. Now, for example, for the human body, we use optics and microwaves to detect and transmission the signals. So, however, the body tissue can absorb and the light and the optics and the microwave. So, if we want to detect some information inside or deep inside the body, so it's not easy. So that means we use the optics and the microwaves can only detect the very, very shallow inside the body. So this is the limit. So for the ultrasound is very safe, is very friendly to human body. We use ultrasound for human body detection for more than 100 years. It's very, very safe. So from our side, we want to use flexible electronic technology to make the ultrasound devices softer and flexible. So if we can, so our target, so this is the traditional ultrasound probe. So our target is to make this probe flexible and stretchable. And we can attach the flexible probes to the body. So actually, the idea on the flexible ultrasound electronics, a few scientists tried to this way. So for example, Professor Xu Shen from UCSD, his group developed some flexible ultrasound device for the blood pressure monitoring and for the blood flow monitoring. My group focused on integrating the flexible circuits with the flexible ultrasound device. And then we use this for the for the diagnosis and the treatment. Now I introduce my group work on the flexible Doppler device for blood velocity monitoring. So for the blood velocity, it's very important for the cardiovascular parameters, especially for the thrombosis and the restenosis. For example, if some defects or the tumor on the in the vessel, so the blood, the flow of the blood will change, the turbulence will occur. So this will cause some very serious, such as the stroke. So if we can monitor the blood velocity, so then we can prevent the stroke. So now for the current clinical method, we have to use the rigid probe, the rigid ultrasound probe to measure the blood velocity. Usually we use the Doppler shift effect to measure the velocity. For the Doppler effect, we can see these equations. So this is the velocity of the blood. This is the velocity of the sound. So this is the incident angle. Sorry. This is the frequency of the sound. So this is the frequency shift. So if we want to measure this, so that means we have to measure the incident angle. And so for these two parameters, we have know these two parameters. And then we use the circuits to can measure the Doppler shift frequency. So then we can, from this equation, we can get the blood velocity. Now, so we some scientists also developed some other method to measure, to monitoring the vascular velocity. For example, by the thermal analysis or by the implanting the pressure sensor. All this method is cannot directly measure the velocity of blood velocity. So the ultrasound use the ultrasound of the Doppler effect, we can measure the velocity, the absolutely velocity of the blood. So we have to design the device and the device array to measure the blood velocity. For example, we can make the rigid probe into a different unit. So then we integrated the different unit with a soft substrate, and then the whole device is flexible and stretchable. So then we can attach this device to the body, and then this is the ultrasound source. So the source will give a ultrasound, the ultrasound, and then we reflect it. So then the detector can get the reflective sound. So then we can measure the signals. So we can also design the device by the arrays. For example, for the different units, we have to put the different unit with the different angle. So we use this angle to tune the Doppler effect, and then we can get the parameters are very accurate. So from this, we can also give some other advantages. For example, for this device, we don't need the hydro for the ultrasound. That means we can directly attach this device to the skin, and it's very soft. So we choose the piezoelectric material we use the one three-pure electric composites as the source. So that's we choose this composite because this material, this composite material has a low acoustic impedance, so this can suppress the shear vibration. So, and then we use these equations. We can select the 5 megahertz as the optimum frequency, because for this frequency can easily to transmit into the tissue, and then we can get the depth of the this can be decided by the depth of the carotid artery. So because this is is very deep in the body, it's about 25 millimeters. So use this, we can also decide the transducer inclination angle design, because this angle theta we have to measure this theta, so then we can get the parameters of the Doppler effect. So for the traditional clinical probe, the angle of the Doppler application is around 30 to 45 degrees. So the interface refraction, so theta is too large, so the interface refraction loss and the attenuation are large. So then we have to design optimal angles. So the theta is too small, the frequency shift is very small and difficult to detect. That's why we make the single is just like this, 17 degree, 20 degree, and 23 degree. So for the rigid problem, it's not easy to get the angle just like this. So we use the double beam method to get the Doppler effect. So this method can overcome the influence of the Doppler angle on the velocity measurements, and then we can use this to measure the velocity. So we use the two beam, beam 1 and beam 2 of the ultrasound. So then
device, so we can to measure the flow, the velocity. So this is a non-stenosis. We can find that it's almost stable. So the peak velocity is about 17 centimeter per second. So now it's for the tube with the pillars. It's for the stenosis. So we can find the turbulence. So use this, we can confirm the device. Now, finally, we compared our flexible Doppler device with the commercial proper device. So we attached this device to the neck, and we at the same time we use the rigid commercial probe to attack the velocity at the same place. So we compared the results. For example, this is a carotid artery on the neck. So this is the flow velocity by the commercial probe. This is the flow velocity by our device. So from this, we can find the velocity is almost the same. So that means, so for our device, we can get the standard of the medical. So this for the radial artery is almost the same. So this results are from the commercial rigid probe. So this is for our device. We can compare these results. So it's almost the same. So finally, we conduct a very interesting experiment for the blood pressure measurement. So we usually use the cuff to measure the cuff method to measure the blood pressure. That means we apply the pressure. So then the artery is closed. So when the pressure is released, so the artery is open. So then we can get the blood pressure. So now we attached our flexible Doppler device here, and then put the cuff on it. So then apply the pressure. So then we can measure the blood velocity. So when the artery is closed, we use this method can measure. So velocity is near 0. So then the pressure is released. So then we can get the normal blood velocity. So this should be the first time to measure use the Doppler effect to measure the velocity during the blood pressure measurement. Okay, so I introduce another work on the flexible ultrasonic cardiac pacemaker. So for pacemaker is very important for the heart failure. Now for the current implantable pacemaker, we have to use the battery to supply the energy, and we cannot measure the parameters of the heart and transmit the signal outside the body, because for the microwave, the body is very easy to absorb it by the body. So for my object, so we want to develop a pacemaker without battery. So we can use the ultrasound to provide the energy, and then we use the ultrasound to transmit the signal of the heart outside to the body. So then the pacemaker, everything is wireless energy or wireless communication. So we designed the device. So we have to integrate this device with the heart. The heart motion is very complicated. So during the heart motion, so the muscle is stretched and torsion. So this requires our device stretchable and flexible. So we designed this device. This is for the ultrasound source device. this is the stretchable circuits. So we use this design to fabricate our device. So for the device, we still conducted the fatigue experiment. So for the bending, we also conducted the bending test. We conduct 500 times repeating bending, and then we compare before and after bending results. So we can find for the system can still perform very well after the repeating bending. So we can also conduct the stretchable test. So for this device, the strain can be we can stretch it into the deformation can reach to 20%. So this is suitable for the heart motion. Now we are for the we also to conduct the experiment and analysis for the bending and the torsion. So during the bending and the twist for the torsion, so we can measure the signal from these circuits. We can find for the bending and the twist of the torsion. So the system can still stably convert the signal to the signal. And all the system, the circuits can receive some energy and convert it into the electrical energy in a deformed state. That means in the flattened status or in the deformed status, the device worked well. So because for this device, there's no battery. That means we use the ultrasound to provide the energy, and the circuits will convert the ultrasound energy into electric energy and then provide it to drive the circuits. So we conduct the energy transmission efficient contact. So the efficiency is up to 23%. So this efficiency actually is very high. Now we conducted the experiment. My student by a poke. It's a special poke because we needed the fat and the muscle. So so this is the transmitter. This is the device. So the student conducted the experiment. So through the fat and the muscle, so the receiver can get the ultrasound, and then we make the different depths. Because for the pacemaker, inside the heart chamber, so the depth is around 5 or 6 centimeters. So that means the ultrasound have to transmit to the body, and the receiver can get these signals. So that's why we conduct the depth from 5 millimeter to 15 millimeter. So from this, we can get the for the media. We also conduct the different component from the fat and the mix the fat and the muscle. So we can find finally we can find that the transmission depth can reach 15 millimeters. So it's enough to suit for the heart pacemaker. Now we also conduct for the communication, for the signal transmission. So ultra fast charging response speed is almost 5 milliseconds. and that means this charge can enable the quick activation and stop our device. We are integrating the temperature sensor with the system. So then we embed this system under the port. So this is the transmitter, this is the receiver. So use this sensor to measure the temperature. So we use the ultrasound to provide the energy to drive these circuits. And then the circuits can measure the temperature and then use the ultrasound to carry the temperature outside to the receiver. So that then finally we can realize the wireless energy and the wireless communication. So this is some analysis for the circuits, especially for the signal to noise ratio. So this is very important for the circuits. So this is the animal test. So finally, we use PVTF as a deformed sensor, as a strain sensor. So use this sensor to detect the heart motion. And this is a device, the ultrasound, the flexible ultrasound device. So finally, we are integrating all the system with the heart. Now, so use this method, we conduct all the procedure of the heart failure. So this is a normal heartbeat, so it's rhythm. Now we apply the high frequency electrical stimulation. So then the heart is stopped beating. So then now our sensor can detect the heart stop beating. So now, so this signal will trigger the outside ultrasound will provide for the energy, and then the energy converted to the electrical energy. This energy will start the heart again. So for this animal experiment, we demonstrate all the procedure of the pacemaker. Finally, I introduce our flexible ultrasonic patch for the wound healing. So especially for the chronic wound. So about 5% of the world's population suffer from the chronic wounds, especially with the diabetes and the elderly, obese, and alcohol drinkers. So the repeated wound inflammation, the finger pricking to measure the glucose, insulin injection, very easy to cause the formation of the chronic wounds. So we want to use the ultrasound to treat the chronic wound. So the principle is very simple. This is from the biomedical principle. So the ultrasound will trigger the kilogram ions combined with the CMK2. So this will this will activation the TM1. So this TM1 will promote RAC1 GTP to GDP. So this GDP is will treat the healing, treat the wound. So for the traditional ultrasound device, so it's rigid. It cannot conform to the wound. So that's why we cannot use the traditional probe to treat this wound. So for our method, so we make the ultrasound device into a 3x3 array. So this we also use the transfer printing to fabricate the flexible array. So for this device, we can attach it to the wound totally conformally. So now this is our device. So we can find that this device can totally conformal to the skin. So this is the whole patch. So with the 3x3 array of the ultrasound source. Now, for the ultrasound patch, we have to conduct the fatigue and the mechanical experiments before and after the bending test. We can find the circuits, the ultrasound source, and the whole system is very stable. So especially I want to mention that for the flexible ultrasound array, it can control. So it can control the focus of the array, the ultrasound array. That means, for example, there are for our system there are 3x3 arrays. So, for example, if the array deformed, so that means the focus of every one unit can be inverted in one point. So that means for the specified point, we can concentrate our energy here. So from the energy, because of the energy concentration, that means we can use a higher efficiency of the treatment. So now we are conduct the IHC test to verify the principle of the ultrasound. For this, we conduct this method especially to demonstrate how to activating the RAC1 protein to control the wound. So this is a treatment experiment. We make an animal model with diabetes. This is a wound of the diabetes rats. So then we attached our device onto the wound, and then we conduct a 1 week treatment. So for the treatment for the 1 week, we conduct a continuous treatment. So we find no significant change in weight. So the glucose fluctuate around 22 or 26. Now this is the results. So this is the results by the for the rats with the ultrasonic patch. So finally, we can find it from day 3 or day 4. We can find that the wound is already for good condition. So we can find anyway. So the wounds in the experimental group, this is the experimental group. So we can find it's faster than those in control group. So from the picture, we can find the results. And we also satisfy the time. So we can find that the wound healing time is shortened by about 14%. So from this experiment, we demonstrate we are use the ultrasonic to treat the wound. So this is data for medical analysis. So finally, give a concluding remarks. I'm not a flower. So flexible bioelectronics have the advantage of the lightweight, flexible, wearable, implantable, could not only promote the integration of medical information with the human beings, object and environment, but also has become the information source for intelligent medicine. Ultrasound technology has a greater potential for disease diagnosis and treatment. So the combination of the flexible electronic and the ultrasound technology has further expanded the wide application of the flexible electronics in biomedical fields, such as real-time monitoring of the blood pressure, blood volume, stroke prevention, cardiac pacing, and disease treatment. So this is my talk. Thank you very much.
Thank Professor Feng for the very interesting talk. Due to the time limit, we have some delay. So 2 questions from the audience. Professor Gao, please. Yes.
Very interesting talk. My question is about the mechanism of ultrasonic healing, wound healing. You mentioned there's a mode of mechanism, right? Could you elaborate a little bit? How does the ultrasound? What is the mechanics behind it?
Oh,
you have I think you have a chart. It's ultrasound promotes some chemical reaction.
Is this one?
Yeah, this one.
Yes.
Yeah. Could you elaborate a little bit? I didn't quite follow the details.
So actually, the principle is for the bio. The principle actually is very easy, but maybe I cannot explain it very clearly. So for this one, calcium ions will activation the protein, this kind of protein. So this kind of protein will trigger this protein.
Yeah.
So finally, this protein will change this.
Yeah.
I just know the principle of this. So
yes, the chart is very clear. But how does ultrasound was able to? Was it because it's through energy, through activation of some?
Because the ultrasound will can trigger this one. So this is just like
trigger chemical reaction between calcium iron.
Oh no. So ultrasound will trigger this one. So this one just like a link. You have to trigger the first point. The first point will trigger the next. So the ultrasound just like trigger the first stage.
Yeah, for example, light activation, right? Light will promote electron to another level, right? If we have a light, shining light, the light energy will be absorbed by electron and push electron to upper level. But here, the ultrasound is absorbed by calcium. When you say activate, what does it mean by activation?
Professor
I don't know how to answer this question.
Maybe I can make a guess. Yeah. So my guess is that ultrasound will activate mechanosensitive channels. Some of the mechanosensitive or human tissues, like maybe perhaps in skin cells, but for muscle cell for sure. Yeah. So they're mechanosensitive sensor. When it's open, calcium will flow in. Yes. 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 For example, yeah.
Bio, because I cannot explain by bio language. Yes. Use the ultrasound. Yeah. Thank you very much.
Okay. Yes, please. You can use mine.
Professor Gong, very interesting talk. As I have a question that for blood velocity estimation, the angle is very important, the theta. But when the flexible probe is bent to conform our skin, the angle may change. So it's maybe it may decrease the accuracy. So how to solve this problem?
Good question. Good question. So that's why we use a double beam model to deal with the Doppler effect. So very good question. So actually, for the flexible ultrasound device, it's very easy to deform. So the angle is change.
Yeah.
So that's why we use the double beam method. So this double beam can compensate each other.
Okay.
So if we use only one, so that will happen just as you mentioned.
Yeah.
Yeah.
Okay. Thank you.
So because we have delays, so
Just one question.
one more.
Okay,
question.
yeah. Thanks, Professor Feng, for a very interesting talk. So when this flexible ultrasound probe attached to the skin, the impedance have a big mismatch. So somehow efficiency will be affected. So in your design, how to tackle these problems?
Yes, good question. So for our device, we don't use the hydro to for the impedance depress. So now we use a two-way to control the interface impedance. One is a method that we use the different intrinsic angles. So from our model, so that's why we have to develop the model to calculate the velocity. So the second, we choose EcoFlex as the package material because the EcoFlex is similar, just similar to the skin. So we use the two method to control the interface impedance.
Yeah. Also, I just associate a question. So, when this flexible ultrasound array, when you conform to the alien shape, and when you use it, I mean, because it's not necessary like a regular shape. So when you processing the data, which somehow need adapt to the shape of your so-called sensor attached areas. So in your later signal processing part, any so-called consideration which is related to the shape?
Yeah, good question. So now here I give the analysis for the angle control to suitable to adapt it to a different shape of the tissue. For example, in our experiment, we attached to neck. This is only for the just to demonstration the application for the stroke. Actually, we also conducted this to the foot, to the feet. Yeah. So to the different place with the artery. So now, so if the angle is changed, we use our model to calculate the velocity.
Thank you.
Okay, so I think you can interact with Professor Feng during the break later on. Let us thank him again for the very interesting talk. So our next speaker is Professor Yi-Hao Chen. So he's an associate professor from School of Aerospace Engineering and also Center for Flexible Electronics Technology in Tsinghua University. So he will give an introduction about the Lab of Flexible Electronics Technology.
Okay, thank you for the introduction. Good morning, everyone, ladies and gentlemen. I'm Yi-Hao Chen from Tsinghua University, and thank you very much for the invitation to Singapore and to the NTU. and it is my great honor here to give an introduction to the Laboratory of Flexible Electronic Technology, Tsinghua University. The development of flexible electronic technology in the Tsinghua University starts from around the early ages of the 21st century in Tsinghua University. And different researchers from different departments in Tsinghua University start their researches in different aspects. For example, from the Department of Mechanics, Professor Xue Feng and other Professor Yihui Zhang, and they research on the inorganic, stretchable, and flexible electronic technologies. And from the Department of Chemistry, for example, Professor Duan Lian, which we will give an introduction this afternoon, they start their researches on the organic light-emitting diodes with the organic materials. And then after many years of efforts and researches, we not only innovate in the frontier and breakthroughs in the flexible technology itself, but also we want to move forward to put our findings and the results and then transform them into a more practical and a larger area, and then want to the applications and the markets. So in the 2016, Tsinghua University and Zhejiang Province signed the framework agreements on promoting cooperation in the field of flexible electronic technology. And then the next year, the 2017, an Institute of Flexible Electronic Technology of Tsinghua in Zhejiang Province was founded. And the institute was focused on the R&D and manufacturing. Then after many years of efforts, we promoted our research platform to a new height. And in 2021, we were officially approved of the National Key Laboratory Program and reinforcing our position in the field. Then the next year, the last year, 2022, Tsinghua University established the Laboratory of Flexible Electronic Technology, and making us the first and the only one national key institution specialized in flexible electronic technologies, which we call the LFIT. The Tsinghua University, the laboratory is based at Tsinghua University, and we have, sorry, this the display is kind of problem. The laboratory is based at Tsinghua University, and we have the LFIT in Tsinghua, Beijing, and the iFIT THU in Zhejiang. And the laboratory is based on the results of a progressive partnership with the Institute of Flexible Electronic Technology of Tsinghua, Zhejiang, iFIT THU, and the Tsinghua LFIT and the iFIT THU, they have different positions and they have different focuses. The Tsinghua group, they focus on the frontiers and the cutting edge researches in the field of the innovations. And in Zhejiang, the iFIT THU Institute, they mainly focus on the applied engineering research and the manufacturing research. We want to cultivate an ecosystem through this kind of combination and to foster the innovation, collaboration, and sharing. And we want to form a complete chain from the researches to advanced tech and finally to the applications. And we also say it's from the lab to shelf. So there is many ways we want to learn, and especially from Professor C.T. Lim, you have done very wonderful work in the commercial sides. We have now two positions or locations, both in Beijing and in Zhejiang Jiaxin City. And in Beijing, the Tsinghua University and the local governments, the Changping district, is building a large science park holding all the national key laboratories in Tsinghua University. And you can see from the left picture, it's a very big science park, and it is surrounded with the mountains and rivers with very good sceneries. And now in the right spot is our lab. We will have a building in the science park, and the area will be 20,000 square meters. And in Zhejiang, Jiaxing City, the city government is also giving us a new space, and it is newly constructed industrial park, which we call the NTU-THU-NUS, the new park. And the area is more than 100,000 square meters. And it will contain the offices, labs, mass production lines, and all the facilities. And that will give us a very good and very large platform and the space for future development. And in our team, we have top-ranking scientists, including members of Chinese Academy of Science and Engineering. For example, the Professor Zheng Quanshui in the nanoscience and Professor Dong Jiahong in medication, and also over 60 national level talents. For example, Professor Feng Xue, Liu Bin, Duan Lian, Zhang Yihui. And also we have some top young talents, full-time researchers specialized in the field of flexible electronics who have proved themselves in this field. For example, Professor Wang Heling and Ma Yinji. And also besides that, we also hire many senior engineering specialized, especially top engineers from well-known and national enterprises, very big companies, who will bring us the expertise in the industry and to help us make the things forward and into the applications. Our lab focuses on the most advantaged researches in the flexible electronic technology, and we do from the fundamental to the application. We have five areas, five main areas. For the fundamental technology, we research on the fundamental research and manufacturing type of flexible electronic devices. And for the core and critical elements or the components of the flexible electronics, we research on the organic devices such as high performance organic flexible electronics and inorganic ones such as flexible microsystems and heterogeneous fusion technologies. And for the application field area aspects, we have two systematic application platforms. So one is to combine the electronic devices with human being, which is the wearable technology and human-computer hybrid intelligence. And the other one is to combine the devices with non-human things, for example, the machines, the equipments, the flexible electronics, and equipment integration technology. And for the facilities and equipments, our lab, our platform have many very high level research labs and standard testing labs. And also, what's more, we have many production lines, which will help the researchers or help the students to make their devices or make their researches more into the industrial level and to make a large production and a large trial in the production lines. In the production line, we have many abilities. For example, the wafer thinning ability, we can make the whole wafer level thinning as large as 12 inches. And also to make many flexible chips, for example, the flexible flash, DRAM, FPGA, MCU, CPU, and GPU, and so on. And also we have the ability of device integration, for example, the SIP integration, or our newly researched CIP integration, systematic packaging, and microsystem integration. And also we have high precision SMT production line, and also the thin film production, which we can make flexible devices on the very industrial level device equipment and the labs. There are some research highlights that I want to show to you briefly about what we have done in the several years, in the near years. So first one is the wafer thinning technology. You can see that from the pictures. The wafer, as you know, that is based on silicon and is very brittle and very thick kind of a round plate, but it cannot be bent or cannot be flexible. But we use our wafer thinning technology, especially based on the mechanical grading of the backside of the wafer, and to reduce its thickness to a very small scale. We can make that to the minimum thickness of 15 microns. And in mechanical, we can know that when the thickness of one thing is to a very limited stage, it can be flexible. Everything can be flexible. So we have now the ability to wafer level mechanical grading of the silicon wafer and to a very minimal stage. And we can see from the picture that there are some steps, not only the mechanical grading, but also the pitting. As Professor Hua Jiangao told us this morning, the pitting will cause the strains and will cause the morphing. We also encounter the morphing or the bending or backhole of the wafer. But what we have done is to avoid morphing after those grading or those pitting of a large scale. When we make the wafer or the chips to a very small thickness or very flexible stage, we can realize the electrical characteristic of very low power consumption and low input impedances, and meanwhile reduce the thermal accumulation, which will greatly increase the functions and the lives of the chips. It is not only flexible, but also it can do better for their performances and to their usages. Here are some photos of the ultra-thin wafer and flexible chips. You can see the flexible chip is just like a film. It's just a film compared with the rigid wafer. And from 6-inch, 8-inch to 12-inch, we can completely make them very thin, and also it will not decrease in their electrical performance. And for every different kind of chips, we have built a data sheet or a database for different kind of chips to get their best or the most suitable mechanical grading process and to make them all well after the thinning process. Another type of flexible chip or flexible device we make is the ultra-thin flexible silicon pressure sensor. The right pictures is the conventional pressure sensor based on MEMS technology. You can see it is very bulky and very thick, this kind of sensor. And so this kind of property restricted it from many kind of applications. It's that especially for some soft, curved, or narrow gap pressure monitoring applications. So based on the thinning process, we use the silicon-based flexible pressure sensor and to meet the need and to support this kind of applications. After the thinning, the pressure sensor is just like a film and it can bend and it's very flexible, but their property of sensing or monitoring mirroring is not changed. And sometimes we can adjust the properties of different kind of application or occasions. And what we use is for major equipment structural health monitoring. We attach these kind of sensors to the machines or to the wheels, to the axis. And just like human, the machines also need health monitoring. We can use this kind of flexible and curved and very thin pressure sensors to make the monitoring of the working status or working parameters of the equipment and the machines. Another one is about the integration technology of the chips. Maybe you know that's the SIP system in packaging. This kind of integration method, just like this picture, which means that we can use some chips, many chips, to form a larger chip, and that will sometimes will increase the integration level of the chips or chip modules. But for the CIP packaging, what we call chip employer, chipping polymer. We take one step forward, that we use the very thin, ultra thin and flexible chips to bury them in the multi-layers of the flexible PCB, and to make them not only on the PCB, but also inside the PCB. You can see that in the CIP packaging, you can make the chips inside in the 3D dimension in the PCB, and that will significantly minimize the size of the modules, and it will carrying exactly the same capability, but with up to 60 to 70% of the original size deduction. There is an example of the CIP packaging. We made an earphone, a Bluetooth earphone, with the CIP modules or with CIP integration. We can see it will increasingly deduct the size of the earphone, and you can make more functions and more batteries in the earphone with the smaller circuits. Another example is a kind of chip we call DC-DC power chip, and the left picture is a commercial product of the DC-DC chip, and the right is what we make by the CIP process. By this kind of process, we can achieve half in size, but twice or 2 times in function. We can have a smaller size, but we can have more channels or more powers in this kind of chip, and it will increasingly increase the chip's function, and especially compared to the traditional DC-DC module. For the researches, in summary, our research team have published more than 1,000 papers in the field of flexible electronic technology, with over 50 featured in Science, Nature, and their sister journals, and many of them are the cover articles. We have also organized a series of special issues and journals on this field in top-tier publications, and we also have many patents. There are more than 500 patents have been granted both domestically and internationally. We also annually organize the International Conference on Flexible Electronics, ICFE, and it is currently is the biggest conference, especially on the flexible electronics in the world. And in 2019, it attracted more than 600 participants on site to attend the conference. And over the 2 years, because of the COVID-19, there are around 200,000 audiences virtually participate in the meeting over the last 2 years, and more than 60 speakers were invited to share. And this year we will also have this meeting in December in Hangzhou, Zhejiang Province, and we invite you all to come and to give and to participate. For the collaboration that we want to extend our collaboration with. With the NTU-NUS and the world, especially on research areas of the flexible electronics, because it is a deep multidisciplinary research, especially for electronics, mechanics, chemistry, and physics, or also the biomechanical engineering. And now we are also currently seeking top young talents, outstanding industrial talents, and postdoctoral candidates. There are many opening positions to apply, and there is the contact information of our lab and the social media links. If you are interested or have any questions, please don't hesitate to contact us. And tomorrow morning, there will be another special session in the tutorial room, and we will give a more comprehensive and discussion of the lab, and there will be teachers from the lab to discuss and to talk with you about the information. And I hope that you are more than welcome to attend. And that's all for the introduction. Thank you very much.
Thank you. The institute is indeed very impressive. So any questions for those who, yeah, you want to find a position there? Okay, maybe just
very quick question. Very interesting. You talk about transfer the integrated circuit from the traditional wafer to the soft substrate. Did you, I mean, in Tsinghua, any kind of efforts that talk to the commercial foundry like the TSMC, CMIC, and consider, I mean, for massive production, how to build up the so-called standard process, which is compatible to the flexible electronics?
Okay, thank you for your question. That in short, that we have talked with many commercialized industries or companies or factories about the transfer of the thinning process, and they are very interested in applying that into the industrial application. And the second, that it needs time that to make this kind of application in real applications, and we all want to do the collaboration with the industry. Thank you.
All right, so this ends the first half of the morning session. Let us thank all the speakers again. Thank you so much. And now we can move to a coffee break and group photo taking. Thank you so much.
One, two, three. 1, 2, 3. Okay, great. Thank you, everybody.
Okay, so we're still in the morning. So good morning, everyone. Welcome back. So now we get Professor Li Puisi, and she will talk about deformable electronics for soft robotics. Let's welcome.
Thanks, our guest chair. Right. Hello, everyone. It's pleased to be here to share some of my research progress related to deformable electronics for soft robotics. It is kind of a new topic to us, and I'm happy to share some of our attempts and also approaches in this direction. It's okay, self-service. No worries, yeah. Okay, so as we know, human and machine, there's a big gap in the mechanical property, and rigid electronics are typically non-responsive, and they do not respond to stimuli. So we look at how do we create receptive and responsive devices that are soft and compliable. Particularly, we started in this area with deformable conductors that you can refer to some of our earlier work. And recently, we have tried to integrate artificial muscles, such as soft actuators, onto sensing electronics and responding electronics in order to cater for interactive soft robotics. Okay, and one of the important components is actually soft transducers. They are basically components that convert a form of input stimuli to output responding device through energy harvesting, sensing, and actuation. And during the design of such components, it's important to take care of the mechanical discrepancy properties, the very intimate interface between the rigid and compliant substrates. And we usually take care of the design-oriented principles and hopefully to achieve a versatile form factor, particularly to realize an imperceptibility in the output performance. So there are different types of soft actuators, including the use of electrical, which can be also classified into whether do we trigger the dielectric property or the electrochemical property or electrothermal property. So all these are induced by electrical control. And magnetic is also a popular stimuli, and also a photo or light-induced actuation. And not to mention the typical pressure, which is pneumatic, hydraulic, acoustic base. And we have a thermal that can be induced by just heat from the environment or light and electrically induced. And of course, chemically, when there is a reaction, it produces a gas bubble or liquid, which also produce a form of actuation to the soft body. So there are many emerging applications, and we do see end users coming to us in the aspects and domains of healthcare, advanced manufacturing, pick and place in food and beverages, as well as logistics applications. And not to mention future tactile display, and also in the metaverse, there is this bionic robotics that would be of interest. So this is an overview of our research program. Basically, we catered for high performance soft actuators that require strain in terms of high output force, low electric field, and fast response. And coupled with the possibility of having self-powered and self-sensing. And most importantly, how do we tailor these soft materials for durability and resilience? In this case, the toughness, tensile strength, and longer shelf life, as well as operation in harsh environment would be critical. So one of the work that we have demonstrated these would be the use of a photothermal modulated dielectric elastomer actuator. So we have incorporated the use of liquid metal that is processed into nanoparticle size form with a good size distribution of about 250 nanometer, and added into a carboxyl polyurethane material that is optimized for both a high strength as well as a mechanical toughness. The use of liquid metal over here provides the ability to have minimize a conductive pathway. Okay, over here, the purpose is not to use the electrical conductivity, but to make use of the shell that is surrounding the liquid particle in the solid form, and to increase the dielectric permittivity. In this case would be the dielectric constant measured as a function of liquid metal concentration. You can see that the dielectric constant is actually increased and the dielectric loss would be reduced, indicating that there is less electrical pathway conducted through this composite. So this composite also shows a good tensile strength property with different weight percent of liquid metal added from 15 to 50 weight percent. And as we increase the liquid metal concentration, we notice that the Young's modulus, it doesn't vary much, but increased slightly. Most importantly is the toughness. It has a peak and then it drops. The reason is due to aggregation that has prevented the toughness to sustain in terms of the viscoelasticity. So the hysteresis loss will tend to increase as well because there is this breakage of the bond between the polymer that is disrupted in the presence of the liquid metal particle. So as we can see, the fracture toughness, there will be some gradual breakage as it exceeds a certain amount of strain due to the crack advancing and crack blunting in a repeated cycle manner. So if we look at the 15 weight percent, it still show a sharp fracture, but for higher amount, there would be this gradual fracture happening. So the optimum concentration at 15 weight percent would be utilized. And this is in agreement with the electrical property that sort of shown that the 15 weight percent elastomer composite has the highest area strain when we apply an electric field. It generates a Maxwell pressure that increase the strain at a certain electric field. When the liquid metal amount is too high, then you can see the breakdown voltage reduce. So we cannot drive the electric field too high for the 33 and 50 weight percent. So the beauty of this work is also the recovery. In the light of circular economy, right now we're trying to achieve, not just self-healing, but possibility of recover the material after damages. So we cut this material into pieces, and then you can do a simple hot press to recover the material, and mechanically it can be recovered very well of close to 60% in the healed area strain. Right. Let's say if there is a DEA and you found an electrical hotspot that burns a hole. Similarly, we can also do a hot press to recover and heal the electrical device. So electrical recovery in a device level would be slightly lesser than the full mechanical recovery. Nevertheless, this work shows one of the most efficient recovery approach that we can have for the purpose of recycling ability. Because of the incorporation of liquid metal, we can also have core stimulation, meaning that we can apply both electric field and light to trigger the actuation. So here, this is without light. And as we increase the intensity of the near IR light, we can find that it's easier. It happens at the lower electric field to achieve a same area strain. right? So this reduced driving electric field sort of save the consumption for electricity and prevent the use of high voltage for such a device. So having a core stimulation would be effective when it's comparing with many composite DEA. In this case, it achieved a tunable modulus, improved dielectric constant, and higher breakdown field strength. So we use it to demonstrate a crawler where in the presence of light, it increased the stride in terms of X and Y direction. So as we can see here, this can be when the crawler is navigating a tunnel, for example, it's just a pure electrical actuation. It doesn't have the flexibility to adjust too much, and then it gets stuck in this tunnel. So we use a light to enhance the stride so that it can go in both Y and X direction in a larger stride manner to trigger the locomotive robot. Okay, so not just in nature, not just animals are moving, but also these plants, right? That they're also having moving structure. So inspired by nature, we have done this work some time ago using a bilayer structure emulating a leaf. That's inspired by their structure where they have the epidermis with the vein skeleton and a palisade mesophyll, which captures light, with the stomata providing the moisture. So we use cellulose and mexine and put it into a membrane to have a bilayer structure to support. And the cellulose serves as the vein skeleton, and the membrane, which is polycarbonate, is stronger. It is the stomata and epidermis that facilitates the water transport. So mexine is incorporated for capturing photoconversion efficiency. It also has a good electrical property and thermal conductivity. The cellulose, on the other hand, it is stronger, having a higher elastic modulus and a low thermal expansion coefficient, with a lot of functional group that works well with mexine. So this kind of composite between mexine and the cellulose creates the ink that is printable, and it has the hygroscopicity that is tunable. And the intermolecular hydrogen bonding between the two makes it stronger. And when casted onto and printed onto the membrane that is inert and hydrophobic, it provides an ability to actuate under different stimuli. So the presence of water has a big role to play because mexine has many interlayer galleries. So when water is adsorbed and desorbed, the interlayer dielectric, interlayer lattice spacing can be adjusted, and it will lead to the curling or the movement of the soft actuator here. For example, under different humidity of 10% or under electrical power, when a small voltage is applied, right, the compliant membrane stack here would change due to the mismatch in volume changes. And the very rapid water desorption causes the contraction in the mexine layer, and the polycarbonate membrane would expand when it is being heated. So this can also be controlled using electricity, where we apply electrical power to trigger the changes in the bending angle, and is rather systematic. A largest bending angle is at 147 degree, and at the fairly low power of just 5 volt, indicating both the thermal and hygroscopic nature of this actuation. When we use the NIR light through the imaging, we also see a rapid change in temperature because mexine has a good ability to capture the photothermal conversion. So it reaches 80 degrees within several seconds. And this movement of the actuation can have a very fast RAM rate compared to just the pure mexine used when we formulate the composite. So we follow the two data measurement. In this case, when we see the difference in the lattice spacing, when it is subjected to light, you can see that the shift in the peak corresponds to the amount of water. So the illumination intensity as a function of the D-spacing can be found here. You can see that the Maxine cellulose composite has a very large change in D-spacing when it is shone by light at the different intensity. So this very effective light trigger self-actuator is also cyclable through many cycles. Comparing the Maxine cellulose with the pure Maxine, you can see that the static force generated over multiple cycles can be shown. This generated stress or strain is comparable to the mammalian skeletal muscle for a self-actuator purpose. So over here, we also demonstrated the ability to sort of have a worm-like robot or smart switches. We can also encrypt information that visible eye cannot see, but under the IR light, there will be camouflage information that is being displayed in a dynamic manner. So then, we realized that having this Maxine and also composite, it is a very good platform for electrochemical actuator. The benefits of electrochemical triggered actuator is the low voltage application and low power consumption. It has a structure that is similar to a battery where you have a cathode and anode. It is simple, lightweight, as well as a very small structure. However, in the Maxine, it is always having this difficulty of the nanosheets that gets restacked, limiting the amount of ion stored and the diffusion limits. So the wetting ability of the composite layer is also a key aspect because eventually we need a high amount of ions, that is cation or anions, that gets absorbed and intercalated to create the strain difference. So what is done here, it's a molecular hybridization using methyl cellulose to prevent the stacking of Maxine. Instead of just a pure physical nanocellulose, methyl cellulose is being used because it can couple very well with the Maxine surface as shown over here. And with this, the aggregation actually prevents and controls the hydrophilicity and allows the vacuum filtration to create this scalable stacking up of hybrid Maxine films. So with this, we also use the X-ray diffractometer to follow the difference in the D-spacing and measured as a function of the methyl cellulose content. So compared to the neat Maxine versus the hybrid Maxine, we can see that the D-spacing variation is fairly small, but is discerning enough for us to show the difference. And as a fraction of methyl cellulose increased to 28%, the distance in the 002 direction actually continuously increased. So this leads to a difference in the strength and the modulus. And of course, the moisture absorption rate is also varied. While the conductivity may not be beneficial because Maxine is really inert, but with the conductivity of 10 Siemens per centimeter, it is sufficient well for use in electrochemical actuation. So a sandwich structure is being fabricated, and we can see this movement or displacement in the presence of electrolyte in a very systematic manner. And this electrochemical actuator can also load and lift a load with 2 or 3 times the weight. Based on this very thin strip, it can lift a small object and pick up a very compliant and deformable object. So the other design, which is also the last example that I want to share here, is how do we also use the so-called ions, right, to further help the soft actuator. We have shown earlier electrochemistry that is based on ions, and how about a gel, because it has a lot of ions as well. So inspired from the gecko-like structure here, we want to achieve adhesion that can be controlled by electricity. An electrically controlled adhesion triggered by the changes in the ions motion. Therefore, we have used the ion gel to replace the electrical conductor, so that you can have both cations and anions that is serving as the conductive layer, sandwiching the dielectric elastomer. So in this case, we can have an integrated layer where an interdigited electrodes is found here, where the fringing field out of plane would be formed because of this positive and negative charges that create the electrostatic force. And this component 2 that has the electroadhesion property would be used to serve as an additional function for grasping of very soft and delicate object. Meanwhile, the top component 1, which is the DA that you have shown, that you have seen earlier, it's the one that trigger the movement that's close to the object. So this is an integrated approach, and the good thing is that we synthesize our own material, so the whole device is actually self-healable as well. So the gel that we use is not just normal gel, but it's actually an amphiphilic polyelectrolyte gel that consists of PMA, and over here there's some cations that is actually chemically cross-linked to the gel. The elastomer is also synthesized using step polymerization. It has the ability to self-heal because of the use of urea pyridinone that is bonded to the urethane main chain. Okay, so this combination of the two leads to an ionic dipole interaction that provides a very strong interfacial toughness. And this is important because very often we found that the gel and elastomer, it doesn't have a very good interfacial adhesion. For example, on EcoFlex, it can easily peel, whereas on our prepared elastomer, you can see high stretchability with strong repeated dynamic tests that has a very good adhesion in this case. Okay, so we measure the normal force and the shear force, okay, as a function of voltage. You can see the normal force, of course, would increase, and it's better for the conductive aluminum plates. For glass, it would be lower. Interestingly, the shear force over here, it's actually higher compared to the normal force. So this is tested on many different substrates, be it conductive or non-conductive. The shear force measured here has a higher adhesion pressure as found compared to the normal force because of the design of this interdigited electrodes that has a good fringing field that provides the adhesion. So the gripping is being demonstrated on a heavier object with a payload of 670. It's also possible to pick very thin profile object that is without any feature like leaf or soft tofu that is slightly wet because it's coated with hydrophobic layer as well. So this kind of electrodes, of course, is suitable for capacitive sensing. So the self-sensing ability is integrated and it can be used for contact sensing or proximity sensing. So when it is anchored together with multiple, there are 4 over here finger, it can be used to detect or spatially resolve the object position based on the difference and variations in the capacitance for each of the finger. So it shows the intelligence of soft robotic in the future for self-sensing ability. Okay, so in short, I summarize here, we synthesize electroactive materials based on the requirement of soft actuators and sensors. Through the use of electronic and ionic conductor, we use multiple stimuli to achieve soft robotics application and healthcare applications. So I acknowledge the funding agency, and I'd like to thank my co-workers who have contributed to most of the work here. Thank you very much.
Thank you very much, VC. Actually, I'm supposed to introduce you just now. Any questions? Maybe interesting, or in the interest of time, maybe we'll take one or two questions. Any questions? Seems like you give a very, very clear and very easy to understand talk. But anyway, because of time, I think if you want to ask any questions, maybe during lunch, I think you'll be around, right? Okay, thanks very much, Tracy.
Yeah.
Thank you. Let's give a round of applause. Okay, our next speaker is Assistant Professor Wu Changsen. Changsen is actually a presidential young professor at the Department of Material Science and Engineering Department at NUS. He's also a PI at the Institute for Health Innovation and Technology, and also N1 Institute for Health. He did his PhD in MSc from Georgia Tech. Also did his postdoc at Northwestern University with John Rogers. So I think today is going to talk about wireless skin interface, optical and mechanoacoustic sensors. Yeah, Changsen.
Thank you, Prof. CT, for the nice introduction, and the organizers for inviting me to this exciting event. Today, I'm going to introduce our recent progresses on wireless skin interface, the optical and the mechanoacoustic sensors for deep tissue monitoring. So, over the past few years, we have seen several global issues on population aging and the outbreak of pandemic. And there's clearly a clinical need in the change of practice from centralized intermittent healthcare to pervasive and continuous healthcare. So the way people are, one great way to do that is through the use of wearable electronics or wearable biosensors that several speakers have spoke about. So the interesting thing about the wearable sensors is that they all measure in the properties of the skin. Why skin? Because skin actually, to material scientists, is a very interesting and natural material system that's 3D multi-layered, multifunctional, and heterogeneous. And actually, its dynamic properties are highly correlated to physiological information. For example, the electrical impedance to hydration, the potential to ECG or EEG, and also the optical properties to the concentrations of different biological materials inside of the tissue. So for the past few years, I have been working on the use of optical and mechanoacoustic sensing in order to extract the information underneath the skin, not just from the deep tissue. So like the bottom images here. So the first topic is about how we use near infrared spectroscopy sensor to measure the optical properties of the tissue for hemodynamics monitoring. So there was a clinical need that approached us saying that, okay, there will be neonates that have these neurological problems, which will cause them to have regulation issues in the nerve system. And so in these cases, they will not be able to sense the insufficiency of blood oxygen supply in the brain, and they will cause sudden death in these children or kids. So that's why we developed this serpentine-based soft optical device that can measure the blood oxygenation saturation inside the brain tissue itself. So the whole device because of the flexible electronics design. It's very soft and flexible, and it can be easily bended and conformally attached to the soft forehead of the neonates. So the whole device consists of the sensors and also communication modules, and the use of serpentine serpentine structures enables the whole device to have a soft property that's similar to the intrinsic skin. So although it's not perfectly matched to the skin modulus or bending stiffness, it's actually in the range of in the range of or in the same magnitude, order of magnitude. So that's why it can be safely and conformably attached to the skin of the human foreheads. And as I mentioned, this was so we developed this sensor to meet the clinical needs from pediatricians, and the end goal is that we can deploy these sensors at home so that the brain oxygenation saturation level can be monitored remotely when the baby is doing daily activities, instead of keeping the baby in hospital for continuous monitoring. So we hope this device can safeguard the children's growth to prevent permanent damage to their brain due to neurological disease. And we developed the sensor with a structure of 2 LED sources at different wavelengths and an array of 4 photodetectors. The reason we're having an array of distances between the photodetectors and the light sources is that we want to probe the tissue information at different depths. So by using the MRI data and the optical simulation using Monte Carlo analysis, we will be able to calculate the percentage of light we measured at each photodetector at different distances that are actually coming from different depths. So as shown by the bottom image here, we can see the percentage of light coming from deeper tissues increases with the distance between the light source and the photodetector. So based on this LED array, LED photodetector array, we will be able to achieve depth resolved oximetry. So by using the information from different photodetectors, we will be able to estimate or calculate the tissue oxygenation information from both the peripheral tissues and the cerebral tissues. And we compared the results with the clinical gold standard equipment and found a very good match in the changes of oxygenation and also heart rate when we perform different physiological activities. For example, breathing, holding the breath, or for holding the breath in this case. And also we deployed the sensors of patients with cerebral health, with a disease called congenital central hyperventilation syndrome. So these patients will only take shallow breaths, and they will not be able to regulate their breaths with the sense of low oxygenation. So in the first case, we conducted a head-up test on them. So in this case, we tilted the angle of the subject, so their oxygenation will decrease. But because of the impairment in their autonomic nervous system, the oxygenation will not recover. So, and we only see the recovery in the oxygenation after they were tilted back down. So we also conducted hypoxia challenge and on both the healthy and the patients, health subjects and the patients. So, and we did a statistical analysis on the accuracy of the system compared to clinical gold standards, and found a very good match in the results, which validates the clinical soundness of our devices. And also for we also found clinical needs in the flap monitoring, which also requires the measurement of local tissue oxygenation. So especially after the plastic surgeries. So after plastic surgeries, clinicians will use the tissue oximeter to measure the perfusion inside the transport fluid flap. And in such a case, the patients need to stay hospitalized for 5 to 7 days just to monitor the health status of these transferred tissues through oxygenation. So previously, the commercial device is a bulky system with tethered configuration. We customized our previous near sensor to be a fully integrated wireless system, so that the patients can wear the sensor outside the hospital to achieve tissue oxygenation monitoring even at home, so that we can greatly reduce the time of hospitalization. So we conducted the animal study and the human clinical study. And for the animal study, we introduced ischemia and congestion events on the arterial and the venous respectively. So we can see when we introduce those ischemia or congestion events, there's a dramatic drop in tissue oxygenation, which matches well with the measurements from the commercial instrument optics here. And also we have conducted the human clinical trials for 4 to 6 days. And we are currently increasing the number of clinical trials to further validate our devices in different scenarios. So, and also by increasing the source detector distance, we will be able to further measure the tissue information in deeper tissues. So in this case, we increase the distance from up to 32 millimeter, and we will be able to measure the brain oxygenation from adults. Then the next topic is about how we use mechanoacoustic skin devices to measure the motion or activity or cardiac activities from human body. So the research can be dated back to 2020, where people have developed this soft mechanoacoustic device to measure the various physiological informations. By putting the sensor on the supraosternal notch, the skin vibrations give us information of vital signs like heart rate, respiration rate, and also unconventional biomarkers, including coughing, sleep dynamics, or speech. But back in the days, we were thinking, instead of measuring point vibrations on the skin, what we can do if we can measure the wave propagations through the tissue. So here we proposed an idea of using an array of mechanoacoustic sensors, and through the measurement of wave propagation, we will be able to correlate this phase wave velocity to the mechanical properties of the tissue under the skin. And in this case, which is the modulus we care about. So why modulus? Because conventionally, if we want to measure tissue modulus in vivo, we need to use very sophisticated instruments like the ultrasound elastography or optical coherence tomography. And of course, there are recent developments of wearable ultrasound patches that can enable us to measure the blood pressure or even ultrasound elastography imagings. Still, they are very high cost, and also they involve sophisticated analysis algorithm, which here, what we are trying to do is to achieve a balance between the sophistication, the cost, and also accuracy of such measurements. So the idea is to use an acoustic exciter to generate acoustic waves, and then use the mechanoacoustic wave sensors to measure the wave propagation. And through that, we can achieve a wireless wearable measurement of the of the tissue stiffness continuously. And this is different from previously reported palpation-based wearable sensors, because for these sensors, they need a calibration of the measurement calibration to achieve an accurate measurements. But because of the principle of using surface wave propagation, we do not require calibration to estimate the tissue modulus. So here is a closer look at the devices we have developed. So on the right side, we will have the two high bandwidth, high fidelity MEMS-based accelerometers for measuring the skin vibrations. And on the left side, we have the main electronic circuit boards that will be in charge of power supply and also wireless communication. So in between, we use serpentine structures to electrically connect the sensors and the control circuit, while mechanically isolate them, because the main circuit board is rigid, and we don't want that to affect the skin and the subtle skin vibration measurements. So we can see on the right, the customized serpentine design definitely helps with the overall softness of the device, and we can easily bend it and also easily apply the sensor to different curvatures of the human body. So, and also we implemented a wireless system that can enable us to remote control the device and also to transport the data out wirelessly for in situ or simultaneous data analysis. So so how we can achieve translate this measurement of skin vibration or wave propagation to tissue stiffness? We constructed a bilayer tissue model. So with the collaboration with our Professor He Ling from Tsinghua University. So by using this bilayer tissue model, it enables us to simplify the estimation of tissue modulus at different layers or different depths. So the first layer commonly used in by the biomedical community is the skin fat layer, and the second layer is a muscle organ layer. And because of this two-layer bilayer design, we and also the intrinsic property characteristics of surface wave propagation, so we can assume that as long as the wave is propagating at a high enough frequency, most of the propagation will stay in the first layer or the shallow depths, and the measurement of these wave properties at high frequency actually can be translated directly to the properties of the first layer. So in this case, it greatly simplifies the analysis, and later I will elaborate more how we can extract the information from the deeper tissue, which is the second layer. So firstly, we validate the device on two-layer phantoms made of elastomer materials. So, and we use, because we want to measure a spectrum of frequency responses. So for the acoustic excitation, we used a broadband white noise with a frequency range from 50 Hertz to 800 Hertz. And we compared the signals generated and also the background noise. And because of the use of high fidelity accelerometers, we can achieve a good signal to noise ratio, about 20 dB, which enables us to measure the tissue modulus even during continuous motions by the subject. So, and from this measurement of wave vibration signals, we will be able to derive these dispersion relationships between frequency and wave number. And the use of this dispersion relationship will enable us to extract the tissue modulus at two different layers. But how we did that is through the use of finite element analysis, and by using the FEA model, we will be able to construct a scaling law of the wave propagation for this kind of bilayer model, bilayer materials. And for this scaling law, we try to correlate 3 different independent variables. The first one is non-dimensional velocity, which is the measured phase velocity divided by the shear wave velocity at the first layer. And the second one is the non-dimensional frequency. And the third one is the ratio of shear wave velocity between 2 different layers. And through FEA analysis, and this plot actually summarizes the relationships between them. And one observation is that as long as we have a high enough frequency, the ratio between the measured phase wave velocity and the estimated or the actual shear wave velocity from the first layer will converge to a constant. This actually allows us to directly obtain the shear wave velocity of the first layer and also the tissue modulus of the first layer through the measured wave velocity by assuming a threshold of 0.6 for non-dimensional frequency. And then by optimizing or minimizing the difference between the measured dispersion relationship and also the FEA-derived dispersion relationships, we will be able to obtain the optimal values of the shear wave velocity of the second layer and the thickness of the first layer. And from there, we can directly calculate the we can directly calculate the modulus of both layers. Then we tested the algorithms and the system on 19 different phantom materials. And on the right is 10 representative dispersion plots, and on the bottom is the plots of the estimated modulus across different layers. We can see that the estimated modulus is in close match with the gold standard values from 10-TILE test. And these estimations do not require prior calibration. And we can just, and the direct estimation will be in good match with the 10-TILE test. And then we did in vitro validation on synthetic tissues. And by replacing the materials on the top layer, on the first layer, in between the 2 accelerometers, we can introduce different modulus changes in the synthetic tissue. And we can see by comparing the measurements with in parallel ultrasound elastography, we can see that the modulus change are in the first layer are properly captured by our technology or system, and we can also see the estimation of the bottom layer, the layer 2, were unaffected by the introduction of inclusion in the first layer. And also we did in vitro validation on animal tissue, which is the porcine tissue. We injected different amounts of PBS solution or water solution into the muscle layer. And we can see, as we increase the injected water amount, we see a constant drop in the modulus of the second or muscle layer, and we see a stable measurements of the first layer. And these values are all in good match with the average values from the ultrasound elastography. And then we did the in vitro muscle stiffness test while the subject is holding different weights. And we also see a constant increase in the muscle stiffness as we increase in the weight. And these values are also in good match with the measurements from the ultrasound, from the depth from 1 centimeter to 2 centimeters. Then we did a continuous monitoring of the tissue mechanics, which is a tissue modulus in this case. And this is undoable with the conventional ultrasound instruments or OCT systems. And firstly, for the first 30 seconds, we ask the subject to hold the weight at 3 different positions so that we can compare our measurements with ultrasound measurements. And then afterwards, in the second 30 seconds, we ask the subject to cyclically lift the weight, and we can see cyclic periodic changes in the tissue muscle modulus changes. And here's a small video showing the process. So for the first 30 seconds, we can see the steady measurements of muscle modulus, and then in the second 30 seconds, the system will be able to capture the continuous changes in the muscles. And as a junior faculty at NUS, I just started my lab, and currently we are working on synergize the energy technology and also the bioelectronics technology. And together with advanced manufacturing techniques, we want to achieve sustainable biosensing technologies and towards sustainable digital health. And we are always looking for talented PhD students to join our program. And lastly, I would like to thank my previous advisors and groups, and also my collaborators for their continuous support. Thank you very much.
Thank you, Johnson. Okay, any questions? 1 or 2 questions? Yes.
Professor, thank you for the very thank you. Professor, thank you for the very nice talk. So I have a very quick question about the first part for the optical sensing. Can we also control the sensing depth of the sensor? For example, if we want to collect the information from both the tissue at the small depth and at the large depth, can we also achieve this type of sensing?
So you are asking whether we can measure different
the depths for the further part of their presentation. I think in this part you already show the capacity to measure both types very clearly. For the first part of this presentation, can we also achieve a similar?
Yes, so that's why we have this kind of array of photodetectors at different distances. So the larger the distance, the more information we can capture from the deeper tissue, because the light will more light will be actually coming from the refraction or reflection from the deeper tissues.
Okay, so you can measure both the
yes. Yes.
Okay, I think in the interest of time, we'll stop here. Please join me to thank Johnson again for interesting talk. Okay, we'll move on to our last speaker before lunch. It's Professor Lian Duan. He received his PhD from Department of Chemistry, Tsinghua in 2003 and is currently with Department of Chemistry, Tsinghua. His research interest is in new organic materials for flexible optoelectronics, and he has authored and co-authored over 300 SCI index papers and also over 180 patents filed with 102 issued. He was also awarded Distinguished Young Scholar Fund by the National Science Foundation of China in 2015, and also appointed Changjiang Scholar by the Ministry of Education in 2020. So, it's time to
thanks, Professor Lin. And I'd also like to thank the organizers for inviting me to this forum. Actually, this is my first time to be here in Singapore. This is my first visit to Singapore. And as introduced by Professor Lim, I'm the last speaker of the morning session. So I'm under big pressure. I have to be quick. So in order, you might not be too hungry, okay? And I'm working on OLEDs. So I'm going to talk so this is I'm from as you can see, I'm from the Department of Chemistry. I'm a chemist. And so we are working on materials. We are working on organic materials because they are intrinsically flexible and they can be made into excellent flexible devices. You can see, and here are these are flexible OLED foams which can be folded and convex and concavely, and also rollable OLED TVs. And in the future, we might have OLED that can be bent upward, both inward and outward. This is what we've done in the lab. And OLED is now becoming one of the mainstream and display technology. So this is just some comments from Nature. They said that to graduates, and so the OLEDs might be a lucrative career for young students. So I'm just here to say that please if you have interest, please work on OLEDs, and also we can combine OLED with other to make OLED as a flexible platform for other flexible electronics, and that would also be very interesting, I think, and that's what we are working with together with Professor Feng. And for the display, we have to have high color quality. This is by the International Telecommunication Unity. They said they released this new standard for this ultra high definition displays, and they should not only have high resolutions but also have wider color gamuts. So to achieve wider color gamuts, we need emitters with narrowband emission characteristics, which is relatively difficult for OLED materials. And so this is the first generation of OLED materials, as they are fluorescent fluorophores, and only 25% of the singlet excitons can give light. And then in 1998, people invented this kind of phosphors, and with the which can utilize the both excitons from the 25% singlet and 75% triplet by this very fast intersystem crossing. But nevertheless, these emitters are nowadays used in cell phones, but they are not perfect. So people are working on new materials. This is another kind of materials which is very popular and also regarded as a third generation of materials, which was invented by Professor Adach and called thermally activated delayed fluorescent materials. The gap between the dark triplets and bright singlets is very small, and so under environment, the heat of the environment, the triplet can be activated to singlet and then give light. But there's also some conflicting factors in designing effective TADF emitters. We need to finely tune the overlap between the frontier orbitals. And to overcome this this opposite requirements of the singlet triplet of the distribution of the frontier orbitals, and so as we can have a balanced up conversion and also a very fast radiative decay, we just proposed this new mechanism which called TADF sensitized fluorescence. So instead of using TADF materials as emitters, we use them as sensitizers and took the advantage of this long-range Foster energy transfer, so that the triplet in the TADF sensitizer first goes to singlet and then transfer its singlet to the final emitter, which is so we call this is a TADF sensitized fluorescence. So we can that we can. But with this combination, the up conversion and the light emission, these two functions can be optimized independently. So we call it TADF sensitized fluorescence, which also we can call it a kind of a Tsinghua fluorescence. That's what we are working on it. So to combination this TADF sensitizer, we can also go with, we have this conventional fluorescent emitters. They can have relatively narrow emission for the first peak, but they have strong filters. And we also have this kind of multiple resonance emitters because the frontier orbitals localized on the individual atoms, so that they can have also have a narrowband emission. So that we are so that in this in my talk, I will just mainly focus on the development of this kind of emitters, and together with our new sensitizers, we can see that because they have a kind of non-bounding orbital characteristics, so it is relatively hard to tune their emission colors. This is a kind of this with this boron and nitrogen. They have an opposite electron. They have an operative electron properties. One is electron withdrawing and one is electron donating, so that we can use this triangular structure to make narrowband emitters. Here the first one is to redshift the color without increasing the bandwidth, and also the other is to increase the intersystem crossing, and we can do this by using a TSF. Also, we have to avoid quenching of these emitters because they have relatively planar structures, and so we also need to develop new multiple resonance skeletons. And here this is a Dabna structure with this boron and nitrogen triangulum, and it's blue, but it's relatively difficult to sensitize. And then we changed we just linked this nitrogen with the atom, the phenyl on this nitrogen atom into carbazole. We make amine into carbazole, and the synthesized procedures can be simplified, and also the emission bandwidth can be maintained. And another thing is that we can simply tune the emission color by just changing the substituents on the opposite on the para position of the atom on the benzene. So if we use electron donating groups on this para position of this phenyl ring, we can reduce the charge transfer characteristics in this system, and then we can blue shift the emission. And if we use electron accepting units onto the para position of this phenyl, we can increase the charge transfer characteristics so that the emission color can be redshifted. And I'd like to show you how effective it is. Just this is the CZBN that's with it, and this if we use by this electron donating and electron accepting, and with this kind of we call it a synergetic, coupling. We achieved the first green multiple resonance emitter, and its emission is green, and its efficiency is also very high. And you can see that, and these are pure green emitters. And how to further redshift the color into the red region and even the near infrared region, and then we just use this kind of strategy, and by the same strategy, we should increase the charge transfer characteristics. That is, we increase both the donor and the acceptor. That is, we use this kind of code. This is boron. This is boron pi boron and nitrogen pi nitrogen. With this with this para position of the boron, we introduce stronger electron accepting properties, and and with this nitrogen pi nitrogen, we increase the electron donating properties so that we could achieve deep red emitters. And because of this non-bounding structures in this kind of emitters, we could significantly lower the vibronic frequency in these molecules, leading to a very shallow power. This is the PSE, which is a potential energy surface. A lower potential energy surface means that we can break this so-called this energy gap law and achieve high efficiency in the red region. So these are the emitters we've developed. Very simple, this part is CZBN, just the double of CZBN, which is a deep red emitter. And if we add some protecting units, protecting bulky substituents, its emission color is redshifted. And the PQY of these emitters, that is the photoluminescence quantum yield of these emitters, can be 100%, even though they are in the red and deep red region, and also very high external quantum efficiency in organic light emitting diodes, making them the best results for the deep red emitters. And another thing is that we also developed another strategy, because that with this we found that we could also enlarge this multiple resonance skeleton. We call it other fused MR emitters. We can see that by increasing the size of the linked rings, the alternating distribution of the frontier orbitals was maintained. And in this case, we can achieve even narrower spectrum than the former strategy we've developed. We can see that this is also a very nice red emitter, very nice green emitter. It is even redshifted and to the pure green region. And so that with this, we made this a very high efficiency devices, and with also acceptable lifetime. And we also to combine these advantages of these above mentioned strategies, we use this kind of a fusion strategy, which is we used a kind of a reached high units together with these multi-resonance units. We achieved even smaller shift of the between the ground and the excited states, and also lowered coupling between the vibronic states and then less vibronic peaks. And we can see that this is a very nice emitter. Its emission bandwidth is further reduced from 30 to 20, and nowadays we can achieve even something below 10, and making them very nice green emitters. And the performance of this device is better than the commercial OLEDs used in your cell phones. If you use iPhone, if you use any Android phone like Huawei or Samsung phone, they use OLED displays. And if our emitters can be used and can be integrated into your cell phones, it would be more power saving. And we're also working on to just like multiple fusion to further reduce the bandwidth. We can see that very narrow band, and less than 20, and for these emitters, and very high efficiency. And as I've mentioned before, these emitters, they have planar structure. So how to protect them from concentration quenching, that is a problem. And we used this kind of wrapping strategy. That is, we use, and also we can to the declaration of the power position, and because this benzene ring and this multiple resonance ring would position like this, and so that, and together with perpendicular to each other. So together with one more protection units and another one more, we can get perfect protection of these emitters. Here we can see that this is without protection, this is with one side protection, and this is with both side protection. We can see that with the increasing of the doping concentration, we can see without protection, we can see redshift of the color, and also broadening of this bandwidth. But for this protected at both sides, its emission spectrum remained unchanged, and we can achieve a very high efficiency for this emitter with well-protected emitters. And we also use that. We also try to develop other methods to protect these emitters from concentration quenching, and we can see that macro cycle is also a well adopted, is also is also a very effective strategy to protect protect the emitters, and we just borrowed this idea into our multiple resonance emitters. We can see that this is calixarin based emitters, and we can see that it's crystal. It looks like a small cap, but this kind of just like a small cap, and this is also concentration quenching little luminescent caps, so making them ideal emitters for OLED displays. And as to these emitters, we can also make high efficiency devices. And I'd like to show you here, we have made perfect red and green and blue emitters. Actually, both the performance of our red and green emitters are much better than the commercial materials used for our current OLED displays. And we are working hard with companies to commercialize these emitters, and hopefully we can see high-end cell phones with our emitters in the coming years. But the most difficult thing is blue. Blue has the highest energy and the lifetime. The high efficiency blue with a decent lifetime remains the holy grail for the OLED emitters, and we are also working. And I think that this our TSF strategy with narrowband emitters would be a key to solve this problem. And this is what we've been working on. We developed sensitizers with very high up conversion rate, which means that kinetically the resonance time of the triplet would be shortened, and we can get a very stable deep blue devices, but the lifetime was not high enough, was still not long enough. And how about sky blue one? Yes, we are working on sky blue one, and we can see that its T95 is over 400 hours, which is very close to the requirements of commercial applications. And that is, if you can achieve deep blue, that is blue with CIEY less than 0.1, and together with a LT95, that means the time takes to lose the 5% of the initial luminescence. Around 5 hours would be good enough for commercial displays, and this is what we've been working on, and hopefully we hope our blue devices would also be used for the next generation cell phone. And I'd like to summarize. And in this talk, I've just summarized our work on TADF sensitized fluorescence OLEDs, and we call it TSF OLEDs, and it has many advantages such as high efficiency and low cost, high color purity, and also with improved lifetime, making them ideal materials for the future flexible displays. And that is all of my talk. And here's a picture of my team. We are climbing a mountain, and this is this is Dr. Zhang. He's working on narrowband emitters, and this is also another Dr. Zhang, and he's working on synthesizers. And these are my assistant. These are assistant professors in my group, and these are my students. Thank you.
Thank you, Professor Tuan. Any questions?
Yeah. Thank you.
Very nice work.
Thank you, Professor Gao.
Wondering that split. So what kind of challenge does flexibility pose in addition to other chemistry?
Actually, OLED materials, they are organic, so they are intrinsically flexible. Yeah. But the problem is that we have to use inorganic parts to make the display work. That is, we have to use TFT, which is silicon and or oxide TFT, and also cathode metals, and that's the difficult part.
Any other questions? I think everybody is hungry. If not, let's thank Professor Tuan for very nice work.
Yeah. Yeah. Okay. Thank you and good appetite.
Okay, we're going to have lunch now outside.
Since we have a delay, so our afternoon session will start at 2:20. Yeah.
Welcome to the afternoon session. In our session, we will have three speakers. The first one by Professor Yifan Wang. So Yifan is Nanyang Assistant Professor in School of Mechanical and Aerospace Engineering, NTU. So he received his PhD in physics from the University of Chicago, and bachelor degree from Peking University. So prior to joining NTU, he worked as a postdoc at the Mechanical and Civil Engineering at the CIT, California Institute of Technology. So Dr. Wang's research focus will be on soft material, architect lattice, soft robotics, and so on and so forth. So let's welcome Professor Wang give his speech.
Okay, thanks, Prof. Zheng, for the introduction. Okay. All right. Okay, so I am Yifan Wang, and I'm from School of Mechanical and Aerospace Engineering at the NTU. So strictly speaking, I do not work in the area of electronics. So I'm working in mechanical engineering and software robotics. But I find they share a lot of things in similar the materials and the structures. All right. So first of all, just similar to electronics, robotics starts as rigid with very many rigid components. So here, first, I'm making a comparison between rigid versus soft or flexible robots, of which many of you may already know, right? So robots with rigid body will have higher load-bearing capacity and work output, while on the other end, softer robots brings larger flexibility on the body and also safer interaction with humans or other biological bodies. Okay, so over the past years, researchers have been trying to push robots from very rigid components to softer and softer structures. So until here, this is a well-known octopus robot that is entirely soft on the body, right? So there is a shift from rigid to soft in the field of robotics in recent studies. So one question that I'm trying to ask today is, do soft robots need to be entirely soft? Right. So if we look at the materials in terms of the Young's modulus that is used to create soft versus rigid robots, we can see that there is a apparent gap here. So for soft robots, it's typically made from soft materials. So modulus typically 1 gigapascal or less, while rigid robots are made of much stiffer materials. So there are benefits and shortcomings for using entirely soft materials. I just mentioned there are shortcomings here, all right? So first of all, using entirely soft materials for robotics, we have load-bearing capacities, of course. It will provide limited support or protection against heavy or high-energy objects, and also it has limited work done to the environment. So after all, for a robot, the most important function is to perform work to the environment, right? If you have an entirely soft body, then the work output will be very limited. So we always take inspiration from nature. So how do biological creatures do this? You can see that from inspiration, even these soft creatures are not entirely soft. For example, a sea cucumber, a sea animal, or starfishes, for example, if they're not under external threat or stimuli, the body is very soft. However, if we touch it or apply a stimuli, it can turn rigid, right, for protection. Another example is an elephant trunk. So the trunk can be very flexible so that it picks up very delicate objects like a banana. And also at the same time, if it needs to perform a heavy task like picking up a chunk of wood, it can also stiffen itself. This is due to a hydraulic system. So biological creatures have different mechanisms to change their stiffness on demand for various tasks. Okay, so the very most useful robot would be something like this, that it combines different functions. For example, self-sensing, shape changing or shape morphing with stiffness variation to perform tasks in versatile environments. So that will be the main purpose of my research. Okay, so what I'm trying to do is to combine the robots from the soft state to a rigid state, and it can change themselves on demand. So soft states give them very high flexibility for shape changing, while the stiff states will cause a high load bearing capacity and also provide support to the body. So this is mostly used for wearable robots if we want to interact with humans. So this type of function is necessary, right? So we can look at what type of materials existing that can change their stiffness. So one example is magneto or rheological materials such as fluids or elastomers, right? These have magnetic particles or dielectric particles inside the fluid or elastomer body. When high electric field or magnetic field is applied, the particles will align or cause stress inside the body to make it stiffen. However, this typically requires very high magnetic or electric fields. The magnetic field is on the order of Teslas, or the electric field is on the order of kilovolts or even 10 kilovolts. So this is not typically safe for wearable applications. So other examples include phase-changing materials such as liquid crystal elastomers that can change its phase upon temperature and also is modulus. However, it requires high temperature changes to trigger the change. The actuation is slow, and also even in the stiff state is also too soft to provide enough protection. Other examples include shape memory alloys or polymers, which have the same problem with having temperature actuation, so it's slow and also need reprogramming at higher temperatures. So my research takes an inspiration from a soft material system, which is called granular materials. Okay, so this is a very well-known effect for granular materials. So granular materials are basically a collection of rigid particles. So if you go to the supermarkets, and sometimes you'll find this, right? This is the vacuum-packed rice, and if you touch it, it's as rigid as a piece of block. Or, however, if you tear down the back, it flows easily. So this is a transition in granular materials called jamming. And the reason causing this is because of the packing fraction difference. So if they are loosely packed, the particles can move freely against each other like fluid-like state. However, when you confine the stress at the boundaries, the particles will have to gain contacts with each other. So the movement against its neighbors is restricted due to the boundary conditions. So physicists have been studying this type of transition as a phase transition, and there is a phase diagram for this. All right. So what I'm trying to do is to take this concept and apply it as a wearable material for robotics that can change stiffness on demand. So, however, directly applying this has several problems. First of all, if you just use solid convex particles into a wearable equipment, it has very high density. Just imagine if you wear a bag of rice or sand on your body. Nobody wants to do that, right? So secondly, an important reason is that these convex particles only repulse against each other, which means if you push on it, it can be very stiff. However, if you stretch or bend it, due to these tensile deformations that do not perform so well, okay? So it cannot stiffen so much in terms of stretching or bending. So, however, we know that when we use it as wearables, a lot of the human joints consist of bending or stretching deformation, right? Not just compression. So this is not going to work so well for wearables. So what I'm trying to do here is to come up with a design of this granular lattices so that is more wearable. So the idea is like this. So we take this particle that is hollow, so it consists of an architectured body with a hollow volume inside, and we link these particles using a topological interlocking strategy, and then we repeat this to be a two-dimensional lattice, right? So due to the fact that these particles are interlocking, or overhanging against each other. So we have to use a different strategy to manufacture it. So in here, we use a 3D printing technology called the selective laser sintering. So it's based on a powder bed. So we can create these overhanging parts without extra support. So it can be printed out in one piece. So that's how it looks like after it's printed out, right? So due to its hollow volume inside, its density is very low, only 0.18 grams per centimeter cube. And you can see that when we stretch it, it has a very high tensile stiffness. Okay, so I would say this is a different strategy of creating a structure that is flexible, right? So for flexible, typically you think we use soft materials, or we make a very thin, make stiff materials very thin, and it becomes flexible. However, in here we are using rigid particles, and they are not thin on the walls. However, using this topological linking strategy, we can create a very soft material. So actually, I brought one piece of the sample here. You can pass it around. Thanks. Okay, so the next thing that we want to do is try to trigger the transition of jamming, right? So if we enclose it into a soft elastic bag and confine the stress at the boundaries, the particles will intrinsically jam together, and these materials will become much stiffer. So due to the pneumatic actuation is very fast, within 0.1 second, you can see that in the stiff state, it is able to hold a weight of several kilograms, while in the soft state is just like a piece of fabric. Okay, so this is pneumatically actuated. So we characterize the mechanical performance. So we treat it as an elastic plate, and we change the confining pressure on the boundaries, and we measured the bending stiffness, basically using a 3-point bending test. You can see that when pressure goes higher, the stiffness, basically the linear regime at the beginning, will increase. So we can characterize the modulus versus the negative pressure that is applied. You can see that it can increases by 20 to 30 times in terms of stiffness. In comparison, I'm also showing in the bottom here a loose particle that is not interlocked together, but just dumped into the bag. You can see that the difference is large. So, since we have a lot of experts in mechanics here, I just talk a little about the mechanics behind it. Okay, so when we have these particles, we can consider it as a rigid bodies with contacts on the side. So basically, it's a rigid structure, and there is a criterion to characterize whether a structure is rigid or soft. Basically, by looking at how many degrees of freedom versus how many restrictions in it, right? So if there is let's say Z number of contacts, if it is below a critical number, it is soft because there is more degrees of freedom versus a constraint. While it is above this number, it becomes rigid. So that is the basic idea behind it. And at this transition, there is a scaling behavior due to the phase transition. So in our discrete element simulations, that we can find that the mechanical properties, basically the bending modulus versus from our calculations, we can find what is the average contact number per particle, and we can see a nice scaling behavior here, right? So that is basically to connect the micro scale mechanical properties versus the micro scale geometric features. So we can use this as a designing feature to design the mechanical properties on the vertical scale. So, and later on, we have tried the different particles in our discrete element simulations. You can see that the different particles can be designed that interlock together. You can see that all of them collapse very well in this scaling law, and we can use that as a designing strategy to design the geometry of the particles for desired mechanical performance. Okay, so, and we have printed out some of the examples. So just note a special example of the chainmail pieces that is already discovered like 1,000 years ago in the medieval times. But basically here we are creating a more advanced modern version of the chainmail armor, right? So for the protection part, So we have done some impact protection on these fabrics. So in the left side, in the soft state, you can see that we are dropping a metallic sphere here, and it's dropping down, and then we turn it to be stiffer. You can see that the material becomes stiffer. In the right-hand side, we have the highest pressure, so it's the stiffest. So basically, we can change this material in these different states on demand by controlling the pressure inside. Okay, so another feature is that since in the soft state, we can almost change it to a lot of different shapes, and then we can freeze it into that shape by applying the confining pressure. So it can be reconfigurable in terms of its own geometry and still be load bearing. Okay. So other examples, we have printed out it in metal, both in alloys and aluminum. So this metal will give us higher stiffness and strength. So it can be used for some even defense or protective applications such as anti-piercing armor. Scalability, due to the fact of the jamming is a physical concept, so it works at a lot of large range of different scales. So in the lower scale, basically on human scale, we can think of using it as a assistive part of the body to create some type of soft exoskeleton devices. On even larger scale, we can create some reconfigurable architectures or structures. So I'm mostly going to be focusing on this lower scale part later. All right. So one of the applications that we have made with it is to create a soft gripper. So due to the fact that this fabrics have variable stiffness, so the idea of the gripper is that we build this into the palm or the hand of the gripper, so that when it actuates, it conforms to the body, but with very little pushing force. However, after it engages, it can stiffen itself. So even the heavy objects can be picked up. So this applies a very gentle force on delicate objects while still being able to pick up heavy items due to the stiffening effect. All right. So here are a few examples of the videos that we created on the gripping of very soft. On the bottom left is a hydrogel sphere, and we are able to pick it up without damaging it. So if we compare it with other work, so the ratio between the gripping to pinch force, basically the horizontal force we apply to the object versus how much weight we can grip, is very high compared to others. Okay. So next is to the topic about wearables. What are we going to do with it, right? So one of the main direction that we are trying to push now is to create portable, affordable healthcare devices, especially assistive devices. So a few user cases, for example, one of them is on neurological and musculoskeletal diseases. So for example, for Parkinson's disease, the patients typically
this disease or
will have tremor, right?
Muscle rigidity and tremors at rest.
So you can see that the hand is constantly shaking, even during their eating or drinking of water, right? So that causes a lot of problems for them. And other examples, for example, on the lower limb, we have this osteoarthritis. So because of there is too much load on the knee, some aging population will feel a lot of pain on their knees due to the heavy load. So existing assistive devices are including this several parts, but you can see that most of them still consist of very rigid parts, and there are problems with this assistive devices or exoskeletons nowadays. So they're not very comfortable to wear due to the rigid components. They're not comfortable to the human body, heavy and bulky. And also one important reason is that they're expensive, right? So even though exoskeletons have existed for a long time, we do not see many of them in patients' homes. All right. So one of the idea that we created using this smart fabric is to create an assistive device for Parkinson's patients. And this is an exoskeleton on the wrist or on the arm. So the basic idea is that we have created this wrist brace using this smart fabric, and we control it with a miniature pump that is mounted on the patient's waist and connected with an air tube, right? So by changing the pressure inside, basically we're changing the stiffness of a damper, right? So when the patients do not have tremor detected, this can become soft for them to move easily. However, when they need to damp the tremor using this device, it can be activated to reduce the tremor amplitude to basically suppress the tremor and assist for their daily motions. So here is the control loop for the device that is developed and some features of it. So one of the advantages is that the variable stiffness unit, due to the lightweight of the fabric, it can be only like 277 grams, including the pump. Also, the whole weight on the body is around 500 grams because we can find very small pumps. And also the total cost is small. So that's quite competitive versus rigid exoskeletons. So some characterization on the tremor suppression efficiency, right? So on the left top here, we are showing basically how much force this device can provide versus the muscle force provided by our humans. So basically the shaded region is a muscle force, while these colored lines are this damping force provided by the device. So you can see in most of the areas at higher pressures, it is able to efficiently suppress the muscle force, basically to damp the tremor. So on the bottom, we can show that when we mount it on a subject, you can see that in a few seconds, the tremor amplitude can be reduced a lot in all the three directions of the wrist motion. So that on the top right, we are showing some videos in the soft state. The subject can freely move his hand, while in the stiff state, you can see that the device is actuated. So basically, this acts as a rigid elastic beam there. So the tremor suppression efficiency can go up to about 80% of amplitude, right? So other things that we are trying to do for now is targeting other parts of the body. For example, if we put it as a jacket on the back, it can stiffen the back to potentially prevent triple fall for elder people. And also we are targeting the lower joint as well to create a knee exoskeleton to reduce the pain for osteoarthritis patients by carrying some part of the weight. Okay, so on the bottom here, I'm showing some advantage of the technology. So that is what we're currently actively working on. So I would like to conclude by showing this vision of us, what do we want to do in the end, right? So as you have all talked about today, we have created a lot of flexible sensors on the body to collect all kinds of various data on humans to monitor the body status. On the other side, what I'm trying to do is to do the other direction, right? We are creating materials and structures that can interact with the humans to provide assistance or protection on demand. So in principle, we are also going to use this variable stiffness by adding actuation, by adding soft actuators on the body to provide a soft exosuit system. So in the end, we are trying to close the loop here. So basically using this sensing data, we are able to use the body status to control the exoskeleton stiffening and actuation. And we can use all kinds of advanced algorithms here using AI and machine learning and so on. And on the other side, the exoskeleton by embedded flexible sensors is able to provide feedback and assist body functions. So in the end, we are trying to close the loop here. Okay, so and with that, I would like to make the acknowledgement. So I'm running a group called Robotic Materials Lab at NTU-MAE, and we have some collaborators that is listed here. Okay, thank you.
Welcome the questions.
Yeah, please.
Yeah, very interesting idea.
Thanks.
My question is, you have compared several macrostructure, cross-link structure.
Right.
have you done it by optimization? I'm
Very
not
good.
sure this is the best design.
Okay, very good question. So first of all, by computing this via discrete elements, simulation requires a lot of computational power because we have like hundreds of thousands of particles and they are irregular shape, right? So we have computed these few examples, but by doing optimization, because it's a discrete system, we do not have a constitutive relation between the geometry versus the mechanical properties. So the only way that we can think of is by running large data, by creating a large data set and do perhaps machine learning to do optimization. And that takes a lot of computational power. Yes, we thought about doing that, but the computational power required for it is going to be very large.
Okay.
Yeah.
Thank you. Very nice work.
Yeah.
Yeah, can I have? Okay, my question pretty much similar.
Okay.
Yeah, so you know in the mechanics community, there's a large community called granular material.
Yes.
Jamming and things.
Yeah.
Can your system be kind of a use theory developing the granular material?
Okay.
They talk about shapes, particle shapes.
Yes, that do. I think that do study this, but I do not find many works studying this like type of hollow or non-convex shape.
Yeah,
for example, they are studying something like a rod or ellipsoid that have been studied, but I do not find a like theory basically for this type of shapes. Yeah,
there's no existing.
Yeah, I do not find that. Yeah.
Thank you, Professor Wang. Very interesting and wonderful talk. So regarding actually this figure, it seems that different lattice structures give different the bending modulus.
Yeah.
Yeah. I'm just curious, is it possible? The first question is possible that we can fabricate a whole structure using different lattice structures. Some regions using maybe different lattice structures. So do you have
I think that can be done because the manufacturing technology, as long as we have the 3D file, we can print it in one piece. So you can have different particles or different geometries in different places for the desired properties that you want. For example, you want some parts to be stiffer compared to the other, then you can change the geometry of that part. That can be done. Yeah.
Yeah. And the question is about maybe the property of the lattice structure itself. I mean, during the withstanding or loading during withstand the load scenarios, I mean, will the lattice structure or the material will be fracture or rupture? And I mean, what are the strengths of the lattice structure?
Okay, so the lattice structure here in the white part, or the one that you just showed around, is a nylon plastic PA12. So it's a well-used material for SLS printing. So the fracture strength is quite high. And in our loading part, so what actually happens is that before the particle breaks, it already dislocates against each other. So the main deformation here is basically the dislocation of one particle against the other rather than the fracture of the particle itself.
Okay.
Yeah, so the stress applied is not enough to fracture the particle.
Okay, yeah. Thank you. And actually, I have a following question regarding this part. So a question is, if is this some flaws or some during the fracture at some specific regions, will it have some strong effect or influence on the whole property?
Oh, in one structure. So in terms of bending, I think yes. Basically, you have basically it means that you have a soft area. So the most of the deformation will go focused on the weaker part. Yeah. Similar to like continuum materials. Yes.
Okay. Yeah. Thank you. Thank you.
No, thank you.
Yeah, so let's move to the next speaker. Due to some conflict, so now the third speaker will move to the second speak by Professor Yihui Zhang. So Yihui is a professor of engineering mechanics in Tsinghua University. Yeah, his current research interest including the mechanically guided 2D assembly, soft architecture, soft architect material, and mechatronics of flexible structures. He published many significant papers in Science Literature and Literature sister journals. He also received many honors and awards. Now let's welcome Professor Zhang for his speech.
Thank you, Professor Zheng, for a very nice introduction. Firstly, I would like to take this chance to thank Professor Xiaodong Chen, Professor Xue Feng, and Professor City Lim for putting together this wonderful symposium. So it's my great honor to have this opportunity to introduce the research of my group on mechanics-guided 3D assembly of electronic devices and microsystems. My talk includes 5 parts. So starting with the introduction to the research background and the motivation, I will give a brief introduction of the mechanics-guided 3D assembly method, and then talk about the challenges faced in the accurate 3D programming based on this method. And finally, and after that, I will introduce the microlattice design we recently developed for the inverse design of curved surfaces. And finally, I will talk about some representative applications enabled by this design method. Okay, nowadays, electronic devices have already spread into almost every corner of our daily life. So for quite a long time, since 1960s, the development of electronic device, integrated electronics follows the prediction of Moore's law quite well. But during the last 10 years, you can see a clear gap, a clear lag between the development of integrated electronics and the prediction of Moore's law. So you can see a clear gap here between the colored curve and the gray curve. This is mainly because the well-established microfabrication technologies have already approached their physical limits. Since the third dimension can bring brand new opportunities, the 3D microelectronic devices have already become an important research direction in the era of post-Moore's law. So when comparing to the 2D designs, the 3D flexible microelectronic devices can provide broader design spaces, better mechanical and electronic performances, and even brand new device functions. Therefore, the 3D flexible microelectronic devices have important applications in bio-integrated electronics, microrobots, tissue engineering, and also healthcare, with the potential to upgrade the device form. Then let's look at the geometrical and the physical features of 3D flexible microelectronic devices. These flexible devices usually have very small scales and also complex 3D shapes, such as curvy ribbons, multi-layer surfaces, and even network geometries. Due to the flexible and the finite deformation characteristics, these flexible devices also exhibit strong nonlinear mechanical responses. And also, additionally, these devices usually contain multiple different functional components, such as the sensing, actuation, wireless communication, and also data acquisition modules. And because of these features, it becomes very challenging to achieve a customized design and fabrication of 3D flexible microelectronic devices. In particular, the well-established microfabrication techniques in the semiconductor industries are mainly developed for planar inorganic devices, and they do not work directly for 3D inorganic electronics. While the recently developed 3D techniques can achieve the fabrication of certain 3D microelectronic devices with some simple geometries, the fabrication of complexly shaped inorganic devices is still very challenging. So the graph on the right summarizes some representative 3D fabrication approaches for inorganic electronics developed in the last few years. Of course, it's worth mentioning that Professor Gao and Professor Xiaodong Chen have developed a very creative pinning-induced 3D assembly method. as presented in Professor Gao's lecture this morning. But in this graph, we only summarize the representative approaches based on the stacked 3D integration schemes, the residual stress-induced assembly, capillary force-driven assembly, as well as the Fox ion beam-induced assembly. And from this set of comparison, you can see that it's still quite challenging to fabricate complexly shaped 3D inorganic electronics. To address this challenge, we started relevant studies from 2012, and now we have established an approach distinct from all of the previous ones. The key idea is to go one step further beyond the traditional 2D fabrication by using compressive buckling to trigger the easily patterned 2D microfilms into well-controlled 3D architectures. After devising this approach, a key aspect involves the exploration of accessible 3D geometries to this approach. So in this context, we have devised a set of design concepts involving the designs of 2D precursor patterns, deformable substrate, as well as reconfiguration strategies. Another fundamental question is how can we develop quantitative mechanics models that can serve as the theoretic basis of the 3D inverse design? So this is also to answer the question of how to map the target 3D configuration onto initial 2D pattern. And in addition to developing the approach itself, we are also interested in exploring some unique applications enabled by this approach. Well, I will use a very simple example to illustrate the process of this mechanics-guided 3D assembly approach. So firstly, we use a very soft material, such as the elastomer, to serve as the assembly platform, and we can apply a uniaxial pre-stretch to this platform. In the meanwhile, we can use the microfabrication technique to create arbitrarily shaped 2D patterns. And in this example, we use a serpentine silicon film as an example. And then we integrate the pattern 2D thin film with the pre-stretched elastomer substrate. And by using techniques of surface chemistry, we can create strong covalent bonding selectively only at the rest sites. And the other places, the blue color, are simply weak interface and can pop up easily from the substrate if you release the pre-string in the elastomer. So this idea has been validated systematically by experiments. And this is an SEM image for the single crystal silicon, the most important material in the current semiconductor industries. As you can see here, the 2D serpentine pop up from the surface into 3D conical coil, and the SEM image agrees well with our prediction. Here, I would like to emphasize that the single crystal silicon is a very brittle material and can undergo just 2% strain before its fracture. So the mechanics design plays a very important role in the design to optimize the processing parameters. So in short, our idea is to go one step further beyond the well-established 2D fabrication by introducing structured design concepts to enable well-controlled 2D to 3D transformation. Because the microfabrication can do mass production, our 3D assembly approach can also assemble thousands of mass structures simultaneously. So our first paper in this area was luckily selected as the cover of Science and also highlighted by Nature and Science. A powerful aspect of this mechanics-guided 3D assembly approach is the applicable range of material types. So excluding the single crystal silicon, our approach also works very well for other semiconductor materials, metals, polymers, plastics, piezoelectric materials, and even ceramics, such as PZT. And also the flexible printed circuit board and integrated circuits can also be assembled into desired 3D configuration based on this mechanics-guided approach. Another powerful aspect is the applicable range of length scales. Unlike many of the other approaches, this mechanics-guided approach applies perfectly well over length scales from sub-micrometer scale up to meter scale. So in order to provide some intuitional impressions, we compare our assembled structures with some objects in our real, daily life. As you can see here, the sub-micron scale 3D structure has a comparable dimension to blood cells. Adjacent to the microscale 3D structure sits a human hair. And for millimeter and centimeter scale 3D structure, we use a coin and a pen as a reference respectively. And the rightmost panel shows the largest structure we have achieved, which is compiled, which has a comparable dimension to human body. So after our group and our collaborators published a few papers in this area, our works were quickly noticed by the editors of Nature Reviews materials and advanced materials, and they invited us to write 2 review papers, which were both published as cover articles. So if you look at the image, the tiger here, you can actually, we just use a very simple kirigami design originated from Asian, China, and Japan to create a 2D kirigami pattern at microscale. And we just use the compressive forces to trigger its pop-up into 3D. So this tiger has the microscale dimension. Because of the powerful capabilities of this 3D assembly approach, it can be used to develop new kinds of flexible electronic devices and functional systems, such as the 4D antenna whose radiation pattern can be adjusted on demand, the 3D bio-integrated electronics that can adapt to different curved surfaces of organs, the 3D microrobots with different locomotion modes, as well as 3D MEMS with different spatial vibration modes. Due to the time limit, I will just select 2 examples to illustrate. So the first example is a 3D bio-inspired electronic microflyer. Many wind dispersed seeds, such as Tristana tear seed, shows a rotational fall behavior and has a very low terminal velocity during the falling. So inspired by this behavior, we studied the aerodynamic behavior, and we used our assembly approach to create a man-made 3D microflyer with a similar 3D shape. As you can see here, our man-made 3D microflyer also shows a rotational fall behavior and shows a very stable aerodynamic behavior. And if you look at this graph, you can see that the terminal velocity of our 3D microflyer is very small. This one corresponds to the smallest microflyer we have fabricated in experiments, and the terminal velocity is just 1/8 of the slope. So it's really very, very, very slow during the falling. And then if we integrate some electronic components onto this man-made flyer, it can be used to monitor the distribution of air pollutant in the 3D space. The second example is a 3D soft climbing microrobot. So in this example, we use our 3D assembly approach to develop a class of liquid crystal elastomer-based microactuator. And this kind of microactuator can show very large actuation deformations at a very millimeter scale. And based on this kind of microactuator, we have developed this kind of 3D climbing microrobot. In particular, the conformable foot pad can conform to different curved surfaces, such as this planar surface, the outer and the inner surface of the tube, and also on the sphere and the wavy surfaces with different wavelengths. And also inspired by the locomotion modes of Hydra, we can use our microrobot to combine the 2 different locomotion gates of stepping and flipping. And then if you integrate camera onto this microrobot, it can achieve the transition between 2 different wall surfaces to achieve a detection in a narrow space. So according to the above introduction, you can see that this kind of 3D assembly approach actually corresponds to a process of post-buckling deformations. So it's very important to develop a theoretical model to serve as the basis of the device design. And for this purpose, we need to first solve the forward problem of predicting nonlinear buckling deformations for prescribed 2D precursors. And in this context, we have developed a double perturbation method, which can predict the post-buckling deformations for simple 2D curved beams. So if you look at the results on the bottom, you can see that the analytical prediction of the 3D deformed shapes agree well with the experimental results and the results of finite element analysis. Then after solving the simple, the forward problem and gaining some insights into the 2D, 3D relationship, we eventually want to solve the problem of inverse design. That is, how do we determine the initial 2D precursor pattern, the bonding size distribution, and the pre-strain level for a target 3D configuration. So for some simple 3D curves like 3D ribbon structures, we can use the analysis of differential geometry to convert the problem into a type of optimization problem. And then by introducing the generic algorithm, we can solve the problem based on the topological optimization algorithms. So the graph on the middle and the right shows some results for simple 3D ribbon structures. And here are some more examples. If you look at the column on the left, the first column, the table on the left, the column on the first column shows the design target. The second and the third column correspond to the results of finite elements simulations for the optimized 3D configuration and our optical images of experiments. And the last column corresponds to the optimized 2D precursor pattern. If you look at the results on the right, you can see that we can extract the key sketches of mantis to serve as our design target. And then based on our optimization algorithm, we can determine the initial 2D pattern as shown here. And this cartoon shows the dynamic formation process of this mantis. This method only applies for 3D ribbons or 3D curves. The inverse design of curvy surfaces is more challenging. We have worked on this problem for around 6 years. And one of the solutions we proposed is to exploit the varying cyclists to achieve customized curvature distribution. So for a straight ribbon in the simply supported condition, we can use the finite deformation theory to derive the relationship between the curvature distribution and the cyclist distribution. And according to this analytical solution, we can assemble this kind of arc-shaped ribbon structure, this kind of asymmetric ribbon structure based on this kind of cyclist distribution and this kind of cyclist distribution. And this method can be extended to X-symmetric curvy surfaces if we discretize the target 3D surface into a set of interconnected ribbon components. So here are two examples, including a hemisphere and a drum surface. However, technically, it's very challenging to precisely tailor the cyclist distribution of 2D thin films, especially for electronic materials. Based on our previous work, by using the advanced grayscale photolithography, the cyclist resolution we can achieve is around 1 micron. And the smallest smallest meso structure we have achieved in experiments has a literal size of around 4 millimeters. And at this scale, you can already see a large distortion of the assembled 3D surface from the ideal design target. So actually, the difficulties in the programming include the high nonlinearity, bending and twisting coupled deformation, and the high machining accuracy. So it's still very challenging to program complex asymmetric 3D surfaces like those one on the bottom. So to address this challenge of inverse design, when we turn to nature to find answers, we note that many cellular microstructures laterally form in many different fruits and leaves, such as these different fruits and leaves. For example, the non-uniformly distributed cellular structures form the closed cage shape in the Philadelphia and the vulgaris to provide a large support for the fruits inside the cage. And inspired by this cellular biological surface, we introduced the microlattice design as a route to achieve desired stiffness distribution in the space, thereby allowing the transformation of the microlattice pattern into programmed 3D curved surfaces. And by using this kind of microlattice design, we can bypass the technical challenges in the gradient thickness control. Then let's look at the capability of this microlattice design. So we first use two flower surfaces as examples, including this kind of stramonium and the jasminoids. So these two flower surfaces both have certain kind of chirality. And based on our microlattice design, it can achieve a kind of discretized mediated deformation. And then by tuning the local porosity distribution, we can achieve different chirality in the 3D surface. We can also reproduce the chirality of the real flower surface. Then we want to develop a rational design method of the bio-inspired microlattice strategy. So here we use an octopus surface to serve as an example. So we firstly, we can generate this kind of discretized surface with a set of developable ribbon components. And then, according to our theoretical analysis, we can derive the stiffness distribution and the porosity distribution according to the desired curvature distribution. And then, with this information, we can generate this kind of 2D precursor design with the triangular lattice pattern. And then we can testify the design based on our finite element analysis and the experimental results. And this graph shows the comparison of the profile of the octopus head. So based on this method, if we can discretize the target surface into a set of pure bending ribbons, we can use our theoretical model to give the relationship between the curvature distribution and the porosity distribution. So based on this method, we have achieved the inverse design of more than 10 X-symmetric mesosurfaces. So here are a few examples, including the surface of hemisphere, the volcano-like surface, palace-like surface, an entire field, and a vase-like surface. The videos on the right shows the dynamic formation process for this hemisphere and the volcano-like 3D surface. This is the finite element analysis. This is the experimental results. So you can see good agreements between the experiments and the finite element analysis. And based on this microlattice design, we can also reconstruct the 3D biological surfaces at millimeter scale, such as the blueberry flower with 5-fold rotational symmetry, the Philadelphia with 2 different 3D layers, and also the flower pot and the abdominal region surface of the garden spider. So for all of those examples, we can find good agreements between our inverse design and our design target. Because this kind of microlattice design is fully compatible with the microfabrication approaches, so we can use this. This method works very well for a broad range of material types over a wide range of length scales. The literal size of the assembled structure range from centimeter scale down to around 200 micrometers, which is more than 20 times, around 20 times smaller than the strategy based on the thickness control. In some cases, if the target surface cannot be discretized into a set of pure bending ribbons, then we need to develop a more generic algorithm for the inverse design. And for this purpose, we have introduced the machine learning algorithm into our inverse design. And in particular, we exploited a point cloud-based method to derive the 2D coordinate and their porosity value for the target surface. So the data set was generated by massive calculations based on finite element analysis. And here is an example of the seashell-like 3D surface. This is the experimental result based on our inverse design, and this is our design target. So here are two more examples based on this machine learning-based inverse design, including a palmetto-like mesosurface and an ant-like mesosurface. In particular, for this ant-like mesosurface, we use a cutting strategy inspired by the CT scanning to discretize the ant surface into a set of ribbon components. And then we can solve the inverse design based on our machine learning model. As you can see on the right bottom images, we can use around 4,000 micro triangles and around 8,000 micro ribbons to reproduce the ant surface very well. Okay, this kind of microlattice design allows us to reproduce the 3D shapes of different tissues and organs. So we can create electronic devices to conform to different surfaces of biological tissues and organs. And here is an example of a breathable hemispherical electronic cardiac device. So based on the geometry and dimension of the apex, we can create this kind of 3D surface with a comparable dimension. And because this kind of 3D device is stretchable and adaptive, so it can be used to adaptively wrap around the apex of the tissue of the organ. And also it can achieve the sensing, a high singular to noise ratio sensing of the temperature distribution, as well as achieve the ablation through the integrated microheater. The second example is Stingray-inspired biomodal actuator. So here we can use our microlattice design to create a device that can imitate the dynamic characteristics of some living organisms. So here in this device, we can arrange circuits on top of this 3D structure. And by using this circuit, when we flow some current on the device, it can create the Lorentz force when the device is placed in a magnetic field. And based on this dynamically alternating Lorentz force, we can excite different vibrational modes of this actuator by adjusting the frequency. So these two different modes have a distinct vibrational frequency. And the last example is a retina-inspired 3D electronic cell scaffold. So in this example, we have created a spherical cap-shaped 3D cell gripper. And this kind of device can not only provide a 3D support to grow RPE cells on this scaffold, but also provide sensing capabilities through the integrated electrodes. So this device can offer monitoring capability of the growth and the apoptosis of the RPE cells through the impedance measurements. And finally, I would like to give a short summary of this talk. We have developed a mechanics-guided 3D assembly methods for 3D microelectronics, and also to provide a theoretic basis of this 3D assembly, we have developed bio-inspired microlattice designs with strong shape programming capabilities. And finally, we have demonstrated a set of unique applications. And finally, I would like to acknowledge my collaborators, including senior collaborators, Professor Yingguang Huang, Professor John Rogers, Professor Zheng Yan, Professor Shenlian Yao, and Professor Li Wen. And also, I would like to thank all the members of my research group. And finally, I would like to also thank the funding support. And with that, I would like to close and thanks for your attention. Thank you.
Yeah, so thank you. We're impressive talks. And in fact, the Professor Huang and Professor John Rogers just recently visited Singapore. Yeah, so I listened both seminar talks by them. Okay, yeah, let's open to questions.
Thank you very much. I have one question regarding the 2D to 3D strand releasing process. So I wonder if you have encountered the undesired adhesion between your 2D precursor and the substrate, and can you elaborate some strategies you find very helpful to reduce that? Yeah.
Yeah, very good question. Actually, the interface is a very important problem in this kind of approach. So during the assembly process, we need to ensure a very low interface energy at the weak interface and a strong interface at the bonding size to provide a robust support for the 3D structure. So during this process, on one hand, we need to develop mechanics model based on, for example, cohesive zone model to characterize the process to allow prediction of the interface delamination. On the other hand, you can play with the interface to reduce the interface energy at the weak interface of the thin film structure.
Thank you very much.
Professor, thank you for your talk. Can I ask, your method can produce non-symmetrical geometries? Like in nature, there are some symmetrical leaves and flowers, but many are non-symmetrical. So do you have any insights on that?
Yeah, very good question. Very good question. Actually, for many of the living organisms and biological objects, they have asymmetric geometries. So here is an example with a certain degree of asymmetry. And by introducing the machine learning algorithm, we can actually cut divide the target surface into a set of different ribbon components. And for each ribbon components, we can use this machine learning algorithm to solve the problem systematically. So by using this kind of discretization idea, you can create your target surface approximately. Yeah.
Okay, thank you.
Yeah, I'm very interested on this part as well. So because in my research, do a lot of so-called AI-based inverse design. So just wonder, when you say inverse design here, means basically once you inverse the problems, you can have many solutions or only have one unique solutions.
Very good question. Actually, for the forward problem, it's a kind of post-buckling deformation problem. So for a given 2D precursor, if you apply the forces to the 3D structure, the final 3D configuration is single and can be solved directly. But for the inverse design, for a given 3D surface, we want to find the 2D pattern that can deform into this 3D configuration. And this kind of inverse problem have multiple solutions. So does this answer your question?
Yes, but in the way of you put some regulation terms and such that you can reach your desired 2D pattern, or actually you don't care what's so-called the final 2D pattern you are looking for.
there are different options you can choose. So in this work, we propose the bio-inspired microlattice design to simplify the inverse design problem. And based on this kind of algorithm, the design target is just the 3D coordinates based on the point cloud representation. And the solution is just the 2D coordinates and the porosity distribution. So this kind of algorithm is easy to solve based on our developed algorithm.
Okay, thank you. Yeah.
Thanks again.
Now let's go to the third speaker in this session by Professor Benjamin T. from NUS. So Professor Benjamin T. is in the Material Science and Engineering Department at NUS. So he is Vice Dean for College of Design and Engineering, as well as Associate Vice Dean for NUS Enterprise. He leads the Sensor AI Lab to develop technology on cutting edge of material science, mechanics, electronics, and biology. So he obtained his PhD at Stanford University. He's MIT TR certified innovator, and he was featured with many media with various awards. So let's welcome Jim gave his talk.
Okay.
All right, testing. Hi, good afternoon. Thank you, the organizers, and thank you, Chair, for the nice introduction. I'm Benjamin T. from the National University of Singapore. In fact, I just sort of delivered a similar talk, so hopefully you've not already heard this talk in the last Friday. But if you are, hopefully you have more questions to ask this time. So the hope in my group is that maybe at some point, as we develop all these very nice soft materials integration with new forms, V factors, and also new capabilities, they can maybe give us what I would like to think of as a digital doctor in your hands. Whether there's a possibility, I think we are very fast moving towards that. Okay, right. So for those who are, first time to Singapore, even if you're not the first time, please visit the sites around, get a chance to enjoy some of the nice food around the Marina Bay Sands. This is actually a very nice photo. If you can, try to take this photo at night and send it to me. I will use it for my future talks. So I run the Sensors.ai labs, and it's actually called the dot because Singapore is a little red dot in many countries. So actually, it's sort of also saying that I'm located in Singapore, and we hope that just like Singapore is an intersection of ideas and technology, I hope that my lab can be the intersection for sensor data and artificial intelligence. This was 5+ years ago, and that was before this ChatGPT and all that came out, right? So I think that we are definitely on a major trend, mega trend of utilizing AI, but importantly, we need to provide them with data, and that's where sensors come in. So I developed in 4 large areas: materials, self-healing devices to tackle some of the challenges in sustainability, learning from our own central nervous system and the brain, as well as stretchable electronics. So I'm very interested to develop, what I call the best wearable technology you probably have. So this is a blindfolded person, right? He's doing a completely amazing action of taking a very sharp knife and slicing vegetables. Don't try this at home. If you get injured, I'm not going to pay for your hospital bills. But the idea is this, right? You don't need vision to actually navigate your environment. Importantly, the person is able to know and tell what's the shape, what's the hardness, what's the material capabilities, properties of the objects that he's in contact with, right? So it's pretty amazing. And besides all these fancy demonstrations of human skin capability without vision, I think importantly, physicians like to use their sense of touch in many ways. In the Western world, they use the sense of touch to check for, maybe stiffer tissues that might indicate signs of disease like cancer. But much more intrigued by the eastern part of the world, where for thousands of years, through refinement of knowledge transfer between a physician and the apprentice, they're able to pass down, and a lot of training, the ability to measure blood flow, other types of health parameters, almost acting like one part of a diagnostic tool, right, for Chinese physicians or TCM doctors. Who has not seen a TCM doctor? Okay, I'm pretty sure I'm in good company. Everybody has seen a TCM. They're pretty amazing, and they're able to tell a lot of things like, which organ is not functioning and so on. So the question I was interested in is, well, can we actually create the sense of touch like human skin and put it on machines that then give us the doctor's touch? Fortunately, I was also almost at the right time. There was this convergence or start of the technology where they started to think of new form factors for developing skin-like devices. So I started my career in Zedang's group at Stanford by learning really from some of the early pioneering work by Takao Someya, John Rogers, and many, many others. And many of you here, I've also read many of your papers. It's a delight to be able to meet some of you here in person. I think there's a lot more that we can do in terms of sharing new ideas in material science and technology and how we can create skin-like devices. So in my group, we think of skin as a human sense as a computer, but it's a sensing computer because it has many different cells that are very specialized and they sense different things around the environment, right? From pain to temperature to vibrations and to force. But really the skin is part of a larger system between materials that are engineered by biology to be very selective to the stimuli, but also is part of a system that transmits the data in an extremely efficient manner through your central nervous system to your brain, which then learns and perform actions. I think this is an important point. I think that as we develop technologies, even at a material science level, it's good to see how it can fit into the entire system architecture. So in my group, we look at 4 different areas of moving electronic skins from the research to further them into practical use. I think there are 4 important vectors that we can look at: scaling the size or density of the sensor devices, making them more reliable. As we make more and more of these very cool technology, hopefully they can self-repair so we don't have to throw them away so quickly and pollute the environment. Importantly, give them the intelligence to analyze the data. So we have done we have published a few I would say, minor, I would say from a Hubble point of view, really minor advances, I think, in the field of soft materials and electronic architecture. So if you're interested, feel free to read up some of these work since I started my group. Today I have time to talk about the science robotics, a bit of the science robotics work, some recent work that we published in machine learning and sensors. When I started my group, I was trying to solve a problem that I think all soft material experts would know, which is viscoelasticity. When you have a very soft material, they tend to be viscoelastic. So this means that it has some time-dependent strain recovery properties, and these affect subsequent measurements, right, when collecting data. In fact, the softer you are, and this is Young's modulus, the softer you are, you tend to have higher viscoelasticity, unless you engineer them to be very, specific with some techniques. The human skin, for example, is about 1 megapascals. A lot of the materials they're used to, like metals, are in a gigapascal range. So we thought, well, can we make soft materials less viscoelastic and be useful as a generating mechanical data? So the approach we took was more hybrid. So we take a soft material, and we knew very early on that structures make materials more sensitive. So we have we have sort of developed a lot of history in making microstructured pyramids. So we started with pyramids. It can be potentially other kinds of shapes. But anyway, pyramids are fairly easy to make. Many of you have probably made this in your lab. What we did was, well, let's put a piece of metal on top, a thin film deposited on top, and then we see what happens when we compress it. Now, most metal films are used in strain sensing, which is sensing in the plane of the material in the direction of stretch. What we are interested in is to measure force in perpendicular to to the material substrate, right? So if you compress on this structure, you crack the films. That's pretty obvious. And so we thought, okay, maybe we can use it. But the problem is that when you do that, as you crack the film, these cracks are formed fairly randomly, and this is a sequential SEM. I must thank my postdoc who did a lot of work finding the exact same pyramid to look at in the SEM. Most of you probably have done SEM. Very challenging, but anyway, they managed to figure it out and always take the same micro pyramid. Anyway, so you can see it's definitely very random, and it's not so useful as a sensor, a compressive sensor. So I have a student who did not give up, and I think hopefully if you are a student or early in your career, if you have some idea, don't give up until you've tried for at least 100 times. So this student probably tried a few hundred times, but he finally landed on one idea, which is, well, let's see if we can, during the cracking process, distribute the load so that we can create the cracks in a more controlled manner. And this led to the creation of this what I call soft interface layer, where we actually allow the loads to be distributed and it's cracking right along the vertex of the pyramid. And then this actually then was a lot. Wei Dong is now in China as a professor, and Ai Zheng is in, I believe, he's a big Chinese tech company. And as you compress this film, when the cracks are regular, you can actually measure the change in resistance, and so this allows you to then determine what's the force that you apply. Turns out that this strategy allows something that moves a random cracked structure or morphology to something that's fairly repeatable or sensitive in terms of modulating pressure and resistance, right? So it is also very sensitive and importantly, less hysteretic. So hysteresis is the strain-dependent property that I mentioned earlier. So because of that, you can have fairly good and accurate fast measurements of vibrations on your skin that where your arteries are quite close to each other, right? And quite close to the surface. And so here, for example, we have two sensors I think there's 6 sensors here, and we actually measure the vibrations across this surface. And then we can track almost in real time how the pulse kind of moves across this, and then it can tell you the speed of flow. Essentially, what we're doing is mimicking the Chinese doctor, right? When performing the pulse, using the fingers on your pulse. So this is one example of how materials is important. More importantly, we need to transmit the data almost like a skin, so we can have a lot of the data and process them in an efficient manner. So then we thought, okay, so we have maybe solved the sensor problem to some extent. We also need to mimic how data is transferred in your human body, right? You have probably, I would say, significant high resolution data, right? Fairly high. They are probably in the millisecond time scale of 1,000 times a second. Importantly, it's transmitted in parallel. So meaning at the same time through your nerve bundles to your brain. And your brains are actually then adapted to process this data through learning. So we say, well, it'd be impractical to have so many wires. You have 20,000 kilometers of wiring just for wiring up skin sensors. So we have to develop a architecture. I think it's important to transmit the data at a high speed over a single wire, but then still allow machine learning to be performed. So this is what we in the field they call neuromorphic, or learning from the brain. And so learning from the nervous system, we create the ACEs, or asynchronous coded electronic skin. This is useful for classifying materials, just like the first person I showed earlier when he grabbed different objects or different vegetables. So we can tell object curvature, importantly, less than 10 milliseconds. We can classify them with fairly simple algorithms. We don't even need to use deep learning, right, to get to very high accuracy. If the objects were the same shape, they can also be determined by the machine whether one is stiffer than the other, right? Again, less than 10 milliseconds. That's as good as real time. The fastest human can react probably in a range of 50 milliseconds, right? So we are probably 5 times faster than this gives your machine more time to react. So how is this useful? I think it's not useful in the way that we've demonstrated so far, but we have now managed to shrink the entire architecture onto a chip 2.5 mm by 2.5 mm. This chip can support 100 sensors. So if you're interested in, and you have resistive sensors, please send me an email. I'm happy to test your material with this chip. That's able to collect very high speed data of 100 sensors. But importantly, you can stack these chips up. So potentially you can have 1,000 or 10,000 of these chips, and they can all transmit data in a high speed fashion. So then it comes to the providing doctors touch. I have a very good student, Kalu, who has unfortunately her dad has glaucoma, which is can lead to blindness, right? And glaucoma is often called the silent thief of sight because you don't know that you have glaucoma. The pressure increases very slowly over time, and by the time you know it, you actually will have a high chance of turning blind if you did not catch it early. This is a big problem. Just in China, for example, there's several million sufferers from glaucoma, and many of them are aged. And as the society becomes older, this problem will increase. So Kalu actually then, sort of inspired by the sensor work, developed a glove that we can put on top of your eyeball and measure how hard or soft your eyeball is. Then these can give you an indication of pressure. For example, who has not played basketball? Everybody has played basketball, right? So you know when the ball is deflated, right? The pressure is low, it's soft. So there's the same idea, but of course there's a lot more complexity because your eye is a lot more complex. We've done a lot of modeling to prove that this indeed can be used to tell eye pressure. And then this was actually submitted to James Dyson, and I must say that the team is the first team in Singapore to win an award from him at the international level in 17 years of the award history. And they did something I could not imagine doing. They got Prime Minister, which is our PM Lee, and James Dyson, a billionaire, together in the same room, showing their work to him. So I think it's quite cool. And I hope that hopefully more of you will have the opportunity to think of ideas for some of your cool materials and devices. So we have then, using a hybrid approach, solve the hysteresis problem, right? So this, most of you are familiar, so I won't belabor the point, but basically this is not such a good sensor, right? In the forward and backward cycle, you want them to overlap. So annular fashion type of cracks maybe is one approach. But then we say that, well, you know, a big problem with many of these sensors is that there's two slopes, right? One very sensitive slope and one less sensitive slope. And they're usually not linear, right? If you look at the change in resistance, they're 10 times, more than 10 times change. So it's not so useful sometimes in certain circuits, electronic circuits. So you need to design circuits that are more, that compensates for that. So to put in a summary, basically what you want from an ideal sensor is a straight line, a slope straight line, as high slope as possible, but have little as much overlap between the forward and backward sweep, and then have less of these bimodal sloping values for their graph, right? So anyway, this is the best sensor you can probably get from the electrical engineer's point of view, okay? So definitely you can make a very sensitive sensor. From a material science point of view, it's cool. But from a system level, having linear type of outputs is actually really important, right? So here is just output versus pressure, but this applies generally to any kind of sensors. So I like to say that Singapore has good dim sum. I'm sure in China, and they also have very tasty food that actually uses an interesting material, and that is the lotus leaf. Lotus leaf. So this is an example of lotus leaf wrapped rice. If you haven't tried it, try it. It's very tasty. I like to think that I got the idea by eating this, but unfortunately I haven't. But we did wanted, or by my students wanted a nature paper. So I said, let's look at nature, right? So lotus leaf is an example of a natural material. We say, well, can we use it, right? And so they actually then take a lotus leaf, and they actually did something interesting. They put it underwater. And so I'll show you a video where if you have a lotus leaf, and you can try this if you have a lotus leaf, you put it underwater, there's something quite interesting that you can observe, right? And this is well known. You can actually trap air on the hydrophobic surface on both sides, right? So here you can see some of the whitish areas are actually air pockets. So as you dip a hydrophobic, super hydrophobic material, material of a surface, super hydrophobic, into water, you actually get air trapped. So we say, well, can we use this trapped air as a means to get a linear sensor, right? So this is a lotus leaf that is blasted with oxygen plasma. And you can see that because the structures are destroyed, the chemistry is destroyed, it doesn't have that shiny surface anymore, right? So we say, well, okay, let's take a lotus leaf and make it a pressure sensor. Now, the air is illustrated in this region here above the surface of the leaf. On top is a water layer, right? So as you put a leaf inside water, you trap some air. And we say, well, can we measure the change in this air pocket as the pressure increase and decrease, right? Turns out that you can. And you can measure the capacitance of this layer, right? If you coat it with some metal, and then you kind of complete the circuit and measure the capacitance with the water as the counter electrode, as the global electrode. So then you can measure some change in capacitance. But it's not linear, right? So how do we make it linear? And that was a project that I actually was, really, I would say, hesitant to start, because after I started it, it took us 3 years to then get into a paper. But what we did is that, well, inspired by this air layer, right, we can actually design the structures that are slightly different from a lotus leaf, but engineered to be able to trap air and have a surface that has very little hysteresis in the triple phase contact line. So it basically moves and it slides like a slippery, very slippery, frictionless surface. So by doing that, we actually transfer the device structure into something that has an ultra-linear slope, and importantly, underloading and loading cycles are the same, right? So then this would then make it maybe suitable for use as a pressure sensor that is very precise. So this technology we call electronic air actually has the highest linearity when used in an aqueous environment compared to all the aqueous sensors that measures pressure. So then we think, okay, again, what do we use it for, right? So in line with the title of the talk, was really about how can we sensorize tools to make doctors perform their surgeries better. One of the things, a well-known problem, is how can we make laparoscopic tools, which are non-invasive tools, more pressure sensitive and then convey their data. The challenge of putting pressure sensors, traditional pressure sensors, even flexible ones, is that it's very hard to integrate them into a metal that's very rigid and yet have the high precision needed for transferring the data. So we thought maybe we could use our technology, and basically what we tried that, and our technology allows simply a fluid field structure that then as it compresses, changes the fluid level and have the sensor outside of the body. Right? This serves a few purposes. First, it's a lot easier to integrate. It's a lot cheaper if you need to replace the sensor, right? And so this maybe gives a chance for surgery to actually have surgical tools to measure pressure. So here's the data. We measure different sensors. Here's 3 sensors. We can see the force profiles, and we can see when you lose contact if you don't grasp it strong enough. This is useful because a lot of injuries sometimes happen when you grasp it too strongly or you let the organs slip out. So I was very interested in touch. Turns out that vision helps us with 90% of the things we do in daily life, right? So I say, okay, maybe it's good to then also look at vision so that we can complement both touch and vision, right, for learning. Most of you would have some injuries before. Who has not had an injury? Okay, good. So if you have it, it bleeds, right? And okay, the cool part is your skin can self-repair. But the tough part is that sometimes it can leave scar or lead to infection. And very often you have to cover your wound with some kind of soft material like cotton that then makes it very hard to see, how the healing is progressing. And there's a lot of fluid that comes out to tell whether the wound is healing properly. So this is not, maybe you think, oh yeah, I'll get a cut, it recovers, no problem. But if you are older than me, most of you are probably here, right? You don't really care so much. But in 50 years, the chance of you having some kind of wound that don't heal, especially your diabetes, is very high. In fact, maybe 5 to 10 times higher, especially when you go to 80 years old. And with the technology that we're seeing today, I think most of the audience will agree we will most likely be able to live longer because we can detect diseases earlier. So I was quite inspired by John Rogers' work on sweat sensing, right? It's basically a microfluidic device that kind of measures sweat, analyze, and change color. Now, can we measure wound fluids? And that was the question. And so I have a very good team of students and postdocs that actually made a device that changes color from measuring wound fluid, right? So this technology we call petals because it looked like a flower, right? And basically, as the wound fluid gets onto this device, the color changes, and then with the advances in machine learning algorithms, right, we can measure the change in color in all kinds of lighting conditions and all kinds of angle. I think that's very important because you want to make it very simple to detect. You can use it at home. So using deep learning algorithms, we could do that, and we proved that, or we showed that the algorithm is very robust and very easy to be implemented on a smartphone. Okay, so here's an example. This is a patch with no wound fluid. This is a patch with some wound fluid. Can anybody tell me the difference between these two? Oh, okay. That's exactly what we're trying to solve. So basically, you can see here, well, the very obvious change is temperature, right? This is a temperature sensor that changes color, right? It's slightly greenish, but everything else is hard to tell, right? So, but interestingly, now if you train the machine learning algorithm with enough data, you can actually measure not just temperature change, which is maybe visible by eye, but some of the biochemical changes like TMA, trimethyl amines, pH levels, moisture, and uric acid. So these are biomarkers for wound healing, right? So using a fairly simple approach, we can hopefully then track how your wound heals, and this was done on animals. So we can track temperature changes, and as the temperature decreases, actually that's sometimes a sign of whether your wound is healing. If it's high temperature, there could be infection. So we can then do studies on ambulatory studies. So these animals are free to move around, and we can simply take a photo as they move and then track healing, right? So was recently featured on Channel News Asia, live TV. If you've never been on live TV, it's kind of interesting experience because you almost had no chance to say, if you say something wrong, that's it, right? End of your career. So anyway, but the best part is you get to take photos with your newscasters. If you're in Singapore, you probably know them. Anyway, so if you're interested, you can check this news. Lastly, I think I've come to the end of my talk. Basically, a lot of more vectors I hope we can co-create together as a community, and many more arrows to kind of develop the field beyond some of the pioneering works that many of the leaders have already done. So I'd like to thank my group. They keep me quite young, and also the funding agencies that funded the work and the collaborators in Singapore. All right, thank you.
Questions? Yeah, open questions.
Thank you, Professor Ting. And the water healing device is really interesting, and I'm curious about you have already recognized the biomarkers of the wood fluids. Is that possible if we can control the healing process of the wood, for example, to control the medicine release or add some electrical stimulus outside to accelerate the healing process? Is that possible?
No, yeah, great question. Thank you. Actually, maybe you should collaborate. Anyway, yes, indeed, you can do sort of maybe drug delivery, and that's sort of the next thing we're thinking about. But importantly, I think you mentioned about electronics. So actually, one of the reasons we are hopefully trying to avoid is to put too much need for electronics, because then it makes the system more complex and you need batteries, right? So the ideal world, if the smartphone can interact with minimal powering or need for power, would be great. So this is something that maybe there'll be potentially ideas around, right? How do you deliver information but yet not have a battery? And some of the RF powering technologies can work that we have developed. But definitely the idea is to make it as simple as possible so that any bandage, next time if you go to a pharmacy like Guardian or Watson, you can actually buy a patch that has some color change, but you don't need to have a battery, right? Because I mean, this if you have anything that's a battery, cost goes through the roof, right? So yes, you're right. We hope we can do drug delivery, but you add another 10 years to my paper before it comes out. Anyway, just kidding. But yes, we can do that. Something we are looking at. Yeah.
Any more questions? Yeah.
Thank you for a wonderful talk. I'm curious about the air's function in your pressure sensor. So what's the use of this air in your pressure sensor?
What's the use of the air, right?
Yeah.
Okay, great. I think as I went too fast, but basically what the air does is that Okay, so here the air actually is trapped in these structures, right? So this air is the reversible elastic membrane, basically, for example, that then compresses and reversibly compresses. The liquid is the electrode, and inside the structure there's a metal coating, and so we are measuring the capacitance change by the change in area of contact. As the pressure increases, the air contact line will move up and down. So this changes the capacitance. So the air is, think of the air as a spring, right? The air is the spring in a pressure sensing system. Right? Most of the pressure sensor device have some kind of rubber, right? This rubber. Okay. Okay, first of all, they are fairly high capacitance devices, right? So most of the time you have, if you use dielectric materials, they don't have very high capacitance, right? So sometimes having too low capacitance, you make it sensitive to noise. So that's one. The other advantage is that you can use in any fluid, any liquid environment, whereas most devices, when they are a membrane with some trapped air, what happens is that the membrane will sag and then it will lead to saturation. So this kind of approach would always guarantee you a trapped air that you can use at maybe different depths, right? So you can have a broader range of operation. Yeah. So that's why you see this is almost a straight line. You don't see most of the sensors. They will be sensitive at the beginning and then sort of slope changes, right? So with this approach, because we are using the capacitance change as a function of area, not distance. It is a linear relationship, right? Capacitance as a function of area change. Yeah. Yeah.
Very convenient but powerful movement patch, and each curious. Mostly the wound may have some color interference, so that impacts the result.
Yeah, that's a good question, right? So we try not to use the wound color. Humans do that. Humans actually look at the wound and try to guess whether it's healing or not, right? So in our case, what we use is actually a substrate that actually covers the wound, but then because the color change is caused by the fluid outside, so you won't actually need to see the wound. You actually only see the change by the chemicals. Yeah, so you don't need to see the wound.
So the liquid will
Absorbed by the piece of diffuse. Yeah, essentially, it's basically a piece of paper that basically by capillary forces moves the fluid, filters and move the fluid, so that you don't even have to worry about red blood cells and all. It's just the wound fluid plasma. So you mean whether this analyze will stick to the, yeah. So this is a one-time use, so we don't intend for it to use for a long time, right? So it will be thrown away. Yeah. Yeah.
Benjamin, yeah, we're interested on this liquid air sensor. Just wonder, do you need to do any calibration for, first operation or regular operation?
It's a good question. Actually, what happens is that most of them, because they're linear, the calibration is quite straightforward. So yes, you do need to calibrate it, but it has a lot higher repeatability. Yeah.
Okay. Thank you. Yeah. Okay, no more questions. So let's conclude this session.
The coffee and tea is outside, and we'll continue our next session at 4:20. 哦，哇，
Okay. Okay, good afternoon, everyone. Welcome back. So our last section includes 3 speakers. The first one is Professor Liu Yuxin from NUS. Professor Liu get his master degree and a PhD in bioengineering at Stanford University in 2016 and 2019, respectively. He was awarded Presidential Young Professorship and MIT Technology Review Innovators under 35. So let's welcome Professor Liu.
Thanks for the kind introduction, and thanks for the organizer for giving me this opportunity. I feel really honored and humbled. So today I will share the tissue mimicking neural interface. So I joined NUS, started our lab in about 1.5 years ago. So we're interested in 2 things. We're interested in interfacing with the skin. We built medical wearable devices, a departure from the conventional liquid-based biomarkers. We were exploring new types of device structures that we want to sense the solid-state biomarkers that naturally present in our skin surface. And the second interest is to interfacing with the nervous system, and that this will be the focus of today's talk. And so we know that there are many different types of the neural implants that's already being used in widely to treat in different types of neurological or autoimmune diseases, like deep brain stimulator, vagus nerve stimulator, etc. And they are usually used as a last resort when the pharmaceutical drugs fails. So we can inject electrons instead of using biomolecules to interact with our human body. And if we take a look at the history of the neuroelectronics technology, this is the first neural implant called stimulus receiver, and it was invented in 1963. And if we compare with the most state-of-the-art device, this is from Medtronic's deep brain stimulator that can be, you can compare the advancement in the past 60 years, and it becomes miniaturized. It has more electro leads, and of course, the functionality side is a great enhancement. So the improvement is mostly building on the wave of semiconductor and transistor advancement. And recently, there is another surge of the research that focus on more on the bio side. And we try, if we imagine the future, we will think that the neural implants will be indistinguishable from our neuron systems. And then this will be put a question here is what can we learn from the nervous system? So this is the outline of today's presentation. So I will first share about the mechanical aspect, and then I will go to the electrical aspect, what we can learn from the nervous system. So we want to have lower bending stiffness, lower Young's modulus, make it elastic, viscoelastic, and also growth adaptive. So the bending stiffness was is introduced to the field of neuroelectronics to measure how flexible the neuron probe is. And there is a consensus in this field that we will try to build thinner and thinner devices. Those are less than 10 micron devices. For example, like the mesh electrodes from Charles Lieber's group or from John Rogers' group, and also the startup company like the Neuralink. They are all building those very thin film device. And
If you look at this, the bending stiffness formula, that we know that if the bending stiffness will increase to the power to the cube with the thickness, right? So if you're bending from the out of the plane directions, so but in reality, it's not just bending from the out of the plane direction, but it's also bending from the left to right and all kinds of direction. So that means the lateral dimension is also important. That's why we need to build not just thinner, but also narrower devices to interface with the brain. That's what largely the direction in this field. So when we talk about the bending stiffness, we compare our device, our micron scale device with the brain, right? With the brain tissue. And then we can have comparable bending stiffness. Those devices has the similar kind of bending stiffness as the brain. But if we looking at a single neuron, right? So then the bending stiffness cannot be matched because of this the Young's modulus of those materials. Those are made of metal or polyimide. Those are polymers with gigapascal Young's modulus, and so that brings us to the Young's modulus. Another dimension that we can lower the Young's modulus is also important criteria. Besides to lower the bending stiffness by reducing the Young's modulus, there's an intrinsic value of the Young's modulus. So those are the work that I have done at Stanford under Professor Zhenan Bao's supervision. And so basically, if you look at for example, the ZAP-TAS signaling pathway, right? So if you interface with your probes with a stiff substrates, then this will change the cell behavior and it will change the migration behavior, the differentiation, and everything. So whatever we input into our biological system, we do not want to perturb the system. We want to keep the same. That's like one of the important aspect for any kind of sensor or stimulator. So we created this micro-patentable electrical conductive hydrogel. So this hydrogel has a very low, because it's a hydrogel, right? But also it's a duroconductive material, and then it has a quite high conductivity, about 47 Siemens per centimeter. And then we can patent this and make a neuron probe using these materials. And the entire device, including the encapsulation, have the Young's modulus in terms of the kilopascal, which is in the region of the nerve tissue, which is much lower than the conventional like tetrode or polyimide probes. What this brings is the lower inflammatory response. So this is implanted on the sciatic nerve of mouse. And then if we compare this soft electrode versus the cuff electrode, that's a conventional stiff electrodes. And then we have lower neuron damage. And also we have less inflammatory response that's characterized by the biomarker ED1. So the next level is that we want to not just make it solve, but also we want to accommodate the movement of the organs. Right. So this is the reason we want to do that is that the cardiac respiratory cycle, when we breathe, there is a movement. For example, in our brain, and also naturally the gut will have quite a large stream. And to have a probe that can work in those kind of high dynamic system, we need to have a kind of a viscoelastic probes that can be accommodating in this this movement. So we develop a system that can be not only be able to implant into the brain, but also can be implanted into the gut. And if we compare with a conventional carbon fiber, right? This is a carbon fiber. It's a rigid probe. So when we put this probe into the gut, okay, and then this will have the mechanically triggered serotonin release. So essentially, even before you measure it, you are already bringing some of the noise from the mechanical mismatch. And if we use a soft and elastic neuron stream probes, the background is very, very clean. And besides that, it also does not affect the chorionic migrating motor complex. And therefore, with this soft and compliant probe really is ideal for those dynamically moving organ. And we use this to track the both in the brain, in the striatum area, and also in the colon, and we see if we feed the mouse with some food, and then we will see an immediate release of the dopamine within about 30 seconds, and then the serotonin starts to increase about 60 minutes. So this time difference agree with the gut transition time, and this is really a general tool that allows us to investigate the neurochemical aspect of the brain-gut axis. Okay, so, and then now we have a stretchable platform. And the next question we ask is, most of the implant system they are built for matured system. So they're built for adults, right? So, but for the pediatric population, because their nerve size grows, and this becomes a problem. So we want to have a device that can be deformed and morphable and morphing in response with the growth of the nerve. And what we envision is something like this. A neuron probe that can be surrounded by a nerve as the nerve is growing bigger, and because we design viscoplastic properties or using for those probes, and then we can have the probe to grow together. So the two strategies that we have used is to use the wake dynamic bonding to dissipate the string energy, and also use glycerol, a large amount of them, to create a mechanical disorder so that we can have this viscoplastic properties. And then we make two structures. One is the strain sensor that tracks the changes of the nerve diameters, and also we have a viscoplastic electrodes that can do stimulation and recording. This is after 4 weeks of the chronic implanted rat. So those rats are growing in size, and you can see it's still conformal in contact with them. And then, as you can see in here, that the rat size grows much bigger over the course of 8 weeks, and so does their nerves. And if we use a conventional calf electrodes, so after 2 weeks, we no longer see the elicited compound action potential. But for the morphing electrodes, we can consistently elicitate the compound action potential. So, so we want to bring this not only in the peripheral nerve system, but also as a general concept to apply to also to a growing, the human growing organoids. So this is the cortical organoids that we build interface for. So this is the device before we release it, and it has a structure of the mesh-like macropore structure that has a elastomer and on the top and bottom, and then we're using P.PSS serving as the electrodes. And we use a bottom-up assembly method. So we put the mini spheres of those human cortical organoids. Those are derived from the iPSC cells, and then this is the day one. And after about 25 days, you can see that the cells grow significantly, and then this internalize a large portion of this mesh electrode array. And here is to show that it's quite robust. After it's integrating for a few days, it really adhered to this probe, because we did some surface treatment to make it adhere to the cells. And even if we use a tweezer to trying to stretch it, it's the spheres will not come off. And this is another imaging of the fluorescence imaging to show that the changes from day 7 to day 100. You can see the electrode arrays were internalized largely by these growing organoids. So we are really building a cyber system that has both the cell, the neurons, and also the stretchable electronics. And so then we did the localized neuron stimulation. So as you can see here is the characterization by the calcium imaging that we can selectively turn on certain channels and then turn off other channels. So we can So what we want to do here is to try to mimic the thalamus input, the electrophysiological input that happens in the developmental process, which is missing in the organoid system because it's just suspended in a culture dish. It does not receive the neuronal input from other regions like thalamus. So this the hope is for this system is to try to push the maturation of the organoid system. Okay, and then the second part that we want to learn from is the electrical part of the nervous tissue. We want to have a dual conductive electrode system to lower the impedance, matching the neuron density, and also want to use the neuromorphic architecture to realize some of the more intelligent functions. So this is a conventional no impedance electrode design. So this is pioneered by Professor David Martin, and then they demonstrate that if you coat a conducting polymer on the surface of a metal electrodes, your impedance decrease dramatically. Okay, so this conducting polymer can directly interface with the neurons. And because we want to have a soft hydrogel system, so we devised a hydrogel system. And what the unexpected result we found is that the hydrogel, because it swells from the conducting polymer, and then this creates this encapsulated conducting polymer. By the way, this is the cross section of the neuron probes. And what happens is we have a expanded interconnect interfacial impedance. This dramatically decreases the electrochemical impedance, and then we demonstrated this by doing the ultra-low stimulation on the sciatic nerve. Because the impedance is so low, then even if we compare with the conventional platinum electrodes, the mechanical micropatentable ECH electrodes can realize stimulation at very low voltage of the 50 millivolts. So this gives more flexibility on the implantable powering system and battery design, and we do not require as high as the voltage that we need before to deliver the same amount of the current density to the nervous tissue. And so in NUS, we're continuing this direction, and we want to see whether this is a universal methods. So we, instead of using a conducting polymer, here we use the reduced graphene oxides to make a three-dimensional nanoporous electrodes. So essentially, we create those nanoturnels to allow the electrolytes to go into the electrodes. And so this is the cross section, the SEM cross section of the SEM. You can see that it is aligned, and then this creates a lot of the turnels in here. And because we can have this kind of structure, the impedance is dramatically reduced, and we can pack into a lot of electrodes. So the electrode size can be reduced, and we can match the density of the neurons. So we call this as a graphene age electrodes. And we compare with the graphene age electrodes with the conventional platinum iridium. The impedance, the specific impedance, decreased dramatically, and it has comparable impedance as the PWPSS coated platinum electrodes. But the coating create a problem because you have two materials. One is a conducting polymer, and then another is metal. In the course of long-term implantation, for example, for a few months, for 6 months or up to a year, you will see the delamination of the probe. The P dot tends to be delaminated from the electrodes, especially for the stimulation case. So here, because we have a monolithic approach, so it's only a single material, but we realized as low as impedance as the coated PWPS coated electrodes. So this enable both low and also stable impedance. So because this is the very small electrodes, we can fit about 20 electrodes in about 100 micron space. So we can see the firing of the neurons that much closer look than before. So here we use the auditory cortex A1 as an example to demonstrate the recording on the closely spaced neurons. So here we're using the algorithm to resolve the physical location of those electrodes, and also we are playing different frequency sound to this mouse, and then we can see that they have different response in here in the spike density here. And if we zoom in here, we can see that it reveals the heterogeneity of the closely spaced of neurons in this A1 area. So we know from a large scale, there is certain organization in the intralaminar space, but we do not know if we zoom into a very close, like the very close to closely spaced neurons, whether this still exists. So from here, we can see they still have similar patterns. Okay, this is the 3 units from the recording. They still have certain similar units, but they do have some differences, some preferences in their tuning curves. So this really is a general tools if we want to study the neurons that is very closely packed. In fact, most of the neuron circuits happens locally instead of in a broad, in a long distance. Okay. So I'm going to play a video, and then you can contrast this video from what Professor Benjamin T just played. So this is a man that without proprioception. So this is, so proprioceptor is a type of mechanoreceptor, right? So instead of a blindfolded, you can chop the vegetables here. If you lose the proprioceptor, just one type of the mechanoreceptor. Now you can still touch, you can sense the touch, slow or fast. But if you don't know where your body is, so we always take for granted that we know, or even you close your eyes, you roughly know where your hands are, right? But for this particular man, he suffers from a genetic disease. He don't have those muscle spindle that functioning normally, so he cannot sense the location of his limbs. So that is what happens if you don't have this proprioceptive reflex. So we want to in here we want to build a artificial nerves that can mimic this proprioception. So this is done in a to bypass the damaged spinal cord, and then we can mimic the proprioception by directly relay the action potential directly to the muscle. Here is the picture of the device that's been attached to the muscle, and they composed of an artificial proprioceptor and also a synaptic transistor. So one is to convert the frequency into the amplitude. Another is to act as a muscle spindle. So in human body, the muscle spindle is a mechanical receptor that's inside your muscle, and when you stretch, and then this will send a signal to this reflex. And here we use a simple voltage divider. So when this string sensor gets stretched, and then this will decrease the gate voltage for the synaptic artificial synapse. So then this will reduce the postsynaptic current. And you can compare that if with the proprioception or without the proprioception, the excitatory postsynaptic current have very different behaviors. One, if you without the proprioception, it will need to continuous increase, and this eventually results in the muscle strain. So the natural, our biological body is already built in this intelligence to prevent us to continuously to stretch your limbs. For example, if you put your limb on your neck on one on each other, and if you have a hammer to lock here, and then you will see that kind of the reflex. That is to kind of to program to prevent this kind of the muscle damage. So we demonstrate here that we can convert a different frequency of the action potential, and then we can trigger different kicking strength. And also this can be done in a bipedal fashion. And here the mouse is anesthetized. So it's like a sleepwalking mouse. So we directly input the signal from the action potential directly into the muscle to create these motions. Okay, so to summarize, so I talked about more of a biomimicking approach, from applied to approach to design for approach, to trying to mimic the mechanical and also the electrical properties to have like flexibility, soft, viscoelasticity, gross adaptive, duroconductive, and also using neuromorphic architecture to realize the closed loop feedback to mimicking the reflex. So with that, I would like to thank our group in NUS and also my collaborators and the funding. Thank you.
Thank you, Professor Liu. Now it's Q&A time. Any questions?
Thank you. Nice talk. I'm quite interested in the electromechanical testing. How do you optimize the long-term stability and the selectivity of the sensor? You're sensing two different chemicals.
Yeah. So traditional electrochemical sensor like carbon fiber, you can also use it based on different voltage, right? You can sense multiple, usually two neuron chemicals, but their peaks are very, very close. So in our case, we screen different types of nanozymes, like iron oxide, nickel oxide, and all of them. And we found that an iron oxide actually can separate, they separate the redox potential. Then we could sense 3 at a time. So in fact, we can have multiple, more than just dopamine, serotonin. We can also sense epinephrine. So that's how we can sense multiple neuron chemicals at the same time. But of course, the sensitivity, the selectivity is not as good as enzymes or antibodies, of course, but it gives certain specificity by tuning the nanoparticles. And for the biofouling problem, for the long-term use, so we demonstrated for 3 months implantation, and there's minimum change of the performance. So we do have a coating like naphthalene on top to protect the biofouling. And I think there are many other strategies we can also employ to resolve this problem. Yeah.
Okay, thank you.
Thank you, Professor Odile. Very interesting and a very inspiring talk. I have a question regarding the viscoplastic materials for using for the growth peripheral nerve. So my question is, for such kind of materials, what is the yield point for the plastic part?
So we wanted to stretch. Yeah. And then it's a permanent change.
Yeah, yeah.
We don't want it to contract, right? If it's elastic, then it will come back. But we want to minimize the stress because the nerve is growing, right? If it's elastic, the stress will build at the interface.
Yeah, yeah.
But if it's viscoplastic, if it's plastic and it's permanent change, then the stress is always at 0.
Yeah, my question is, for materials, if you stretch a little bit, it's still in the elastic region. Only you stretch it for very relatively large strain, it will enter to the plastic stage. My question is how much the strain, what are the strain?
So
after that, it will enter to the plastic.
So the materials that we use, the PDMS-IU, the materials, it's viscoplastic. So we can, it's like a Play-Doh. When you stretch it, even a small change, if you stretch slowly, the key is that if you stretch very fast, it will still behave like an elastomer. If you stretch slowly, which is the case for growth, and then it will have a permanent change.
Oh,
yeah.
Okay. Sorry. Thank you.
Hello, Professor Liu. Thanks for the very. Oh, sorry.
So you said it's a vehicle, there's vehicle very slowly and always will deform to zero stress. So that means there's no threshold.
Yes.
Right.
Yeah.
This is viscoelastic.
So this depends on the
It's like
strain rate. Yeah.
it's like if you use a rheological model with spring plus a dash pot, right? That kind of.
Yes. Yes.
So there's no yield stress associated.
Yes. Yes.
Viscoelastic.
Yeah. If we stretch really slowly, yes. Yeah.
So it's a viscoelastic.
Yes.
Thanks for the very well-organized presentation, Prof. Liu. I didn't quite get about the graphene etch electrode. How did you reduce the size of individual electrodes? Did you use individual reduced graphene oxide sheets as electrodes? If so, how did you solve the wiring problem of so small electrodes?
Okay, so I didn't get to talk about the manufacturing of the probes. So essentially, we are making fibers. The fiber have the diameter about like 10 micron or below. We can change the diameter. So essentially, we can make a hydrogel that's made of the RGO. And then we just evaporate the water, and then it will shrink in size. And then we can have individual fibers, and then you can do different insulations. At like the SU8 or other pairing, and then yes, we do have to connect this out to the head stage. So we have to connect individual wires out. Yes.
Okay. Any more questions? So if not, let's thank the Professor Liu one more time. So our next speaker is Professor Sheng Xing from Tsinghua University. Sheng Xing received his bachelor and PhD degree from Tsinghua University and MIT respectively. He worked as a postdoc researcher at UIUC, and his current interests are primarily in the exploration of implantable micro nanoscale of electronic device for neuron signal sensing and modulation. Let's welcome.
Yes, thank you, Chairman. Good afternoon, everyone. I would like to take this opportunity to thank Professor Chen Xiaodong and Professor Feng Xue for organizing this wonderful symposium so that I can meet all the colleagues here in Singapore. My name is Xing Sheng. I'm from Tsinghua University. I'm affiliated with the Department of Electronic Engineering and also the IDG McGowan Institute for Brain Research. So my research area is mostly focused on the interdisciplinary area between the electronic engineering and the brain science. And I think the previous speaker, Professor Yuxin Liu, already gave a nice introduction about the brain electrodes, right? And my work is mostly focused on the optical part. And we're trying to design and fabricate the microscale optical electronic devices for the advanced neural interfaces. So I will not go to the details about the motivation, since the Professor Liu already did that, right? We all know that the brain science is a mystery, right? A lot of people get interested in this area because it's fundamentally it has a lot of unknown questions, right? We need to solve, and in the application side, also it helps us to guide us for a lot of neurological disease treatment, right? So the brain science has been considered as the last frontier for the life science and all the sciences. Okay, and we need to develop new technologies to try to understand this the brain structure and the functions. So here I would like to take a quote from a famous neuroscientist, Professor Sitten Brainer, and he once said that the progress in science, right, depends on the new technologies, new discoveries and new ideas, probably in that order. So in his opinion, since he takes the technology as the first, right? So that means that we need to initiate the new technologies first, so that we can have new discoveries and new ideas, not only in the brain science, right, but also in all the life sciences and the general sciences. Okay, and when we think about the brain technology, most of you may think about this the non-invasive techniques, though this wearable sensor, so that we can put it on our head to read out some brain signals and use it, right, for some disease diagnosis or some brain machine interfaces. Okay, and these non-invasive techniques have been widely used, and they are easy to use, right? Everyone can use that. Right? They use different physical signals, like electrical signal, magnetic signal, optical, and acoustic signals to interact with the neuron signals inside the brain. Okay. However, these techniques already, although they are being widely used, but they have some limitations because it's not directly interacting with the brain tissue. So it has a barrier, right? The skull and all the skin and hairs, right? So it has a relatively low spatial and temporal resolutions, and also these physical signals like the electrical, magnetic, and optical acoustic signals have limited tissue penetration, so we can not easily to get into the deep brain by using these non-invasive techniques. Okay, so for some specific purpose, especially if we want to go to deep inside the brain, we have to use the invasive or implantable techniques. Okay, this is my research motivation. So we're trying to develop advanced neural interfaces. More specifically, we're trying to develop some microscaled electrical and optical devices and use it as a tool to implant inside into the brain to directly interact with the signals inside the brain tissue. So that on one hand, we can use that as a tool to explore a lot of fundamental science questions in the life science and the brain science. And on the other hand, we're trying to also collaborate with the clinical experts to try to develop new tools or method to treat the neurological diseases, hopefully in the near future. Okay, and so we are actually interested in the different parts or different components of the brain, right? We're trying to develop different type of devices to interact with the neural system. For example, this is our representative work. We can design our device as a membrane so that it's flexible and it can be mounted on the cortex, the surface of the brain, for some stimulation and sensing purposes. Or we can go inside, right? We can design and fabricate our device in a micro scale so that to integrate them into a probe so that they can be inserted into the deep region of the tissue to generate light and optical and electrical signal to interact with the brain signals for tissue brain stimulation and sensing. Or in another work, we're also interested in the outside part, right? The skull, the bone, right? The cranial bone of our head, right? So we develop a scaffold material that we can help to facilitate the bone defects and the bone refracture, okay, to help for the healing. Okay, in another approach, right? So these techniques are actually very invasive. So if we're interested in technology that can go to deep brain but not so invasive, okay, we can go through the vessel, right? We're trying to develop a miniaturized fiber-based sensor so that it can goes into the brain through the cerebrovascular system, basically the brain vessel system, so that it can go to the deep brain. This work is under preparation. Okay, so the time is limited. So today I only talk about one work. This is a recent work we just submitted for. This work is not published yet. Okay, well, in this work we're trying to solve a very fundamental and simple molecule sensing problem. Okay, we are trying to sense the oxygen. Okay, we have many substances inside the brain. Okay, a lot of different chemicals, right? But the oxygen probably is the simplest one and also the most important one. Okay, and here we're trying to develop a photonic-based probe system to insert it into the deep brain tissue to sense the oxygen level inside the deep brain. Okay, this is based on a fluorescent signal change, and also to facilitate this implantable probe, we develop a wireless-based circuit to operate it for the freely moving animals, and the entire system can be mounted on the skull, right, and work wirelessly to read out the signal. Okay, and for the background, and the oxygen, as we said, is everywhere, right? We probably didn't realize that. Okay, and actually, but it's very important, especially for the brain function. And we know that if we don't eat, we don't drink, we can survive for several days probably. But if we don't breathe, right, without oxygen, we probably cannot survive for after a few minutes, right? Oxygen is important, even though we don't realize that. Okay, and especially for the brain. Okay, our brain only has about 2% of the body weights. Okay, for normal humans, like 100 pounds, the brain is only about 1 to 2 pounds, right? But it consumes, okay, about 20% of the overall oxygen. Okay, because the brain is always working, right? It's always functioning. Okay, even though even if we are not moving. Okay, and that makes the brain is the most the organ most sensitive to the oxygen, right? It's very sensitive to hypoxia. Okay, hypoxia means the low oxygen level. 这个叫缺氧，对，缺氧状态，对。Okay, and in lot, it's also associated with a lot of diseases, right? Like the external injury, okay, the stroke 叫中风，对吧？中风。Okay, seizure 是癫痫，对 ，and the brain tumor, okay, and in lots of scenarios, okay, the real-time oxygen monitoring is very critical. Okay, and there are a lot of techniques people have been developed to try to detect the oxygen levels inside the human body, right, and inside the brain. Okay, you may be very familiar with this method. For example, this is called the brain oxygen saturation. Okay, and especially during the COVID-19, right, people are everyone have this one in your home, right, to use this as an oximeter, right, to detect the oxygen levels. Okay, but you have to understand that this is a detection of the blood oxygen. Okay, what does it detect? It detects the hemoglobin, the HBO and the HB. Okay, 就是叫血红蛋白啊。It actually sends the oxygen level inside the blood. Okay, it's not a direct measurement of the oxygen molecule. It's a measurement of the protein. Okay, basically the protein HB and HbO2. Okay, based on their optical differences, right? So that they have a different optical absorption in the red range, so that they can have a different colors. So use this method, we can use the optical method to measure the color change of the blood, so that we can measure the oxygen level. But this is an indirect measurement. It measures the blood oxygen. It's not a tissue oxygen. Okay, you have to keep that in mind. And another method, okay, it's called the functional magnetic resonance imaging, fMRI. Okay, is another method we can use to detect the oxygen level. But also it detects the blood flow. Okay, it detects the magnetic properties, difference of the magnetic properties between the HbO2 and HB. Okay, that it can give us some imaging, but it also indirect measurement. It measures the blood oxygen, not the tissue oxygen. Okay, and there are some methods that can be used to directly detect the oxygen. For example, the electrochemical method. Okay, this is called the electrochemical electrode, right? It's called Clark type electrode. Okay, based on electrochemical scanning. Okay, it's called the polarigraphy. Okay, it can measure the oxygen pressures or oxygen concentrations inside the tissue. But it's actually have a very complicated setup. Okay, it has some diffusion membrane so that it can have high selectivity. Just let the oxygen pass through. Okay, it has a electrolyte inside, and it has the silver electrode and the platinum electrode for sensing and the reference. Okay, it's basically a complex tool, and it's actually very, very big and bulky. Okay, it's already being used in the clinical, in the hospitals, mostly in ICUs to detect the brain oxygen signals for some people under the serious diseases. Okay, and another method is based on the optics. Okay, in this method, people use these fiber-based optical sensors. Okay, they have some coatings on the tip of the fiber. These coatings has a sensitive optical properties, sensitive to oxygen level. Okay, it has some phosphorescent dye materials that have a different emission intensity under the different oxygen levels. Okay, it's based on the photometric method, but still this is a wild method, wild techniques based on a fiber sensor, fiber sensor. Right, we need to develop a wireless-based portable solutions for the biomedical use. Well, this is our approach, and here we're trying to develop a wirelessly operated photometric probe based on this microscaled optical electronic devices, right? And the fluorescence oxygen-based fluorescence coatings for the oxygen sensing in the living animals. Okay, so we'll go to the details about our device design. Okay, this is a multi-layered structure, right? All integrated in a implantable thin film flexible probe. Okay, to detect the oxygen, the most important component is an oxygen-based sensor. Here is the sensor is based on a TFPP is a platinum-based complex. Okay, it has a unique structure and whose optical properties depend on the oxygen levels in the environment. Okay, basically that this structure have a optical quenching. It has absorption peak in the violet region, okay, around 400 nanometers, and it emits in the red region, okay, emits around 650 nanometers, okay, and this light emission is highly dependent on the oxygen level, so it has an oxygen quenching property, okay. Basically, when you supply the oxygen, okay, this is in the pure air, in the pure nitrogen, it has a very strong fluorescence, red fluorescence, but you supply some oxygen, basically here you flow the oxygen inside, the fluorescence will be quenched. Okay, so based on this emission difference, we can detect the oxygen difference. Okay, to accommodate this optical properties of this molecule, right? It has absorption and emission. We designed the microscale devices to as a light source and the light detector. Okay, and here the light source is a violet LED. Okay, it's a violet micro-sized LED, and to fabricate this LED, and we use a conventional technique to grow this material based on indium gallium nitride. Is basically a compound semiconductor material. Okay, we use the standard fabrication process to fabricate this micro LED arrays, and then develop a technique to release this micro devices, thin film device from the original sulfide rigid substrate and transfer them on a flexible substrate. Here we transferred it onto a probe, flexible probe. And similarly, we can have a light receiver. Here the light detector device is also a microscale device based on the gallium arsenide. Okay, similarly, this device is grow on the gallium arsenide substrates, and we go through the micro fabrication to fabricate it, and by chemical etching, we release the micro thin film device and transfer them onto our implantable probe. And by doing that, we can realize this microscaled light source and detectors, right? This is the LED and this is the detector. And both of them have a size around 100 micrometers, and the thickness is only about a few micrometers. And it has a emission in the violet part, right? The emission peak is around 400 nanometers. And the detector, here we have a coating, field coating on top of it to optimize its spectral response. It has a response in the red part, right, which is designed to detect the fluorescence of the molecule. You can see the light source, the LED, and the detector matches very well with the optical properties of our phosphor material. Okay, and this is the fabricated probe in this thin film flexible probe with a width about 200 to 300 micrometers. Okay, we integrate the micro LED and detector on the tip of this probe. Right, this can be implanted into the deep brain tissue for oxygen sensing. You can see that we tested in the air environment. Okay, in the air and in the pure nitrogen environment, we can see that this coating have different optical response. Okay, in the low oxygen environment, in the pure nitrogen environment, you can see have a very strong red fluorescence. Okay, and to accompany this implantable probe we developed, okay, we designed a wireless circuit to control it and transmit the data. Okay, specifically, we use a battery to power the LED, and we use a LED driver, right, to drive the LED, and we use the amplifier to receive the signals from detector, and use a Bluetooth chip to wirelessly transmit the data to the external systems. Okay, this circuit is around the size about 1 centimeters. It can be mounted on the head of some test animals for some experiments. Okay, the entire system has a size about 1 or 2 centimeters and a weight about 1 to 2 grams. Okay. Okay, and then first we tested this probe in the in vitro environment. Okay, we put it in the chamber and free flow different oxygen and nitrogen into the chamber. We can see that this probe have a response, right, sensitive to the oxygen pressure, and especially we can see that in the low oxygen levels, the fluorescent intensity will increase significantly. So this makes this device very sensitive to the low oxygen region. Okay, and actually the response, the inverse of the intensity versus the pressure follows a linear relationship. Okay, this is called the standard Stern-Wörmler relationship. Okay, and okay, we can test the dynamic properties of this probe. Okay, we flow alternated oxygen and nitrogen. We can see that according to the flow of the gas, and this device can have a response, right? Can have a response, and the response time is around 1 second. Okay, and then next we can do in vivo experiment to test them in the living animals. Okay, we implant the probe into a mouse, and we mounted the wireless circuit, and we flow a different gas to the animals, right? To change the flow of the oxygen. We change the flow of oxygen. We can see that our device can detect the brain oxygen levels, right? Dynamically according to the different oxygen flows, right? And we compare our results with a commercial fiber sensor. This is the fiber sensor, NeoFox fiber sensor. You can see the results matches very well. Okay. And then this is second experiment. Okay, we will try to block the artery, block the artery, 就是叫 in Chinese called 颈动脉结扎. It blocked the artery here, just block the artery of the mouse. Okay, to block the blood flow. Okay, this will reduce the oxygen supply inside the brain. I can see that during this blood blocking, we can see that the animals experience a very low oxygen level inside the deep brain. Okay, but when we release it, we release this ligation. Okay, the oxygen supply will recover. Right, we can have the oxygen level go back to the normal. Okay, and because of the use of this wireless circuit, we can do it in multiple animals. Okay, this is we simultaneously test the oxygen levels in the deep brain for 3 different mouse when they are freely behaving in the chamber, and we supply the different oxygen pressures into the chamber. We can see that this device can dynamically check the oxygen level inside the brain tissue. Okay, and next we're trying to use it to discover some brain functions in some disease model. Okay, so here we develop a disease model, a seizure-based disease model, 癫痫 a seizure-based disease model in the mouse. Okay, we're trying to monitor the tissue oxygenation. Okay, in the seizure event, under the seizure event. So how we do that? We implanted the probe into a specific region called the hippocampus region, and we insert another electrical electrode, okay, to apply the electrical currents to induce seizure. Okay, to induce seizure, and we can track the oxygen levels under the seizure event. Okay, Okay, this is the result. So the kindling is the electrical stimulation. We apply short stimulations, right, last for 1 or 2 seconds, and you can see that accompanying with this electrical stimulation, there is a drop of the brain oxygen. Okay, there's a drop associated with this stimulation. Okay, associated with this stimulation, which means that this electrical stimulation will induce the cerebral hypoxia. Okay, and here shows a movie. It shows a movie. Okay, this is the mouse. This is the mouse. It has wires. This wires is for the electrical stimulation and the electrical recording in the hippocampus. Okay, and we apply a short pulse to stimulate the mouse. Okay, you can see the induce a seizure event. This is we call the electrical field, electrical signals. This is the oxygen signals. Okay, this is a seizure. Okay, this is a seizure. Very strong electrical signals. Okay, associated with the brain activities. Okay, and then the mouse starts to take a rest. Okay, and we can record a low blood oxygen level, low oxygen levels. Okay, and then later on this oxygen level will recover. Okay, there is a delay. Okay, you can see there's a time delay between the oxygen reduction and the electrical activity. Okay, that means that this electrical activity, the neural activity, is a cause of the oxygen consumption and to reduce the brain oxygen. Okay, and we can actually test it in multiple different regions, and we found some interesting results. Okay, if we stimulate this CA1 region, the same region, and we record the oxygen level in different places inside the brain. Okay, you can see this records the oxygen in the M1. This records the oxygen in the CA1. Okay, and depends on the different brain regions, and there's a different time delay. Okay, and these different regions show different temporal responses, so different oxygen reduction time. Okay, after the stimulation. Okay, and we can compare these results with the blood oxygen. Okay, people say, well, we can do it MRI, right? We can do functional MRI, also detect the oxygen. But as we said, this is blood oxygen, so it reflects different signal. We compare with the literature, we can find that people did the similar experiments, right, in the mouse. They stimulated the brain and they checked the blood oxygen with fMRI. They can do imaging. They always capture an increase of the blood flow and the blood oxygen supply. Okay, but in our recording, okay, our device captured decrease associated with the seizure. Okay, so that means that this tissue and the blood oxygen are fundamentally different. They are related, but they have different signals, right? And they have different meanings inside the body. Okay, and to further improve the system, right, we can optimize the circuits. We can optimize the circuit. Right now, this circuit is mounted on top of the mouse, right? It's rather big, and we can remove the battery. We can get rid of the battery, okay, and put all the components on a flexible substrate and fully mounted underneath the skin, right? Underneath the skin, okay. And this is the demo inside a rat, okay. It's a rat. It's bigger than the mouse, okay. So this is a battery-free power circuit, okay. Without the battery, okay, we can reduce the weight by half, okay, the system. Okay, we take the imaging to check the status of the circuit inside inside the head, okay, underneath the skin. Okay, and how to power this device? Because we don't have battery, we have to use the coils, right? We have to use the coils to inductively power the device and the probes inside the animal head. Okay, and similarly, we can use this battery-free powered device to capture the oxygen signals. Okay. Okay, I think that's the end of my talk today. I'll give you one example about our research interest. Our research is basically interested in developing different kind of optical, microscale optical and electrical devices to sense or stimulate different signals inside the brain, right? And this is in this particular example, we're doing oxygen sensing. Okay, we demonstrate that this oxygen tissue sensing, okay, have highly important correlations with the normal brain activities and the health state of the animals. Okay, and finally, I would like to thank our group. Okay, these are the students who did all the work at the Tsinghua University EE department, and I would like to thank our collaborators and our funding supports. Okay, And finally, this is a small advertisement. Okay, I'm organizing a special issue in the journal called Fundamental Research. Okay, the issue is called Multimodal Technologies for Neuron Modulation and Sensing. And this is the editorial team. Okay, our team. Okay, if you are interested, you are welcome to submit related manuscripts, either original research or review articles to the journal. Okay. Okay, finally, thank you for your attention.
Okay, thank you. So now it's a question time.
Thank you, Professor, for your talk. So you are using a molecule called PTFPP as for the oxygen sensing. It must have a lifetime decay, right? So will this is a concern for the using time of the device?
Oh, you mean it has a stability issue, right?
The molecule will decay as it's implanted in the brain. Is it?
It has a degradation. It's called photo bleaching.
Yeah, degradation.
It's called photo bleaching. When we shine the violet light onto it, right? The intensity will decrease gradually. Okay. So the way we optimize that is that before the implantation, we do a pre-treatment to degrade it. Okay. To make the bleach. Okay. During some time, for example, we put it under the violet light for 1 hour to make the intensity or the efficiency decrease. Okay, and then it will reach a relatively stable stage. Okay, during some time, during a few weeks. Okay, and then we use that probe for our in vivo experiments. Okay, and the signal is relatively stable in this case.
Okay, thank you.
Very nice work. Yeah, I just have a very naive question. When you have implantable device in the brain, do you take it off after some time, or do you just keep permanently in the brain?
Oh, it depends on the application, right? For some application, for example, the deep brain stimulators, DBS, to treat the Parkinson disease,
okay.
So the device will be implanted permanently. For a few years, maybe 5 to 10 years.
So do you worry about lifetime of the device? How long?
In that case, that the device need to be highly stable, right? It can work, last for many long time. But for some device, for example, this oxygen sensing probably will not be implanted for long time. This is used to monitor specific disease or trauma states, right? For some disease states. So once it's cured, for example, during injury in the ICU.
Okay.
Right, in the ICU, people will use that to detect the oxygen level.
Since you're talking about deep brain, right?
Yeah,
yes. Danger, to take it, you build in and take it off. Yeah.
Yeah. So surgeries can do that.
Surgery,
of course. Yeah, that's doable. Yeah. Mm-hmm.
Thank you, Professor. Very wonderful talk. I have a question regarding my question is actually, will the other factors in vivo will influence the sensitivity or the properties of such kind of sensor, such as pH or some
the selectivity, right? The
selectivity or maybe sensitivity.
Yeah, right. It's a normal issue for electrical sensors. If you're doing electrochemical recording, you have the interference by other substances. But here we're using optical sensing. Okay, based on this specific phosphor here, it's actually it's only sensitive to oxygen. And we try different substances. For example, we tried the nitrogen, the carbon dioxide, the carbon monoxide, and it will not have any sensitivity to different gases. It's only sensitive to oxygen, right?
Okay, thank you.
Yeah.
About the same work, and I have a problem encountered before. I do a fluorescence probe, but when I mix with PDMS, the efficiency of the fluorescent probe interacting with the gas may be hindered, maybe difficult to react. So do you have some
optimization advice when I mix the fluorescence probe with the PDMS?
Oh yes, I think so. If you mix these particles inside some solid, right? The gas diffusion will be
hindered,
delayed, right? Will reduce the response time. That can happen. And here we didn't notice a significant reduction of the response time. It's because this film is very thin. It's only 10 micrometers. It's only 10 micrometers.
Is it also because of the oxygen is very small?
Yeah, the PDMS is very gas permeable, and the oxygen and water can just penetrate inside. Okay, but if you use a thick film, it may be an issue. Okay,
just thin film. Okay, thank you.
Yeah.
Okay, any more questions? So if not, let's thank the Professor Shen one more time.
Okay, thank you.
So our next speaker is the Professor Chen Xiaodong. Anyone who don't know Prof. Chen? Okay, now you can start.
Who is he?
So you can see such long.
Thanks for Suzhou. Very good honor and also pleasure to be here. In fact, this is very, I don't know, I can remember when my last talk being in NTU campus, maybe a few years ago. Really in this kind of open public talk. Usually, like, the student report to me for a group meeting, right? I never report to students in typical topic, right? So I do my best, to share, something what we are doing. I mean, I will make sure I'll finish before 6 o'clock. Okay. And talk about this kind of soft electronics, interconnection, and also packaging. Some of work we are publishing, but some work we still going on. So I want to really share with the community something we feel this is really important for the soft electronics, flexible electronic device, it's kind of future development as well. So this morning in the city, Okay. So this morning city mentioned about emerging technology, right? So this is something I also want to, because city more emphasize about AI facilitate healthcare. In fact, for their top 10 technology, AI is the last one. Okay, there are more other kind of technology related to the flexible electronics one. So this one here, the first one talk about flexible batteries. The second one about generalized artificial intelligence. This is also about flexible electronics really. Why? You need reliable data, right? So this is always, I argue, flexible sensor of your tool can give you the reliable data, allow you to really further expand your AI domain. And then the fifth one about this kind of metaverse for mental healthcare. So this is also extremely important about this kind of monitoring device. Part of effort, of course, about flexible sensors, flexible technology developments. I mean, this morning, previous speaker, many people talk about this already, with this kind of sensor parts. The number 6 one is about wearable sensors. In fact, this is one of the key areas we are developing in the last few years. I mean, welcome to visit our lab. We do not provide this kind of a large amount of vegetable, but we still have something salad for you to test if you want. And then the number 8 one is about flexible neuroelectronics, right? Exactly previous two speakers mentioned already. I've got last one about AI facilitate is healthcare. So you can see 10, we cover at least 6 already. So now you can see how important for the flexible electronic technology, right? So this is something one, it's really the emerging enabling techniques. Do you remember? Just now, Senshi mentioned already, right? For the Brandon, in fact, very, let's say Nobel Prize laureate. He's kind of Singapore citizen, honorable citizen. So he spent a lot of time in Singapore. He built a strong foundation for Singapore's healthcare. But Brandon, he mentioned about just now sentence techniques, right? And then following about this kind of idea development. So technique is important. So that's why flexible electronics extremely important. So I want to double emphasize again about this one. Okay. So now talk about flexible electronics. The question is, everyone know already we are really experience, a lot of this kind of new experience come from technology. So this is like this kind of last 70 years, various kind of computer-based technology from ENIAC, go for this kind of personalized computers, go to smartphone. Many things are going on now. But of course, we also keep asking ourselves one question: what's going to happen in another 30 years, right? From 2007 to 2037, so another 30 years. But I know it's not far away from now. It's on just about a few years now. What's going to happen? In fact, I don't know. I don't also have the answer, right? But one thing I really I'm sure is something really happening with this kind of human-machine interface. The device must be conformable, smarter, and lighter. So this is something one. In fact, this today also with a lot of people talk about human-machine interface. So this is going to happen just about 14 years away. In fact, it's not just last minute to happen. In fact, there are many kind of developments going on now. We regard this kind of robotic surgery, exoskeleton, or even wearables. Many ongoing on this kind of development. So that's something one really very fascinating to us. Then, what to be to us, right? So this is something one. In fact, my groups or our group is really interesting to have this kind of conformal bioelectronic interface. So this is something one we feel is very important to what is called stretchable, biocompatible, and durable. And by the way, this image is not really, not real one. It's generated by AI. It's AI generated image plus with something with visual. Because some of image can do much better. Which I think our students still working on to really make this device can be very compliant to all this different kind of shape. But this is our vision lab. Along this vision, what be methodology? So with my group is use this 3M approach. 3M start from molecule modification, materials development, and also very important methodology developments. 3 part together to really develop this kind of conformal bioelectronic interface for the various sense digitization. So this is something one the key areas. I will not talk too much about. In fact, many people really can refer with our many papers in different topics from materials developments. In fact, we work closely with Huajian together to develop this kind of mechanical materials science engineering concept. So this is the way we feel will be the kind of next approach to the diverse kind of materials, that's programming materials as well. And then, of course, people can see a lot of this preparation already, but not to highlight much. I just want to show you something we feel we need to address the key important parts, like this movie. So this movie you can see, right? Let's watch this movie first. So this movie show you kind of one real hand, another prosthetics, right? And then we really can capture this needle, and then you can see the signal can transmit into this prosthetics and capture this needle as well. So this is something the movie, it's real movie, it's not fabricated by AI. And also we published a paper about a few years ago. But again, just published, right? You can see, although we can publish, by this technology, no one will try to do it, right? Why? You can see all this kind of connection. Do you like this kind of connection? Very kind of, it's really, I know we precisely put this kind of sensors in the position. We want to get a massive signal. But you can see the connection, the size, is not all this kind of very, very kind of lousy structure, right? And also you can see this kind of connection. So that's why it's only for publication. But no one will really take this technology. Moving forward, next step, right? So that's what's the problem here? Interconnection package. You can see also, my students try to, because last few years we try to come with this repeated experiment, because there's always some social media coming, want to really take this picture, and the student involved in this kind of photo taking or movie taking, how struggling it is, right? It's always although it's just about a few second movie, but take us still for maybe half day. Some still might smile already, maybe longer to repeat. It's repeatable, okay? It's not really, it's repeatable, but it's taking some time. So that's why, how we can really move forward? Because it's a packaging problem. All this kind of interconnection problem at the end will really determine how robust or this technology is being widely used by communities. So according to this kind of Dantian law, right? So assistance, strength, robustness is not dependent on which the highest or the strongest part. It depends on the weakness parts. So in this case, for the soft electronics or flexible electronics, In fact, we have many, many advancements already in different kind of sensors, in elements, element sensor, whatever, many things developed already in previous speaker mentioned many as well. But one of the really kind of problems is soft interconnection. So this will be the foundation layer. So if we move from next steps, right? In the last almost like 20 years, a lot of this kind of breakthrough in the flexible sensors everywhere. Okay, but of course, be careful. All these developments start from electrodes, materials, of course, foundation, chemistry, but electrode, diodes, sensors, transistors. In the technology readiness level, still low, and also its function still simple. It's almost lower complexity, also functionality is very low. In the future, you really go for daily applications. You can see all different applications, whatever is kind of intelligent system, or other kind of sensitive digitization, and also digital healthcare. We mentioned today a lot already. From here to here, a lot of this kind of gap we need to pass through. Of course, first one we need to pass through is how you really connect all these kind of elements together. So that's why here called soft interconnects. It's a kind of fundamental technology gap there. This also will be really kind of a big barrier and lead to moving this kind of multifunctional stretchable systems. So this is something we want to address it. But how address this one, right? I mean, everyone already is a lot of development on different perspective already. Then, in fact, many people also tried for this kind of interconnection problem. You know, not only first one in my group, many people also tried it. And then also in the last almost 10 years, the many approach, including this kind of commercial anisotropic conduct film, conduct paste, solder, and multiple even approach to really want to combine all different components together. However, still many problems. First, improve this kind of easy debonding different components, and also the connection part play very important this kind of signal noise ratio. If that part connection is really weak, the whole system noise will become dramatically. So all these problems come out. This is fragile connection, still challenges them. So that's why we ask ourselves how we really can address this kind of problem to robust technology for the community to follow, to use, and really push our this technology to more frontier. And then our dream is Lego. Can we can Lego-like integration? If multiple components together, integrate together, and then if something want to change, just change diameter at the end, and know based on your module approach, you can really have various kind of functional systems as you want. So that's why here Lego-like integration is possible. And then you found all this kind of Lego integration is come from which problem? Interface problem. It's always a surface problem because different modules integrated. It's a surface problems. So that's why the fundamental question will go to the science into materials. It's about interface and also adhesion. How do you create interface, have a more strong interface and also more strong interaction? So in this case, you really can address this kind of bottleneck problem in a soft connection of a flexible device systems. And then moving back for a few years ago, we developed this kind of mechanical interlocking approach. So this approach is used to enhance the interaction between two materials. In fact, theory itself is very simple. It's GK adhesion theory, right? For two materials, if you reach the interfacial tension, you cannot change. Once you can change it, increase the surface area, increase contact area. So that's why at that time, we build this kind of gold nanowire models, and then you increase interaction between PDMS with the gold. And also meantime, increase kind of friction and friction between the two materials. So in this case, you really can increase 10 times of this kind of adhesion. But in this case, for this kind of gold, it's really well organized by this kind of template. We found this kind of gold nanorods template there. So this is something you know, for our students, take maybe about 1 week to form this kind of to grow template for nanowire and go to the film. So this takes us a long time. But this theory to us already, you really need this kind of nanorods really well organized order, like the previous skin so here. Not necessary, right? As long as this kind of surface increase the surface area, you really dramatically enhance this kind of adhesions there. So that's why we think, why not make it really randomly, or make this kind of nanorods randomly, whatever, how this way. And then we furthermore also wondering for us, right? For this kind of gold Why is it peel off from silicon? Because interaction. The gold growth on this kind of silicon surface is two-dimensional diffusion model. Then cannot penetrate. The previous we tell us already, right? You want to increase interaction between two materials. How do you make sure gold can penetrate in substrate? But of course, impossible for this kind of silicon substrates. So that's why we further think about solid substrate that cannot work. How about liquid substrate? Metal can diffuse in liquid for sure, right? Of course, it's not joke. I mean, it really is. People ask, joking, right? How really use this kind of gold in a liquid substrates? But it's really possible. So one thing we change here is that typically the fluid substrate, we don't use this kind of flux. PDMS is a solid substrate. But if you ask yourself, if I just have a cure of a PDMS, in this case, there's a lot of this kind of monomer still in lower, this kind of low polymerized ligand inside. So in this case, the gold can penetrate by the thermal abbreviation. So this is the fundamental science behind. And then, of course, how to do it? This process is very simple. So typically, people deposit on this kind of a full polymer PDMS as substrate, but we use a half cure PDMS. It's not this kind of half a polymerized, this kind of PDMS, very low this kind of polymerized. In this case, a lot of this kind of polar structure inside. And when you use gel heat to heat this kind of gold immediately evaporate, the gold atoms will penetrate inside, and then in limited time, because gel heat, the whole chamber is about 90 to 100 degrees. So in this case, we use this remaining heat to further polymerize this monomer and the monomer PDMS inside. So in this case, gold was really captured inside. So this is how gold penetrates inside, use remaining this kind of thermal radiation to further polymerize. And then, of course, it leave enough time, gold will be really continued growth at this kind of nanofilms, gold nanofilms, conductive films. For this approach, we call thermal radiation assisted metal encapsulation. In short, we call trap, right? Exactly, the gold was trapped in the PDMS. So this is the idea. How the sample looks like, this one. So this is gold. This is gold on PDMS. It's stretchable, bendable, foldable, and also restable with regard to how you really want to apply it, right? And also you can see the back layer. You can see the back layer is black color. What's black color? It's not carbon, it's black gold. The gold become nanoparticle aggregate together because it's got optical properties there. Because it's got gold structure there. This is also very, very stable. In this case, of course, we tested this kind of stability there. You can see gold is very, very stable. Let's go on PDMS and on silicon, peel off, or glass peel off. Let's go on pure PDMS, also peel off. But use our trap approach. Gold is very stable because it's kind of interlocking inside. So this is the way increase kind of stability. But of course, what structure behind that? In fact, this is something one kind of wrinkle structure. This wrinkle structures really like what? Like our skin, right? Skin lots of wrinkle structures. So that's why the PDMS is pretty stable there. And also the cross-section structure here, the PDMS composing materials, the gold film. Gold film ensure conductivity. This is ensure stability. This is kind of substrate for this kind of flexibility there. So overall structure come together, have this kind of highly stable and also stretchable conductors there. But of course, you also can further make a pattern, not necessarily film like this one. This could be pattern. And also we can use, my group is using this kind of jet printer together to print this kind of pattern gold electrodes on different substrates. But PDMS is also not so ideal. No, it cannot use for integration. Why? PDMS like this kind of paper, easy from crack, and then apply certain strength, crack will migrate. So that's something not ideal substrate, easy to have this kind of crack formation. So that's why we change another systems for this kind of thermoplastic elastomer, for this SCBS. SCBS have two kind of properties, elastomer like the PDMS, but also this kind of thermoplasticity. This allow have certain self-healing capability. It means apply certain force, the SCBS can self-heal together. This is the property SCBS do not have it, and PDMS do not have it. So in this case, recently we work with close with Gao Jian and also other group together. We develop this technology we call biphasic nano-disperse interface. This is one used for interconnections as we want now. So how we do it? Here you use this kind of SPS as substrate. We use our trap approach to deposit this kind of gold on SEBS substrates. So in this case, the some of gold particle will penetrate in the SEBS. And they have, so in this case, very important to have two components. First one is a gold exposed gold connection, make sure conductivity. And also another part is to have exposed SEBS, because once it bind together, SBS will cell heal. So this is also very important components. This is something that allow us to do this kind of solid, this kind of soft connection, soft rich connection, even can do this kind of incubation because this combined interface developments. So very important part for here, the trick here part about the density of the gold density on the SEBS surface. For gold density, you cannot be too low. If it's too low, you can see a lot of gold here, but a lot of SPS also exposed here. But once these two conductive put together, they stick together, but they cannot form this conductive parts. In this case, this is not good for this kind of connection. And also, if gold is too high condensed, in this case, they band together, cannot bind together because gold cannot bind together, right? So in this case, this also conductive but cannot bind. So you must have this kind of certain kind of densities there, allow this kind of interface can bind and also conductively. Of course, we spend a lot of time to build this kind of phase diagram of this kind of when it's time go to bind interface. Let's certain have this kind of thickness dependence and also the variation speed dependent to build this kind of interface there. So in short, so this is also we do this kind of on object, this kind of depth profiling to tell you in this kind of bind interface go how it looks like about this kind of density, compared with the non-adhesive, compared with the non-conductive, how this kind of gold distribution will be different on the SBS as well. And also we work project together, really we build a model to really understand how this kind of gold is really penetrated in this kind of SBS. So you can see just about 25 nanoseconds, the gold immediately form this kind of cluster. Of course, this is something new during this kind of nucleation process. They can form almost like this kind of 5 nanometer gold cluster in the SBS, and also quite large this kind of density. But of course, this is not enough. We really do not take a longer time. Modern is modern nanoseconds. For us, is we typically running for about 1,000 seconds. In this case, the gold particle will close to about 20 nanometer. The gold will penetrate in SBS about 100 nanometer. So this is allow this condition to really make sure this conductive parts when this can stick together. So this is something what we call biphasic network growth model to ensure how this can go connect together. So once this one done, of course, how it look like, right? Compared with the current commercial one. So with this kind of soft connection, we compare all this kind of commercial market available, this kind of commercial paste, silver paste or carbon tape or couple tape or whatever different tape you can see. The typically for this kind of mechanical stretchability is about 45% in terms of electrical stability, mechanical about 60%. But use our bind interface, we can reach almost 180% in terms of electrical stretchability, 600% about this kind of mechanical stretchability. So this can see, this is our work, this is compared to this kind of commercial current work. This is how advanced we can make it. But of course, not about soft connection. We also can do soft rigid connection. We also can do encapsulation. So this is something we want really explain a lot of this kind of capability. Then because this one, now we develop this kind of Lego-like integration, really had this kind of module-based approach. Typically, for one sensors like you just now sensing prepared, right? You need all together and then put in this kind of mouse for animal experiment. But for us, we don't need anymore. We just build all this kind of connection together first. You can leave this one last step. You really can put the tissue layer to wrap already and then connect it. Use our bind interface here. So this is typically how this kind of step can really reduce a lot of efforts. Module approach. Put this one on the tissue area. This one connect earlier and then just connect this part. So this is how our bind connection can help dramatically improve speed and also very stable as well. So give you one example about this kind of flow. Just now you can see this is about 21 channel of EMG. Now it's how this structure looks like, right? Much better now structures. And then we can really to have different module come together. And then, so let's just give you an idea about EMG parts. You can see very stable. The typical one also always a lot of noise connections, but for us, it's pretty stable. And also, even underwater, Now we can really underwater also can get reliable EMG signals. So this is kind of water with this kind of interference resistant lens. This is also very important for us experiment. And I'm not, because we put out almost 1 year for animal experiment. So we tried almost 5 different kind of animal experiment already now in the last 1.5 years. And then we try into this kind of organ size will range from centimeter up down to 100 nanometers. And then we try this kind of nerve recording this kind of muscles, cortex, egox detection, and also the bladder stimulation. So all these experiments is doing pretty well. The foundation is why? Because we put the sensor on the tissue first and do connection later. Different to the traditionally put everything first, assemble everything first and insert. So this is how our advancement comes with other kind of technology. So in short, so this kind of biointerface we feel is really kind of new paradigm for this kind of stretchable hybrid electronics. Yeah, many things can still work on based on this one. We're still working on it. And then this really can build about future Lego-like integration. Many things could be, of course, a lot of fundamental science questions we still want to address that. And then, of course, in optical integration, it's really, I want to go back to the very, very beginning movie, right? Just how do we remember we saw one movie about this kind of fingers, right? And we put all this kind of different, a lot of this kind of logic, this kind of line connections now. Now I can tell you we don't need to do any more. We can we're going to simplify this approach because with all this kind of technology can combine together. So of course we also address a few questions there about this kind of interface. Because you want to go to this kind of EMG signals, very important is your signals must be reliable enough, and also your impedance must be low enough. And then for this case, the fundamental question will be you must have this kind of electrodes with very low this kind of bioelectrical interface impedance length. And then how low you want to go it? We found the target for this kind of impedance on human skin is about 10 kilo ohm. And this is typically the current all this kind of report data. All this kind of impedance still a bit far away from the targets for the human skin needed. So recently we found one thing we just modified this kind of electropolymer, which is this kind of hydrogel, like with PVC and PVP. We found these two polymers have really interesting problem. It's called this kind of molecular anchoring. They can really, of course, this is because it's kind of hydrophilic balance there. They can somehow penetrate in this kind of stratum, this kind of corneas there. So this is allowed to really significantly lower this kind of impedance there. So this can see for this impedance can lower almost close to this kind of human skin, about 10 kilo ohm. And also very high adhesive, almost like close to 100 Newton per meter. Typically, it's about 50 to about 50 Newton per meter, but we can really have a 4 times increasement. And because this one, now we can really put this one on our gold electrodes, just like I tell you, then we really can get reliable signals, and like this movie is sold. So this is the kind of movie, use our electrodes. This electrodes use our this kind of pattern electrodes coating with this kind of polymers. And then we capture this kind of muscle signals. We have the 16 channel here. Then we use this channel to control this kind of robotics here to really grab this kind of the candle you want. You can see this signal is always intention, right? Because muscle, although he doesn't have hands, but question is still intention. So that's why we can capture muscle signals. Use this kind of muscle signals coupled with the algorithm developments. Then really can control this kind of a machine there. But of course, this experiment also takes us about a few years to really come out with this kind of proof concept. It really works. Just use the on-skin electrodes can really precisely control this kind of machines there. But many missing still going on. But of course, we're also looking for, maybe work with close with our Tsinghua side, really how we can really deploy such technology with more this kind of engineering perspective rather than science perspective there. Beyond this kind of integration, we also put a lot of this kind of plant sensors. I will not tell you how detailed it is. If you're interested, you can really refer this paper. This paper is just about how it's kind of electrodes to really electrically stimulate this kind of flat trap. Typically, flat trap is kind of mechanism sensitive. You need a touch 2 times close to flat trap there. But here we propose to do not use this kind of mechanical touch, use electrical stimulation, can really make this one close. Of course, it works. Now, even we can, moving forward step, can connect with the digital world. How connect it? Use this smartphone. We can really use smartphone to close the flat trap. Okay, inside is also involved many kind of integration, connection inside. So a lot of science and fundamental applications lab. And then we can even make even more fancy, can see really integration robots and really bio robots, right? To really capture the moving object, capture this kind of small parts. But this is important advancements because we understand how it works. Okay, so in short, sense the word, pursue the future, create endless possibility. But of course, foundations, we must work close together. Okay, thank you very much. I'm happy to, by the way, finally, this paper, right? So I feel this paper is very important for community. The technology roadmap of flexible sensors. It should be, my view is for a lot of graduate students, it's a must read paper, right? Especially want to in these flexible technology areas, because we are cover many top 10 emerging technology, right? So that's why you do not have reason, read this paper, promote this paper as well. Okay. Okay, thank you very much. Yeah.
Okay, thank you for the wonderful talk. Now it's question time. Okay, first question. How many institutes in the last paper?
142 authors.
How many institutes?
No idea. Or maybe if we don't know. Less than 100.
Yeah, very impressive talk. So I'm wondering, how do you bind two SCBS together? Is it because there are some solvents still within the?
We just have like go on SBS, right? And then just stick, use a certain force just apply on top.
So it's the gold nanoparticles penetrating into the another layers.
Yes, exactly.
Okay.
Also, the SCBS also penetrate with another SCBS.
Okay.
The SCBS has kind of cell healing capabilities there.
Is there any required minimum force to make them to?
Not really, just a simple, just touch. We didn't quantify how much force we didn't really need it, but with gentle should be enough. Yeah.
Okay, thank you.
Yeah.
Okay. Go.
Very exciting talk. So your human robotic control, right? The arm control. You said, did I miss that? You said the electron skin.
Yes.
So electron skin will pick up the muscle signal.
Muscle signals.
So it's like picking a signal. How does it transmit the signal?
Because but of course this one we help with the algorithm, right? Because every action here, you also generate kind of muscle. It's called EMG.
Yeah.
So that's why.
So through EMG.
Through EMG.
Pick up EMG signal.
Pick up EMG signals. Okay. And they use less EMG signals to control the process.
Okay. So I thought it maybe by some muscle contraction. It's not.
In fact, it's a muscle contraction, right? All action is kind of.
But it's not through mechanical contraction. It's through EMG, right? The electrical.
Yeah, electrical stimulation. Yeah.
Any more questions?
People can always go dinner.
So just in the micro E domain, right? So when we do the heterogeneous integration, those let's say to the VR TSV collection. I mean, similar to the TSV collection, we will do the intercollect. Any more precise modeling work need to be done, like the modeling the impedance, modeling the thermal effect. We'll consider this kind of, just put together and do the intercollection.
Yes or no, right? I mean, yes, for a whole system is very important, master discount modeling, and then no at this moment because we do have a manpower, we do have a funding to do all that parts. Unless, give us some support, then we really can consider that part, right? Because why I say this way, because in this, at this moment, there are many things we can do it. Then we have to choose some of our project will be easy with less funding support.
Okay, thank you.
I have a question about the band interface. My question is the band is reversible?
No, it's one time.
Yeah, okay.
Yeah, that's how we can make money.
Okay. Yeah, it seems like for logo, it's every piece is reversible. You know.
Yeah, but the question we have for let's make reason self-healing is not allow us to do that one. Yeah.
Okay. Okay. Thank you.
No problem.
Okay, so if no more question, let's send all the people the whole day.
Okay, the workshop is completed. So for the dinner, the people who attend the dinner, please wait inside. Oh, maybe you can.
Just wait near the back door and we'll go to the bus pickup point together. And our sponsor, Premier Solution, they prepare some USB drive as gift. So it's first take is behind. Also, there are some brochures. Take it if you are interested.